participants, and dear students. It is a delightful moment to extend my warm welcome to all of you. Before we proceed, I would like to take this opportunity to share with you a brief introduction about ourselves. Akal University, under the leadership of Baba Iqbal Singh Ji Kalgi the Trust, Badu Sahib, has started its sixth academic session this year. The mission and vision of this university is not merely to impart literacy, but also to provide high quality, spiritual value based education. The Kal University has mandated to uphold the three basic principles of higher education, namely teaching, learning, and research. The ultra modern facilities for teaching and research are the hallmark of university. Now, I would like to give a brief introduction about our Department of Chemistry. Our department has been established to foster education and research to meet the growing demand for qualified and efficient individuals in the country and across the globe. The department offers undergraduate and postgraduate courses with honor stream. The department strives to provide national ambience in a local setting. A mentoring-based teaching method is followed, where each student is personally guided so that he or she can reach its true potential. Special coaching classes for NET exams are routinely conducted in the department. Research projects and practical oriented teachings are supported with the help of an able lab infrastructure. Staying true to our social commitment, the department conducted research projects on various local issues such as water and soil pollution. The department is supported by an exceptionally qualified and motivated faculty with a strong commitment to teaching and research. All faculty members hold PhD degrees, with most of them having postdoctoral experience from reputed institutions in India or abroad. Ladies and gentlemen, in previous years or sessions, our department has organized a number of webinars, including nanotechnology with healthcare, carbon dioxide utilization, and applications of bioinorganic chemistry. These webinars provide a venue for stakeholders working in chemistry to share practices, ideas, and resources. To maintain the continuity of learning, we plan today's virtual national conference on recent trends in green chemistry to benefit our students and students across the nation. Sustainable and green chemistry, in very simple terms, is just a different way of thinking about how chemistry and chemical engineering can be done. Over the years, different principles have been proposed that can be used when we think about the design, development, and implementation of chemical products and processes. These principles enable researchers to protect and benefit the economy, society, and the environment by finding creative and innovative ways to reduce waste, conserve energy, and discover replacement for hazardous substances. To protect our mother nature from the ever increasing chemical pollutants, scientists are restlessly developing and modifying the chemical processes to make them sustainable. Under this preview, interactions with distinguished scientists might bring opportunity to learn many new things of today's research. So, this one-day national conference on recent trends in green chemistry will be very helpful for all the learners. The main aim of this conference is to offer an understanding of recent developments using green methods. People working in the fields of green and sustainable development, bioresource, natural products, drug design, catalysis, and modern scientific design will be benefited through this conference. With deep sense of appreciation, I am grateful to all our distinguished speakers for accepting our invitation and sparing their valuable time for our learners. With these words, I extend my warm welcome to our honored speakers, Professor A.K. Chakrabarti, Professor B.C. Rano, Dr. Navjeet Kaur, and Professor V. Jayatirtha Rao, sir. Dear sir, thank you for accepting our invitation on such a short period of notice. Next, I would like to give my sincere gratitude to our Honorable Vice Chancellor, sir, who encouraged us and support us to organize this virtual conference. Now, I would like to request our Professor Shantanu Ghosh, officiating Dean Research, Akal University, to give his valuable insight on today's event. Over to you, sir. Thank you. Yes.
Visual. Yes. Okay. Uh, Good morning to all. And I take this opportunity to, uh, first of all, congratulate the Department of Chemistry for organizing this one-day virtual conference on green chemistry, the recent trends. And I also extend my heartiest welcome to our distinguished speakers. Uh, the first speaker, who is Professor A.K. Chakrabarty. So welcome to this one-day virtual conference. This effort by the Department of Chemistry is part of our commitment to foster uh, the research ethos at our university and to cultivate the students' commitment towards science. As many distinguished scholars have suggested, science is about asking the most basic questions with the most basic methodology, and it is about knowing about us and knowing about nature. So, in depth questions are the hallmark of a good scientific question. In fact, green chemistry is one of the major areas of the thrust areas of the government of India today because of obvious reasons of uh, environmental pollution and also about the what do you call it, global warming that is happening because of these pollutions. And I guess one of the major concerns that we have today is to how to sequester carbon. So one of the thrust areas for technology by the government of India is also about how to conduct experiments in basic and material sciences to expert to generate the expertise about these green methods of green chemistry. So chemical reactions also would contribute towards making of better batteries for electric current storage, which will be the hallmark of green transportation. So a lot of research is being done in those aspects as well. Uh, so our distinguished lines of speakers today, uh, we are happy to share with our students their expertise, and I again take this opportunity to extend my heartiest congratulations to the Department of Chemistry. I wish all the success to this one-day national workshop. Thank you, Dr. Dr. Bubun.
Very good morning to all of you. Thank you so much, Dr. Sandeep sir and Dr. Santani sir, for giving me this opportunity to welcome Professor Chakraborty. Uh, Means it is very difficult to describe Professor Chakraborty's achievements within a few minutes, but still, I want to share one slide. You can see. First of all, thank you so much, Ashit sir, for giving us this opportunity, and for we will definitely learn many things from your lecture, and our students will definitely enjoy your lecture. Thank you so much. So,
Sir, can you share the slide? First open that slide, then go
give
to
me
share.
just 1 minute.
You want to share this?
Yeah.
So you could share and I just make it share till that particular
Yeah. Thank you.
image.
Oh, so Professor Chakraborty, sir, obtained his master's degree in 1977, and I think it is much before than all of us when take birth, at least means at least I born 1987, so 10 years before he completed his master degree from University of Bardhaman. Then he obtained his PhD degree from Cultivation of Science, Kolkata, 1985. And after that, he did two postdocs. One is from the Clemson University, USA, 1985 to 1987, and then Purdue University, Indiana, in 1987 to 1989. Then after, he joined Bardhaman University as assistant professor, and he served almost 4 years, 1990 to 1994. And then later he joined in the Department of Medicinal Chemistry, NIPAR, Mohali. And till he served up to 2019, from 1994 to 2019, he was there. He was the departmental head of this medicinal chemistry department. He received so many awards, and I think he deserves to receive many more. And he published more than 180 research articles. All are in internationally reputed journals having good impact factor. He supervised more than um, more than 40 PhD students, 130 master's degree students, and uh, he filed 42 patents. Okay, and for our student, it gives me immense pleasure to inform you that our one of my our faculty, Bajinder sir, is received PhD from Professor Chakraborty. And Professor Chakraborty research interest is he basically synthesized many new novel compounds through CH bond activation, different catalysis using ionic liquids and aqueous mediated water. And he has screened all those synthesis compound for different biological activities like anti-tuberculosis, anti-inflammatory, and many more. So with this short introduction, I'm again welcome you, sir. Thank you so much. Now I'm stop sharing my slide, and now you can share your um, slides, sir. Thank you. Over to you, sir.
Thank you, Bhuvan, and your colleagues. Uh, in the Akal University to give me an opportunity to discuss with you the green chemistry, particularly sustainable chemistry. I am sharing my screen. Do you see the screen?
Yes, sir.
Okay, let me put full screen then. All right, I think the screen is full now. So in this one-day virtual national conference on recent trends in green chemistry, organized by the Department of Chemistry, Akal University, Bhatinda. Bhatinda is a place which I have visited very frequently. There is a neighboring university, Central University of Punjab, Bhatinda. So in this context, I visited. So I like Bhatinda, and I'm very happy that an Akal University, as a private university, also is making an impact in the overall education in that part of the country. So why a green chemistry? So chemistry, particularly organic chemistry, is in the center stage of any application of the chemistry. And it looks like that drug development and discovery happens to be the major stakeholder of the exercise of any form of chemistry, particularly organic chemistry. Though it has to amalgamate several key areas, particularly in the drug metabolism and chemical toxicology. But as we see that due to the preparation and usage of drugs and pharmaceuticals, there has been a severe adverse impact of these chemicals on the environment. And this slide demonstrates that the waste produced, which is defined by the E factor, means the total waste produced per unit of the desired product. And the major chemical industries are very much polluting. So if we leave out oil refining industry, which is the first entry in this E factor across the chemical industry, remaining three entries, bulk chemicals, fine chemicals, and pharmaceuticals, all these are intimately associated with the various kinds of execution of the chemical processes. So looks like that those are very detrimental in the context of producing a lot of adverse waste and polluting the environment. So that is the reason we have to do the chemistry for the comfort of life. But what is required? Chemistry has to be executed in the right way. So that means how to avoid the adverse effect of the chemical research on the environment. It is in this context the need to integrate the green chemistry with the drug discovery and development in a particular, or in any chemical development in particular, is essential. It has been recognized, and accordingly in 1991, green chemistry becomes a formal focus through the agency called Environmental Protective Agency, which is housed in United States of America. Though this is a regulatory agency, it does not regulate your activity. What it does, it encourages new technologies and processes, and most importantly, it never says you not to do it, but it says you how to do it in a better way. So it inspires chemists to devise greener reaction condition for the old synthesis. It also suggests that develop green synthesis for the existing commodity chemicals and design new compounds that are less toxic, but with the same or better physical properties of the existing compound, mostly as a drug-like property or maybe other materialistic property. So it does promote to do the chemistry in a more effective way. So the green chemistry it utilizes a set of principles to reduce or eliminate the use, sorry, my upstairs there is some work is going on, the use of generation of hazardous substances in the design, manufacture and application of chemical products. And it is intimately associated with the sustainable development, because it tells you that how to meet the economic, environmental and social needs of the present generation without compromising the ability of the future generation to meet their own need. So green chemistry appears to be a practical approach to reduce all the adverse effects of the chemical processes on the environment. And according to the ACS vision of green chemistry, it is nothing but improving people's lives through the transforming power of chemistry. So that is the reason green chemistry, whose primary objective is to protect the environment, to provide a quality life, and is intimately associated with the human welfare. So that is the reason it is another form of the sustainable development when it comes in the domain of the exercise in chemistry, and it is the major driver for the development of the modern chemistry. So it is in this context, I thought that let me discuss with you some principles as well as some practices also, that what are the sustainable chemical research in academics, particularly in the context of development of the new concept and their application. The greenness of a particular chemical processes is divided by various matrices. These are the 7 matrices. Out of these, the 5 matrices are very much controllable under the domain of the chemical exercise. Incidentally, the first matrix, which is though not effective compared to the other one, the effective mass yield was proposed by none other than by the person Thomas Woodley, with whom our next speaker, Professor B.C. Ranu, was associated during his postdoctoral research in the United States of America. But at the same time, one has to keep it in mind, there are 12 principles of the green chemistry, and similarly, there are 12 principles of the green engineering. So, but it is not possible that for a particular chemical process, it is going to address all the 12 principles of the green chemistry. But what it can provide a checklist with the help of which one can make a qualitative and also quantitative assessment of a newly devised process, to what extent it might be greener compared to the existing processes. Therefore, whether a reaction is green is highly subjective based on the specific synthetic situation in global context of synthesis. Like in some cases, it might be making the product in 100% yield might be the better one. But depending on the context, it may not be yield, may not be the criteria. These are the ways one have to look into the various ways to assess the greenness of a particular process. So the green index of a overall process is decided by a priority, the 5-point agenda, like consumption of resources, energy, undesirable effects on the human being and the ecosystems, and various kinds of safety. This safety is not only the safety of the consumer, these safeties are also associated with the various people who are involved intimately in the preparation of those commodities or the product. Coming to the chemical manufacturing processes, in the industry, R&D, they state forward, they try to address these 6 agenda appears to be the very obvious way to get entry into the sustainability of the chemical processes, which are stoichiometric to the catalytic reaction. I'll give you a few examples. Multi-step to fewer step roads, liquid acid-base to solid acid-base catalyst so that it can be reused and recycled. I'll give 1 or 2 examples. Safer processes, avoiding dangerous toxic reagent and byproducts. Entry number 5 happens to be the very common way to address the greenness of a particular chemical manufacturing process, which is called improvement of the reaction media, which proposes, if not the solvent-free reaction, there might be some issue in the bulk production for the heat transfer issue, but it might be that can you adapt a environmental alternative reaction media, which might be environmental benign, like water, supercritical media, ionic liquid, and etc. And of course, adapting routes of higher atom utilization economy. Moment we adapt the catalytic process, to some extent it addresses the atom economy. But I'll give 1 or 2 examples in a specific atom economy. So then question is coming that how to address green chemistry or how to implement a sustainable chemistry in the academic research. I gave you this example. Now these are with reference to the finished product which are produced in the bulk quantities, like in industrial process, in the context of the drugs and pharmaceuticals, but it does not take into account all those exercises. Like it says that this is called the drug discovery funnel. So it says that probably around 10,000 compounds of diverse chemical structure if one synthesize, and if luck goes, then one might come up with one drug molecule which will come to the market. So when you go to these statistics for the pharmaceuticals, it is that particular finished product, but it does not take into account of the remaining molecules, which is a completely diverse chemistry. The exercise goes in the discovery phase in the industry as well as in academia. So there also, if the chemistry adapted are not complying with the green chemistry principle or the sustainable ways, we are going to generate a lot of adverse effect on the environment. That is the reason, not only in the industrial sector, it is also necessary to address those issues in the academic sector also. Generally, we talk about the bulk production, though it addresses very nicely that where is the scope of addressing to some extent the sustainability of greenness while doing academic research also, or the discovery research, while the scale of the reactions conducted at the early stage of program, which is called normally discovery medicinal chemistry, either in the industry or in the academia, is usually small. But the cumulative footprints generated by tens or hundreds of laboratories in pharmaceutical company, it has not counted like Akala University Chemistry Department, NIPAR, and etc. for that one. So that becomes a significant impact. Moreover, the delay that might incur the post-marketing and making it a scalable product to re-engineering the discovery process, then you might lose the credibility by this time your product is coming to the market, some competitive stuff. So both in the context of the environmental aspect and at the same time, a smarter strategy to bring the market as quickly as possible, it is necessary to address those issues. So this nice article very nicely demonstrates where is the scope of addressing sustainability or green chemistry in academic research. All these 4 gentlemen were synthetic organic chemists and CEOs of the corresponding companies like AstraZeneca, Pfizer, Glaxo, etc. So what they did, they have analyzed that the various chemical processes or chemical routes which are adapted in making their best selling product, which are the drug molecules. And that gives you that these are the various unique processes, like various kinds of reactions, and that can give you scope. Like these are the popularly very frequently used organic transformation or chemical transformations which are constituting the processes, and you have enough scope to implement each and every of these ones, so you can adapt in your discovery chemistry or maybe in the academic research and try to contribute a greenness or sustainability of chemical research. So that is the reason there has been a lot of sensitizing article like this one, which tells that green chemistry tools to influence a medicinal chemistry and any chemistry-based research organization. in the context of the discovery chemistry, like medicinal chemistry, where I belong to, generally there is a misconception that you need not to do all those things. All these things has been done by the best organic chemistry school. All you have to do is somehow take those chemistry and make a few milligram of compound and give it to the pharmacologist. So to sensitize this mindset, this nice article has come. What it tells, it prompts areas of further synthetic research to suggest that chemistries that are at present underrepresented and are in clear and robust need of clear and robust, reliable and widely applicable methodology, you try to contribute new knowledge in the chemistry. It also suggests that even there might be already tried and tested procedure which are even widely employed also, but try to improve it where there is a clear deficiencies in areas such as atomic economy and safety. So it is not merely a responsibility of the industry sector, the academicians, either in the academic institution or in the discovery phase chemistry in the industry. Now the question is that how do you contribute? Like if I take into this one that in the Akal University for that or many other private universities, so you do not expect to have a similar kind of infrastructure to take a very complicated research program for that. But what you can do, you can provide, and if you are becoming a little bit careful and completely aware about the chemistry. So what you have to do, you have to be very much careful about the knowledgeable about the chemistry and the background. Then I'll take a very simple example and then tell you that one, how even with a not to the state of the art infrastructure, one can contribute to the knowledge of green chemistry. So the conservation of atom economy. Dimethyl sulfates happens to be an industrially popular alkylating agent. As a matter of fact, I have done myself in my PhD thesis during my PhD work. So majority of the cases, steroid and terpene synthesis, that AB ring system comes from the beta naphthol. Beta naphthol has to be converted to the corresponding beta naphthol methyl ether called nerolin, and then you do all the Friedrich reaction, halogenation reaction, try to do that. And if you do the methylation reaction using dimethyl sulfate, it is done by aqueous sodium hydroxide, and large amount of sodium hydroxide is required to make the reaction condition overall alkaline. But most importantly, in dimethyl sulfate or any dialkyl sulfate, there are two alkyl groups which can be transferred to the corresponding phenol. But if you take sodium hydroxide, only one of the alkyl group is transferred to the final product, and other half is lost as a sodium methyl sulfate because it becomes water soluble. We thought that, is it possible we can replace sodium hydroxide by lithium hydroxide? So in that case, we are going to generate the lithium salt of the phenol, and then lithium being a coordinating in nature, it is going to make this kind of 6-member coordinated complexes with dimethyl sulfate. It is not only going to make it much more effective, it is bringing close to this one. So it is going to first methyl transfer will take place, and the other methyl group is going to be liberated as a lithium methyl sulfate. Now, since lithium methyl sulfate still has a possibility to undergo chelation reaction, it will undergo again interaction with the phenolate molecule, and then ultimately second molecule is going to discover. So it becomes a atom economic transfer of the two alkyl group of dimethyl sulfate. Reaction works very nicely. Only solvent is used is a THA. Very clean reaction. And at the same time, it came into our knowledge, the survey of the good manufacturing practice, GMP stands for good manufacturing practice, bulk reactions in a research facility during this period, 1985 to 2002. So what they have done, they have segregated the various kinds of unit chemical reactions and found out that conversion of carboxylic acid, like either you make esters or ester make carboxylic acid, that constitute close to 1/4 of the overall GMP reactions. So we thought that then since we used to do this very routinely, whenever you have a carboxylic acid in your academic research and you wanted to identify if the carboxylic acid or not, very easy way to identify will be convert into the corresponding methyl ester. And the popular way in the academic institution was that you convert into by diazomethane, treat with diazomethane. Diazomethane is not a storable material; it's a gaseous material. You have to make the corresponding precursor N-methyl N-nitrosourea, we used to call NMU. Professor Nanu and myself overlapped for some time during our PhD work, and both of us used to have at least 500 grams of the stock material. We used to preserve in an amber color bottle in the refrigerator because we have to very routinely do this exercise. But NMU nowadays is considered, at the time that kind of awareness are not there. So, but NMU now is going to be extremely carcinogenic, and most importantly, the diazomethane being a gas, it becomes very difficult for you to control. And always we used to inhale because we used to get the smell of the diazomethane. The moment you are getting the smell means you are inhaling the diazomethane. So we found out that this protocol, lithium hydroxide dual activation protocol, can be very efficient way for the replacement of the or alternative to the toxic diazomethane protocol. So here also, the lithium hydroxide is going to make the lithium salt, and then due to the chelation, the similar way due to the 6-member transition state, both the methyl group is going to be transferred to the. So it became a very nice way to demonstrate. Here also the reaction was THF as a very clean reaction. So let me give you a few example of the stoichiometric to a catalytic reaction. In early stage of my tenure at Naipan Mohali, we had focused on making this compound because at this time, 1994, a natural product, licochalcone, was isolated from lico-rice root. Till today, there is only one drug for leishmania, is miltefosine, but still having a lot of adverse effect. So this licochalcone was found to be a very good active molecule regarding leishmania. So at that time, it was an investigation, and that is the reason our focus was to prepare a large number of chalcone and see can we get a best active molecule. And that is the reason. And later on, we would have found out that you name any kind of biological activity that people have not tried to making it and use of this one. These are a few representatives at the time. And nowadays, hardly you will find out any research publication which comes in BMCL or organic chemistry, medicinal chemistry letters, where at least one or two issues does not deal with the preparation of the chalcone and their biological activity. So since we had to make it, it's a very simple reaction. The textbook chemistry reaction is a Claisen-Smith condensation reaction, and we have gone through the literature, found out that these are going to be a potential or maybe a notable disadvantage of the chemistry which has adapted that one. So we thought that can we put into use the dual activation role of lithium hydroxide and use it in catalytic amount, not in a stoichiometric amount. So philosophy was like this. The first catalytic amount of lithium hydroxide is going to react with the acetophenone, right, number one, to make the corresponding lithium salt. And this is going to now make a 6-member chelated transition state with the aldehyde. And through the aldolate, the reaction will go. Now, this aldolate in turn can act as a base, so we don't need another lithium hydroxide. So now this aldolate will undergo proton exchange reaction, which again want to make the aldolate, and this is the way the reaction will go. So the entire process depends upon the number one, particularly the formation of the transition state 2, or more importantly, to put 3 into the catalytic cycle is through the chelated transition state 4. And the entire credibility should depend upon that how effectively the metal cation, in this case lithium, is going to be served as the chelating agent. So when we replace lithium hydroxide by any other alkali metal or alkaline earth metal hydroxide, the reaction doesn't work in catalytic amount. You need a more than stoichiometric amount. So only it works in a catalytic amount around 10 mole% in ethanol as a solvent, and the resin being the same thing. Only lithium amongst all this thing has the capability to hold tightly the transition state 4, and that is the reason it acts in catalytic amount. Then we found out there are a lot of people are designing this kind of compounds with the pretext that they are equivalent to the curcumin, but they are not exactly curcumin. So then these are called bis chalcone, and we found out the same chemistry can be adapted to make the bis chalcone, and again the credibility depends upon the chelated effect of the chelation effect of the lithium cation. So with this we made it, and we realized that the best active compound is going to having when we have in one of the aromatic ring have a large number of methoxy group, but there is a problem. We found out it is very difficult to test those molecules in the aqueous condition because it tends to precipitate. And we thought that one way will be, can we increase the hydrophilicity, and one will be that can you at least one of the methoxy group, not all of them, can be converted to hydroxy group. So then we need an hydroxy chalcone, and we realized in the literature this is the way to make the hydroxy chalcone. It is very difficult to make a clean synthesis of the chalcone by condensation of an hydroxyaldehyde with gas. Still, it is a potential issue to make a very efficient synthesis. Sometimes it works, lithium hydroxide, but not all the combination. So what has been found out, the people who are trying to make this compound for various kinds of biological evaluation, they are taking that hydroxyaldehyde protect with the THP protection group, and there we need a costly catalyst, and most importantly, this reaction is performed in halogenated solvent. So there is we found out that is it possible that this is the way people are doing it. So these are the various literature. So we thought that no, let's do one thing, that we do not protect with the THP, we protect with the methyl sulfate, we have a methodology, and then finally, can we do the deprotection, and what could be the deprotection? Now, Green's book provides you a large array of synthetic methodologies, and we found out that when it comes to the real application for making the biological active compound or applying the same demethylation protocol for your synthetic design, both in pure organic chemistry school like this JOC and JAX paper, or in case of the medicinal chemistry school, we found out that stoichiometric phthalate anions are a very good popular reagent. Like in this case, you make the normally isopropyl salt, make the sodium salt. So this is the popular reagent when it comes a real application of this demethylation strategy. And we found out this is a major problem like HMPA and etc. for that. So here is a case on our hand that we found out that probably can we convert a stoichiometric reaction to a catalytic processes. So what we thought that we need, let's take say aliphatic thal, there is a problem, they are low molecular thal, they are very much stinky, it becomes very difficult to handle them. Comparatively, aromatic thals are, since their volatility is less and they are less stinky also, still there are some smell, but not as bad as isopropyl thal or ketone thal or propanthal. We thought that if we take potassium carbonate to start with catalytic amount, potassium carbonate being a base and thal generally acidic in nature, it will undergo acid-base reaction to make the phthalate anion. Phthalate became a very good nucleophile, will undergo nucleophilic attack over here, and it is going to make the byproduct over here. That is anyway, we cannot avoid this one. And you are getting that aryl oxide anion. Now, is it possible now to make a proton exchange between the remaining unreacted thal and with the in situ generated aryl oxide anion, so that we do not have to add a large amount of potassium carbonate? So we found out that yes, the reaction works. And later on, we found out that potassium carbonate can be replaced by potassium chloride also. And the reason will be clear when we go for the, what is the protocol? The protocol is that you have to take NMP as a solvent, heat at its boiling point, generally 196 degrees centigrade, so boiling at 202 degrees, bath temperature 196, it works very well. Half an hour, the reaction was quantitatively. That this is not merely a temperature effect was found out before. If you take diphenyl ether, whose boiling point is 260 degrees centigrade, the reaction works, does not work at all, right? We have to take NMP. So here we found out that solvent plays a very important role. When the organic chemists normally consider the use of a solvent, we only focus on these two parameters for their polarity, dielectric constant or a dipole moment. But there are three other physical constants who they actually are responsible for making them a really molecular. These are called normally molecular solvent because they interact molecule to molecule basis with the solute. That's the reason they are called molecular solvent. Other category of solvent like ionic ligand, etc., those are called bulk solvent. It is their bulk property which actually gives the solvent a character. So molecular polarizability, it was known by physical organic chemists long back, but somehow it was not taken into consideration by the organic chemistry. And we found out that it is the combination of the molecular polarizability, donor number and acceptor number, because of which NMP becomes the next best solvent next to the HMPA. So that is the reason in case of NMP, this is going to be the relative stabilization of phthalate anion. So phthalate anion is going to be much more easily formed in case of NMP. So that is the role of the solvent. We did find out that reaction can be very well sensitive to the Hammett substrate constant. I'll come back to this one later on. So with that, what it provides you in a competitive environment. If there are two methoxy group in a two different chemical environment, you can selectively demethylate one. Like in this case, that it does not demethylate this one, it is this one, or oxime versus aryl methyl ether. Selectively, the aryl methyl is going to be protected. That is the contribution of the substitution coefficient. So then we thought that phenols are sometimes also protected as a aryl ester also, like acetylate or benzoate and etc. Can the same chemistry be adapted? Yes, the same chemistry can be adapted because what it does, it undergoes nucleophilic substitution reaction here, and remaining chemistry remains the same thing. Now, since we are using NMP as a solvent, these are aprotic polar solvents. Since they are cation-specific solvents, so the moment they trap the potassium cation, since F minus is being generated, these are normally called a naked anion, this acts as a base. So the potassium carbonate can be replaced by potassium chloride. So truly it becomes a neutral condition for the dealkylation reaction and non-aqueous condition. So we found out that yes, it provides you an additional advantage. In the same molecule, you have an aryl ester, like phenol has been protected as ester or alkyl, then selectively you can deprotect one. That might be useful in a competitive cases where you have to keep one methoxy group intact. So then again, the green chemistry research areas in the perspective of pharmaceutical manufacturers, we find out, although we have done this thing earlier, but we can find out very good support of why we have extended the chemistry. Demethylation reaction or ester hydrolysis is a very commonly used reaction in the perspective of pharmaceutical manufacturing processes. We thought that can we put into use our non-hydrolytic cleavage of the methyl ester? Because since half-phenolate is a very good nucleophile, it is going to react with the methyl. Now carboxylate anion is a much better leaving group compared to the phenol. So reaction should progress efficiently. Only issue comes over there. Earlier it was a proton exchange to make it a catalytic. There was involving proton exchange between thiol and a phenol, and we know thiols are more acidic than phenol, so there is no problem to have a proton exchange. But now it is a proton exchange between a carboxylate anion and the thiol. And we know carboxylic acid are better bronze state acid than thiol. So why then the proton exchange should take place? And here is another role of the solvent in controlling your chemical reactivity. When you talk about the pK value, those are basically in aqueous media. So moment we are changing the media from aqueous condition to aquatic polar condition, then which was a better protic acid in an aqueous media become an inferior protic acid in a aquatic polar media. So much so, if we compare the relative acidity, bronze state acidity of thiophenol versus acetic acid, this is their position. That means thiophenol is going to act as a better acid. That means thiophenate anion will be generated by proton exchange, and the reaction works very well. But then when we extended our chemistry in a real situation where we want to have one hydroxy in one thing, we find out that we got it, but we end up with a mixture of dihydroxy and monohydroxy. Dihydroxy can be very easily separated by chemical process or might be the column chromatography also, but it's very difficult to separate these two monohydroxy compounds. So theoretically, we have a very nicely exploited this hydroxy is going to be effectively more efficiently cleaved selectively, but we could not get a separation. Only with the help of GCMS analysis, we did find out that in fact there is a mixture of 68 and 32. So purpose didn't serve when we were taking both the methoxy group, but then we take into account that it is possible that one become an aryl ester, other become an alkyl ether, then we can selectively deprotect the aryl ester. So then we thought that is it possible we generate the starting metal in such a way that one aromatic moiety will be aryl ester, other is an alkyl ether. So this is going to be the case, one case which has been protected aryl ester and other. So here came our exercise that how do you protect the aryl ester. By this time, we have started this one that only this was the catalyst known popular organic chemists for doing acylation reaction for dimethylaminopyridine because it activates through nucleophilic attack on the anhydride or acid chloride. And these are the problem. This is the LD50 value is very small. That is a highly toxic material apart from its mutagenicity. And nowadays it is a banned chemical entity also. So here is a case we found out. We went to the literature to find out that there are no other catalysts. Only one paper was published, and incidentally we are going for an electrophilic activation, and incidentally from India, from Kanpur IIT, from Javed Iqbal's group, which has used cobalt catalyst, but there is a redox chemistry involved there, although they have used various kinds of acylation reactions. So that gave us that necessity to do this thing, and that ultimately we have found out maybe more than half a dozen of publications, right? But I'll bring your attention to the last catalyst, which is called percuasive acid silica gel. So we have now, based on the which one is very easy to carry out, we do those reactions, and we have made our compound, and compounds are subjected to antilational activity, and that data I'm not going to discuss right now. So now, after having this, we thought that what is our, actually we have some issue, we have sorted our issue to make our compound, but is that the only contribution we have done? So what is the contribution towards the chemistry knowledge? Since we are doing medicinal chemistry, and many people have a confusion that whether medicinal chemistry and organic chemistry are the same or not. It is. Inside the medicinal chemistry, there has to be a very thoroughly knowledgeable and skillful organic chemistry. And this article has been written by Paul Lawson, which is the director of AstraZeneca head. Maybe, I don't know, he might be chemist also. It also says at the same time it is important that medicinal chemists continue to develop their core expertise of synthetic organic chemistry. It is also one of the moral responsibility of the medicinal chemist to contribute new knowledge of organic chemistry. Not like that is to be done only by organic chemistry, basic science discipline. So then we found out these two catalysts. We were happy making our compound and we forgot about our catalyst. But later on, we found out you name any reactions, any synthesis, etc. These are a representative, maybe I have done 10 years back and etc. That our catalyst has not been done. You name any CSR laboratory, including IICT, IITs like IIT Guwahati, IIT Kanpur, carbohydrate chemists abroad, and etc. They have not used our catalyst in a different form for that. So that is the. As a matter of fact, I know through my students, there are some scientists at the time, they used to prepare 5 kg of my catalyst and put it, because whenever they have to think about any heterocyclic chemistry, etc., first they have to try this one, which I never did that thing. But later on, we have extended this thing for a maybe about 5 or 6 different reactions. Similarly, another catalyst, which is a little bit milder, but HBA for silica gel also has attracted so many people in Central University, State University, across the country, even beyond the country also, they put to use our catalyst for their purposes. So that is the contribution we have done to the chemistry. We talked about it that we call demand-based thiolate and generation chemistry, right? Now, this happens to be a research article published by my close friend who retired from chemical biology. So at the time, this was the target molecule, and this is the first total synthesis was aimed by Professor Ashish Banerjee. And at the time, he was in IECB. When I used to occasionally visit, he has narrated me for that. Incidentally, my advisor was at the time there, and I used to send him time to time my research article. So one day what he told me, whatever the reagent has been put into the Green's book and whatever could be imported at the time from the India, he has tried everything. It gives a messy reaction. So at that time, then my teacher told that, why don't you try Ashit's demand and supply? So he used to use the word demand and supply. And it worked very well for that. So then what I said that you are bothered by demethylation. When nothing works, try the demand-based thiolate and ion generation. So this is the contribution apart from our own need to the chemistry literature. I'll give you this one Now this is the thing we did. So by this time, I forget about my chemistry. I was in NIPER and I got an email from Douglas Tabor. Those people who have worked in the carbon chemistry or keep track on the carbon chemistry, Douglas Tabor is one of the pioneers in doing a lot of fundamentals of the rhodium acid catalyzed reactions. So he asked me a NMR of one of the compounds. And what I found out, that compound carbon-13 NMR was not reported. So I got concerned that probably there is a problem in the matching the data. And the reason is that this reaction was initiated in my previous place of Bourbon University, where I didn't have an NMR for that one. So through some limited efforts, including requesting Professor Ranu and etc., only the bare minimum we have to do the NMR, where we could not prepare the standard reference compound. Wherever we could prepare the standard reference compound to other men, we used to prepare the compound, check their melting point, and compare the literature and do the comparative IR study with our product. So we realized, so what we did nicely 2D, 3D, all the data for that, and I have sent all the details to Professor Tabor. We thanking for your interest in our work. He said that first, thank you for giving attention to my request and giving all the data. But I have retired 5-6 years back, but now I am teaching. And I have given a CUME examination to the PhD student. Those people who are aware about the CUME examination, the PhD in the United States, is the toughest examination. Right? The syllabus is like last 10 years, all the journal of organic chemistry. So he has picked up my paper and he said that there is a very good correlation between your reaction rate and the corresponding carbon-13 data for that. Only I found out the carbon-13 data of that compounds are not there. That is the reason I was doing. So it looks like that it has brought the attention for the people, and primarily because the chemistry behind that. So this also you have to keep it in mind that not only you should join the bandwagon, just everybody is doing green chemistry, let me also do the green chemistry, then impact will not be there. You do the green chemistry, but try to find out in which way your chemistry is going to catch the attention of your people, apart from you are solving your problem, getting a publication, making the compound, whatever it is. So let me give you a couple of examples of the atom waste. So first principle of the green chemistry is the minimization of the waste. If not, you can completely stop making the waste formation. I have talked about so much proudly about the sulfur chemistry. The major problem with handling the sulfur compound, particularly aromatic sulfur compound, is that once you open the vial for longer period of time, it will be aerial oxidation to make the disulfide, like diphenyl disulfide. 2-methoxyphenol is very much prone to undergo aerial oxidative cleavage, and the solid material, whatever accumulates in the screw cap, is actually the corresponding sulfide. We thought that can we make the disulfide? By this time, a couple of papers came, including one from the IC Bangalore also. Very complicated chemistry to make in situ the disulfide by very costly catalyst. We thought that can we simply use the simple reduction power of the alkali metals, because sulfur bonds very much sensitive to undergo cleavage by single electron transfer processes. So then we can make use of the disulfide, basically in situ generated of the phthalate anion, and then the entire chemistry can be repeated. So we can make use of the disulfide. Whenever the disulfides are there, we use those things, use this chemistry and make our compound. But one prominent example I'll give you in the context of the manipulation of the functional group. Another way to protect the phenolic functional group is the benzyl ether, because very easily it can be cleanly deprotected and by hydrogenalysis, catalytic hydrogenalysis, right? But there, what you do, you are losing that pH-2 moiety as a toluene. So we devised a counter-attacking catalyst or reagent system in this way. Like if we take a lithium bromide catalytic quantities in the presence of acetyl bromide, then we can adapt a acetylative debenzylation reaction. The acetate can be very easily hydrolyzed to get the phenolic compound, or it might itself might be a starting material. But now we are going to regenerate the benzyl bromide. So now the benzyl bromide can be used again and again. And we found out a thorough analysis. There are two things very important. Number one, that it depends upon the relative leaving group availability of the phenol, and also it will depend upon the ability of this oxygen to become a very strong chelator of the lithium. So these two factors is very important. So here in a competitive exam, environment, we find out the phenol having a very strong electron withdrawing group is selectively being deprotected. On the other hand, if we take a different phenol in which the electron density of the ethereal oxygen is going to be relatively different than the particular one, like the second one, electron rich, so it is getting selectively deprotected. We realize the chemistry can be used inside. This is an example where we have a benzyl ether, we have a benzyl ester also. This is not deprotected because in the carbonyl group, it makes this oxygen is a very less donor, so selectively it takes place. Same thing over here also. But we can make a reduced selectivity also by tagging the corresponding reagent system directly to a particular phenolic residue. Like you have a chelating group which is adjacent to the corresponding moiety, then you can deliver selectively the corresponding acetyl bromide and make a deacetylative acetylative benzylation reaction. So we found out that if we take this one where R equals the electron donative group, the selective deprotection takes place over here. And the second one, that the one which is adjacent to the acetyl group is going to be selectively deprotected. So practically no deprotection takes place. So total actually is 50 plus 40 means 90. But here what happens due to the presence of the acetyl group, it undergoes during the aqueous work of some deacetylation also. Then we found out that a solid phase alkylation reaction can be used for making a very, by this time, solid phase chemistry is very much popular in medicinal chemistry, and meriphyl resin can be used as a benzyl group for that. So we found out that this can be done. So ultimately, when the reaction is done, we generate a modified meriphyl resin, which is a bromide form, which is much more reactive and active also. So we will regenerate the meriphyl resin bromide form, and this is a more active. And this chemistry can be, it works with the various kind of substrate. It can be adapted for making a, I think 6 or 10 component library we have done, and the reaction works well. So this is the way the reaction works, acetylative deprotection reaction. Like in this case, normally, very rarely we recycle, but depending upon if the reaction is a large scale reaction, then you need not to throw out the benzyl bromide, which is going to be regenerated and can use it. This becomes a true sense application because you are getting not only the corresponding meriphyl resin, you are getting a more active meriphyl resin. Let me give you during my remaining period application in the preparation of the drugs and pharmaceuticals. I talked about this dealkylation, this dimethyl sulfate, but if we take the today's context, the green and cheap methylating agent, so most popular is dimethyl carbonate because it is going to attack with toxicity. But dimethyl carbonate is a ambient electrophile. It also can undergo a acylation reaction also. So it becomes a little bit tricky to, although we have some methodology, I will not discuss it today now. So if you compare, then methyl alcohol is going to be the next best reagent. Dimethyl sulfate popularly used in the industry, but dimethyl sulfate is a major problem is that it undergoes hydrolytic cleavage to sulfuric acid, and if it is too old, you have to make it a purified, and that become a difficulty. So we thought that can we make a methyl alcohol, but problem is that methyl alcohol is a very poor electrophile. You have to take a catalyst for that purpose. So by this time, we have very efficient solid acid catalyst. We thought that can we put into use. In fact, this catalyst can be used for a direct esterification of any kind of alcohol by carboxylic acids, and only you need a molar equivalent. You need not to heat the reaction Beanstalk water separator. If the reaction under neat condition don't need any solvent, and it was found to be useful for the making of a ibuprofen prodrug also, because these are done in a very messy way, so it can be done product synthesis also, and various kinds of fatty acid esters which are very difficult to synthesize in the classical esterification protocol, and the corresponding various kinds of flavoring agent. During the time we were delving into this green chemistry early stage, we found out this amino alcohol moiety is a ubiquitous structural feature present in a very important class of the drug called cardiovascular agents, popularly known beta blockers. And the one easy way to make will be a epoxide ring opening reaction by the amine. So we found out the various catalytic methods. I'll take you through catalysts. Zinc perchlorate happens to be a very effective catalyst, and with the help of this catalyst, we demonstrated that we can use the naftalpidol and the propanol, those are cardiovascular agents in therapy, both in a racemic form, and if we convert into the corresponding chiral substrate, which can be obtained by taking a chiral epichlorohydrin, then we can get an R propanol and naftalpidol. Similarly, we can make the S2 also and get the corresponding S. So both RS as well as RS works, and there is no change in the optical purity. Metoprolol is another class of reagent, but there this amine moiety is an aliphatic. So the moment we take an aliphatic amine and try to do the epoxide opening reaction, if it becomes normally zinc perchlorate is such an active catalyst, it becomes more than one reaction, like one amine can react with two epoxide. So for that, we need a milder catalyst, and we found out zinc tetrafluoroborate is a milder because the corresponding conjugate acid is going to be less acidic, like perchloric acid is the best, more acidic than tetrafluoroborate, and the reaction works very well. And both RS as well as RNS metoprolol can be synthesized adapting this group. Another both the optically active compounds. Diltiazem synthesis, which was at the time, maybe till today also, one of the 10 top-selling chiral drug, and it is for another type of cardiovascular agent called calcium channel antagonist. And the critical step of the reaction is the epoxide ring opening of the corresponding glycidic ester by 2-aminothiophenol, and we found out zinc perchlorate can be a very efficient catalyst, 2.5 mole%, and the evening can be done for this purpose. I talked about the catalyst, and solvent happens to be the one major criteria in providing a greenness-based system. And this slide tells you that the use of solvent, non-organic solvents, is the major mass utilization, more than 85% of the mass utilization in any typical chemical manufacturing processes. Although little bit old statistic, but I didn't get the updated statistics. These are normally low molecular weight organic compounds supposed to be recovered, but the recovery efficiency generally varies from 50 to 80%, average is 60%. So close to 40% of this chemical waste goes to the environment, mostly to the air and to the water. That is the reason managing solvent system becomes one of the key green chemistry research area in the pharma industries, and they try to find out what could be the most environmentally benign solvent, and these are called Pfizer solvent selection guide. And you'll see that these are the three different classes. Undesirable, middle one is tolerable, means usable, and the first one is the most preferred one. And most of the common organic solvent which we organic chemists normally are very fond of are not going to be the recommended one. So, but the top of the list is the water, which probably reaches that water might be the ultimate green solvent. So, and we realized that incidentally that the first organic reactions was reported by Dielsal order in 1930. As a matter of first organic synthesis, polar synthesis was done in water. Aqueous reaction happens to be the atom efficient also because it's a rearrangement reaction, but probably most documented organic synthesis was done by the Dielsal reaction 1931. It was not done in organic reaction. It was done in aqueous media first. And then people tried to find out that in fact there is a selectivity gain like endo-exo ratio. Most beneficial effect was done by these people. They found out that there is a beneficial effect in terms of rate acceleration, and it became a common knowledge to the synthetic organic chemists across the globe due to press law. So we thought about that what are the contribution of the water in this reaction. Water does accelerate the reaction, it does modulate the selectivity, and people have used water assisted synthesis of the intermediate for the synthesis, but all those things are in a particular type of reaction. And the reason they have contributed is due to the hydrophobic effect and the hydrogen bonding effect. But all these things refers to a particular reaction called Diels-Alder reaction. We try to have a global answer to that. What could be the molecular level interaction with the substrate in general when you move out from the domain of the Diels-Alder reaction to any in general organic reaction? And again, the N-Bock formation put our attention, and this was the catalyst, 4-dimethylaminopyridine. So we need an alternate catalyst. So in the meantime, I have told you there may be half a dozen of catalytic method for the acylation reaction of the phenol and alcohol or amine. Some of these things can be extended to the N-Bock protection also, but there is a danger over there in many of the cases. Some of the cases which we could not publish right now, we have data, enough data evidence. You may not end up with the right compound. We are getting a completely wrong compound. It's a different context and talk about. So what we need here is a case we need a completely non-electrophilic activation, but non-metallic procedure. So for that, can we put into use the hydrogen bond ability of the water molecules so that it will activate through this transition state electrophilic activation, and in turn, the oxygen atom of the water molecule will undergo hydrogen bond with the amine, so the dual activation through transition state 2 and the reaction should proceed. It's a very clean reaction. The self-monitoring reaction, as long as the reaction goes, the carbon dioxide gas effervescence can be seen. So you need not to monitor the reaction by TLC or any other techniques. It's a very clean reaction. And another reaction we have to think about is that to get these products to further extension of the compound for biological activities. And in this context, we have found out a few thiamethyl addition reactions, but we found out that the target product we are going to subject to enzymatic analysis, enzymatic testing, and they are very much sensitive to trace amount of the metallic impurities. And sulfur is a notorious element. It can trap a very trace amount of the transition metal. So here is a case we need a completely metal-free conjugate addition reaction, and we thought that can you put into use that same dual activation role of the water. This is the electrophilic activation, this is the dual activation, and the reaction works very well. So we are very happy. Then we found out that, and we have proposed the reason this amphiphilic means electrophile dual activation by cooperative hydrogen bond formation reaction. After publication over after next year, we found out a paper come in Science where they are doing a nucleophilic addition of a hydroxyl radical to an acetaldehyde molecule, and they claim that this reaction is promoted by single water molecule, and the reason the single water molecule catalyzes is because it undergoes a dual activation through the hydrogen bond formation reaction. The same principle which have adapted, almost the same language has been adapted to explain the reason, and they have demonstrated by a critical analysis of the energy of this transition state that yeah, this is the reason why the reaction is going. There had been a major issue in the marine chemistry that this kind of polycyclic ethers, they are called toxins, very toxins, sexy toxins, those are the very target molecule at the time. And they have a peculiar structure that they are all 6-member cyclic system. So since it is not possible to meet the need having a natural sources, so people are looking for a synthetic way to make those toxin derivatives. Maybe you can reduce the number of ring system. But any efforts which are done in the laboratories, either using a classical organic chemistry synthesis, using a non-acid method, they end up with either getting a 5-member ring cyclization or a mixture of THC and DHF ring cyclization. So then they came across and tried to analyze is the intramolecular epoxide opening ring reaction, and the 2 water molecules undergoes hydrogen bonding over here, and that is the reason it works only in the aqueous condition. So then they repeated that if you replace the solvent by water, the reaction works very efficiently. Herein also the same principle, exactly dual activation role, line by line has been adapted to explain that one. So we're very much happy that actually this is being utilized the principle to extend to various kinds of other reactions. That our contribution has a far-reaching consequences in the organic chemistry was found out later on. In 2018, Organic Letters has published a virtual issue called a Platinum Anniversary Collector's Edition. So what they have done, they have picked up one paper article published in each year of the organic chemistry from 1998 to 2018, and they compiled the issue. And in the 2006 year, they have picked up this particular work, which is a catalytic chemoselective N-T-Bock formation amines in the water. And this was sent to me by one of my students. He was my student from Burdwan University, where I taught him chemistry. Now he is a faculty in ISM IIT. He sent me WhatsApp message. There are only only papers are. Then what do you mean by only papers? Then when we went to the this virtual issue found out this is the only article representing contribution from India in this collection volume in the first 20 years of publication of organic letters, which tells you that one, the far-reaching consequences of the chemistry which is behind this publication. It is not merely a simply another way to make the en-banc formation. So by this time we are convinced, and wherever the possible, we try to take the advantage of aqueous reactions. I'll take very briefly three such applications: novel all-water chemistries. So this came into our knowledge because this is the new way to treat cardiovascular diseases. It was approved by US FDA, relatively newly approved molecule. So we realized that there are a lot of patents literatures are appearing, but when we went to the patent literature, we were really surprised that none of the patents are any new processes. These are all basically concerned with a different ways of crystallization procedure so that you can minimize the impurities. Impurity was the major problem over here. So then we realized that if by developing a crystallization procedure or maybe using a different solvent system, you are minimizing the impurity. So why not to attack the root cause of the problem? Can we minimize the impurity the way they are being generated? So we found out these are the various components which are installed in the final structure of the molecule, and the way the components are introduced sequentially. So that is the root cause. We found out that this has to be attached as late possible because that is a major way to make the impurity. Other also does that one. So in this we have redesigned a completely different route. And in each and every cases, the reaction is going to be promoted by water. When we use the water, if the reaction is promoted by any other solvent, we do not pledge the promoted by the water. And as expected, we have patented also, patent has been granted. So we have a very two-step synthesis, and the reaction works with RS. And we can have a protecting group free synthesis also. So as I told you, I'll give you only a limited example that in the first phase, that the acylation reaction with the chloroacetic anhydride, it works only in water. When you take in water, people have a apprehension that probably a trace amount of metallic impurity is going to catalyze the reaction. To prove that, we have taken tap water, pure water, and pure water means this is double distilled water, glass distilled water, and last one is a ELGA purified water. So all the cases reaction works very well. So it is not due to any country. So the reaction works in tap water, and it doesn't work with any other solvent. Right, let me skip this one also here. So the other molecule is lubilazole. Lubilazole has been approved for different reasons for nervous system. But later on, it was found out it might be a new way to treat the various kind of cardiovascular agents also, although those are yet to be approved by the US FDA. But that is the kind of molecule one should attack so that by this time they are approved. Like these are the various disease indication one can find a repurposing of the same molecule. So this is the right kind of molecules where there is not much patent from India. Our is the first patent. So this is less crowded area for the process chemistry. So we adapted this one. And herein also, we have re-engineered a completely different way to make the each and every case the reaction will be promoted by the water molecule, except the last one where we have to take ethyl alcohol and it is the next base to the water. So it is a more concise route has been decided over here. So this is the case for the reductive amination reaction, we have to take ethyl alcohol, but ethyl alcohol is the next best organic solvent. And here also that reaction works only in water, it doesn't work any other organic solvent. And the reason might be this kind of hydrogen bonding, chain hydrogen bonding takes place. Taking some example from the literature that this is how in the water surface, the 3 or 4 water molecule, the hydrogen bond is projected out of the surface, and there is the cases where it can undergo hydrogen bonding with the reactant. And this is how exactly it happens for the nucleophilic substitution reaction also. Selectively, nucleophilic substitution reaction takes place over here. Last example is a nanocatalyst and aqueous condition double advantage. So we are attracted by this scaffold. This is also the equivalent to the beta blockers, but beta blocker you have a amine over here. But here is an alcohol oxygen over here, and that is the reason that this scaffold A can be obtained by a nucleophilic opening of a epoxide by a phenol, but not by an amine. Now, since phenols are very weak nucleophile, we found out there is a very less number, and this is the various kind of diverse kind of molecules. These are again the beta cardiovascular drugs, and these are the CARB expectorant. So diverse kind of therapeutic agent contains this molecule. These are called a platform pharmacophore. So these are the few representative examples. Best reaction works with the gallium-based bimetallic complexes, and it's a very costly catalyst. It is from binaphthol has been used as a ligand also for that. we found out that can we activate the epoxide simultaneously. So in this regard, we came into across some literature where the thiol epithyl and episulfides lone pair of electrons are being polarized by the silver nanoparticle. Silver nanoparticle is a softer nanoparticle, and oxygen is a harder than the sulfur. So we thought that can you use a palladium, being a harder metal, can be able to polarize the epoxide lone pair of electron, and in fact we found out the entry number 11 provides a recipe in which actually we are generating a palladium nanoparticles under the reaction condition, and you have to use tetrabutyl ammonium bromide to make it that it does not undergo agglomeration. So reaction works very well. But we found out the reaction works only in aqueous media. The contribution of water is a twofold. Number one, in aqueous media we can have a nanoparticle formation also, and at the same time water is needed so that water undergoes hydrogen bond formation over here, right? So, but this interaction is very much crucial. What we found out that although it might be treated as a nucleophilic ring opening reaction, but it works much efficiently with a phenol which is a less nucleophilic, like paranitrophenol and 4-methoxyphenol. The reaction is faster with paranitrophenol. The reason behind that there has to be this back donation from the palladium nanoparticle to the aromatic ring. This can be called a anion pi interaction, which is a very rare in the literature, but we didn't have a scope to claim this thing as a big claim. Certainly one day it will become a descriptor in the drug discovery at least. So, and here also, if the phenolic moiety is having a electron withdrawing group, the reaction, this will make a very good charge transfer possibilities. That is the reason, and here is the role of the water molecule. So you need a palladium nanoparticle and water molecules, and the reaction works very well. And we have extended the chemistry to make all those drug molecules. So what I try to put before our younger colleagues and the students of the Akal University, that yes, you have enough scope to contribute a green chemistry or a sustainable chemistry while you are doing the chemistry. So look for an opportunity, but what is important, you must be strong in your chemistry. And even if you are not much equipped with your infrastructure, but if you are equipped with the chemistry knowledge and you know the problem, analyze the problem, only objective should be, it should not be treated as, no, I have also joined the procession, right? You join the procession of green chemistry and sustainable chemistry, but you must find out that I must be the flag bearer, right? So that approach will depend upon how you are handling the problem. It is my suggestion to all the young researchers here or whoever is listening to my talk. So in this context of the conservation of atomic economy, we found out a very age-old reaction like dialkyl sulfate reaction, how we can make an atomic economical transfer of the both dialkyl group. Then we can use a classical chemistry called Claisen-Smith reaction, and how it can be replaced by lithium hydroxide. Most importantly, that demethylation reaction that popularly used a stoichiometric phthalate can be converted into a catalytic compound by a demand-based phthalate and generation. And recycling waste, particularly in terms of the acetylative demerger reaction of aryl benzyl ether, and which can be integrated to the very nice way to do the solid phase synthesis using the methyl resin, a better way to use the methyl resin. And the solid supported protic acids and transition metal based catalysts, particularly phosphoric acid and fluorosilicate gels. So as I told you that one, that rarely you'll find out any Indian university institution, call it a CSL laboratory or IITs or Central University, State University. At one point of time, their chemist has not used my catalyst. Transition metal based catalyst, particularly the beta blocker synthesis at the time, because the hot topics, and we have contributed a very important catalyst for this purpose, and application for the products and the drug intermediates. In the context of employing water as a reaction medium, our query was that one, how do we understand the molecular level mechanism of catalysis of organic reaction by water, particularly away from the Diels-Alder reaction? And towards this efforts, we have proposed a amphiphilic, means electrophile declophile dual activation through cooperative hydrogen bond formation reaction. And it is a conceptual advancement in understanding aqua chemistry and its rational use. And we have extended this one for this cooperative hydrogen bond formation for a all water chemistry, for making a greener synthesis of ranolazine and rubelazole. All the reactions are, all the steps are promoted by water, and extended the double benefit of nanocatalysis and aqueous media for making a epoxide technology, which is otherwise very difficult to do, and applying it for a platform technology for the synthesis of various drugs. So chemistry underpins everything we want to do in the modern society, but looks like that the current processes for making the chemicals are not sustainable in terms of the resource and the environmental impact. And green chemistry aims to tackle all this problem, and there has been a real progress. When you talk about the green chemistry, means we are changing the solvent or we are making another catalyst. So people try to find out. So it is a incremental development. But at the heart of green chemistry is innovation and the discovery of new chemistries, and not merely the incremental improvement of the traditional synthetic methodologies. The word green in green chemistry refers to fresh, young, and new, has been told by Paul Anastas, which is considered father of the green chemistry. And I think I try to convince you that we have not simply taken water as a simply water medium. Why water is going to be used for catalyze the reaction? And in this regard, we have first proposed a dual activation role, and this is not only help us to make our own chemistry. Many people have used the same principle and solve various kinds of problems. Naisergi has done the reaction series in United States of America, and remaining that ranolazine synthesis and lubulazole synthesis in aqueous chemistry, apart from other things, has been done by Dr. Dinesh Kumar. He is an assistant professor, Department of Medical Chemistry in IIFR Ahmedabad. And other person who was senior to him was Damodar. He is entrepreneur itself now. I think at Hyderabad, he has established his own concern. Brahma has done all this. He is now in Jubilant Infosys. He is a senior person over there in the industry. He has developed all the zinc tetrafluoride catalyst for the beta blocker. Sudipto has introduced a different way to do the ionic research in my laboratory. I could not get time to talk about his chemistry. He is a assistant professor, Department of Chemistry, IIT Delhi. Kopil has initiated a nanocatalysis research over here. I could not put their figure like Dr. Rajkumar, who has done that thermoglycan reaction aqueous media. He is the dean and head of the department of the Pharmaceutical Sciences, Central University of Punjab, Batinda. Along with Santosh, there is another person, Santosh. He was my first batch PhD student. He is a faculty in University of in Australia. And Sune, who did the N-block formation reaction, he is a senior level research director in AstraZeneca, and probably in their Switzerland center. And many other students has contributed. And all these works were done in this institute, NIPER, from 1994 to 2019 September. I was there. I have superannuated in 2019 September, and then I have moved to a neighboring institute, IIT, new IIT, in the Department of Chemistry as a visiting professor, IIT Roper. And most importantly, thank you very much to inviting me and listening to my lecture.
Thank you so much, sir, for your such a valuable lecture. From your lecture, I think all the participants learned many things, like you have discussed scope and need of green chemistry, importance of green chemistry, various reaction categories, and then importance of medicinal chemistry, implementation of green chemistry principles in academic research, and then you have discussed the chemoselective O alkylation, chemoselective O methylation reaction, and then synthesis of chalcones, lithium hydroxide catalyzed Claisen-Smith reaction, cross aldol condensation, deep protection of aryl methyl ethers, properties of various solvents, and then selective cleavage of aryl ether, heterogeneous catalyst. In your lab you have synthesized this, and then utilization of waste materials, then synthesis of beta blockers, implementation of solvent on environment, aqueous mediated reactions, which are very important now as far green chemistry is concerned, and then Bock protection and dual activation by water. Thank you so much, sir, for your valuable presentation and talk. Now I am requesting at least one or two participants, please unmute yourself and share your views, because our next speaker, Professor Ranu, is also with us. He is waiting for his talk. So only one or two participants, please unmute yourself and share your views.
Good morning, sir.
Yeah.
Thank you, sir. It was a great privilege that we are hearing from you. Mini lecture on green chemistry. Most attractive part of the lecture was the use of green chemistry, or most emphasis on medicinal chemistry, which is the latest progress in the medicinal. Therefore, thank you, sir.
Thank you, Manmeet.
Thank you.
Now I'm requesting Musarat Samim. He is from Jammu University. Please unmute and share your views.
Yeah, very good morning, sir.
Good morning.
So it was a pleasure to hear you again after the value-added course on green chemistry, which was organized by Indus International University when Bhuvan sir was there. So it was a pleasure, and I am really much overwhelmed to share this that you are a part of my life, and inshallah, I will definitely overcome from this situation and will meet you once in life. So it was a
All the
pleasure
way.
to hear. It was a pleasure to hear you. Thank you so
All the way.
much, sir. And overall session was very interesting and wonderful. We are not here to ask anything. I'm quite nervous in front of you, but it was overall so wonderful, sir. Thank you so much, sir.
All the best.
Thank you, Musarat. So thank you so much, sir, for your valuable time. Thanks a lot for giving us this opportunity, sir. Now, our next speaker means Professor Bishi Ranu, sir, also with us now. He is available. Ranu, sir, can you hear me?
Yes, I can hear you.
Okay, thank you, sir. So let me introduce sir. Means for that, I want to share is just a minute. Means a little, just a minute, dear participants. Yeah, is it visible?
Yes.
Okay. So, thank you so much, sir, Professor Brindaban Chandra Ranu, sir, for giving us your valuable time, and you have agreed to deliver your valuable talk for us, for our participants. And let me introduce Professor Ranu. Professor Ranu presently in the position of INSA honorary scientist at Cultivation of Science. He did his PhD in 1982 under the supervision of Professor Usaranjan Ghatak sir from Cultivation of Science, and after that he did postdoc during from USA in 1985 to 82 to 85. Then he joined uh, Cultivation of Science from 1985, and then he this he was the head of the Department of Organic Chemistry from 2003 to 2008, and then he served the same institute as a senior professor from 2006 to 2013, and then he retired from 2013, but he again joined as a JC Bose fellow and now present INSA senior scientist in the same department. He received so many awards, it is difficult to mention all those awards because it is a short time. Uh, I don't want to discuss that and waste time of valuable time. Just mentioning few because sir is the fellow of Indian National Science Academy, fellow of this JC Bose National Fellow, and then he received JC Bose Medal of Indian Chemical Society. He supervised more than 35 PhD scholars, published more than almost 300 research articles, and all are in internationally reputed journals having high impact factor. And his research interest is on based on green synthesis, green catalysis using supported materials, benign and less expensive transition metals, and ball milling mediated synthesis. And let me share this. This is the and thank you so much, sir, for giving me this opportunity to co-edit a book which was published last year with you. Thank you so much. With this short introduction, I am welcoming you once again, sir. Now I am stop presenting this, and now you can share your slide. Thank you, sir.
Please.
Over to you, sir. Ranu, sir. Can you hear?
I have to share the screen. Where is
Yes,
it?
yes, sir. Yes.
Right, I got it. Can you see the screen?
Sir, not now.
Not now. Okay. Just a minute. I mean, other people are not sharing the screen. Say that one participant can share a screen. So, can you turn off this? I mean, sharing screen from other participants.
Sir, please, okay, we are checking, sir. Please. कौन share कर?
Dear sir, actually in this case, the multiple person can share their screen. If you are getting this message on your screen,
Yes,
it's
sir, yes,
visible
sir.
now.
You can see it now.
Sir, first open your presentation in the background and then try to share.
Yes. Can you see the screen now?
Yes, sir, but it is a different slide, I think. KPI data from first.
No. That's a different thing. Yeah. No.
Yeah. You need to do the same procedure, means follow the same procedure. Yes, now it is visible, sir. Okay.
Now it's all right? Okay.
Yes, sir.
I'm going to, yeah.
Yeah, you please make it in full screen.
Slides, I'm getting it. Slides. Okay, it's all right?
Yes, sir.
Okay.
Thank you.
Okay, then very good morning, everybody. And thank you, Bubun, for inviting me and allowing me to share our works with your students and all the audiences present there. Yeah, as it is online. So, yeah, maybe we are losing that pleasure of meeting the people in person and also having that impulse from the audiences. Yeah, but that's we have to accept the new normal and we have to go with that. Okay, and thank you for the introduction also with so many good words. Yes. Okay, what I'm going to talk today is mainly on green chemistry. Which, I think. Okay, just a minute. You can hear. Where is height? The top was not being seen, I think, right?
Yes, sir, it is visible.
It's visible.
Yes,
I know,
it is visible. It's changing also.
Okay. Okay. I think top part looked like that. The top part is not hiding or something. Yeah. Anyway, I cannot get the things. Okay. Fine. So as you get my title is mechanochemistry and visible light photochemistry, two powerful tools for green synthesis. Both are very emerging concepts and both are in the still you can say that growing stage. Okay. So before that, I will explain all the terms. That's what is mechanochemistry, what is visible light photochemistry, and also the green synthesis in a new way. I mean, we have already heard an excellent lecture from Professor Chakraborty about the green synthesis, but let me refresh some of the words. What is green synthesis? Okay, or green chemistry. As you know, that's in a book. The green chemistry is called sustainable chemistry, an area of chemistry and chemical engineering focused on the design of products and processes that minimize or eliminate the use and generation of hazardous substances. Perfectly all right. Okay. If someone is asked what is green chemistry, 90% of the people will tell that. But it's not could be not easy to memorize all the things and to tell exactly the same way as it is written here for the students. So what my perception is that, okay, look at green chemistry from some natural processes so that we don't memorize it. So what I think, if you look at this way, then what is green chemistry? Basically, it's a clean chemistry. Why? How? The doing chemistry the way nature does chemistry. I think everyone can now understand, everyone can memorize, and I mean nothing. That what is green chemistry? Now everybody can tell that doing the chemistry, the nature does chemistry. It's so simple. You need not memorize the big definition and the coin all the words. Doing chemistry the way nature does chemistry. Now, how nature does chemistry? Again, I'm giving a very simple example. I mean, all of you have learned it in your school days. That is photosynthesis. Whether in a biological class or in a chemistry class, maybe in a biological class, the photosynthesis. But what I'm telling here, that the implication of this reaction, and I think that is the greenest reaction of the whole world or the scenario. What is photosynthesis? As you know, it's the reaction of carbon dioxide and water in presence of chlorophyll and sunlight to give glucose and oxygen. That's fine. But now we could try to analyze the reaction, try to understand the reaction. It's the reaction of two elements, carbon dioxide and water, which are abundant, non-toxic, and easily available, right? Okay, keep that in mind. I will come to green chemistry later. And what it is making? See, glucose is a very, very important material used in drugs, used in food supplement, and very important material. And what? Oxygen. What is our life? So practically all two useful products without any waste, without any things which affects the health. Okay. So first thing, what is green chemistry? Green chemistry is a reaction of two materials which are non-toxic, abundant, simple, inexpensive, producing products of high use, non-toxic, environment friendly, and no waste. Okay, that's half of the green chemistry is this. Okay, next half. How the reaction is being done? If you look at this, catalyst is chlorophyll and sunlight. No organic solvent, no other solvent. Okay, so chlorophyll is inherent in plants, green plants, and sunlight, that abundant nature's thing. So here, now come to this, that use of catalyst, which is again non-toxic, environment friendly, and inexpensive. And use of energy, what is called energy. As you know, if you do any reaction, if you look at any reaction textbook, you will find that the two things are being mixed or heated with getting something. That is heated. 90% of the reactions, when you look at the textbook, it needs heating or something. Okay. So, but heating means what? Heating means you are using or expending electricity. And electricity means what? Then you are consuming fossil fuel. So that against the green chemistry, against the nature things and all the things. Okay. So if you can use sunlight or at room temperature and sunlight, that is excellent. So you are not using any extra energy. You are using the energy, or the God's energy, the sunlight. Okay. So that's another thing. So for the green synthesis now, use of some catalyst which is environment friendly. Is it possible to use no solvent or environmental solvent? Okay, and use of energy which is abundant and which is nature's energy, the sunlight. So these things. Okay. Now, again, I'm summarizing things. The green chemistry, from this thing, nothing, you've not memorized or anything. From green chemistry point of view, from this, looking at this thing, it is simple. It is inexpensive. It is renewable. It is toxic free. It is waste free. It is you can say that it is secured. I mean, no chance of explosion or anything. And use of chemicals which are non-toxic and production of chemicals which are non-toxic. Okay. Now let us look at the official definition of green chemistry. If you look at it, just from the analysis of that, green chemistry is environment friendly. I showed that in the photosynthesis, environment friendly. Simple, I already told you, simple. It is renewable, sustainable, atom efficient. All the atoms are used up to make glucose and oxygen. Economical, no doubt about it. It is safe, no question about that. No non-toxic and no waste. So what is designed here in the official way of green chemistry, you can have the essence of all these parameters from a simple reaction of photosynthesis. And no one can forget photosynthesis. Photosynthesis in your blood, you can say. those who are having the lessons in science, there's photochemistry in your blood. You know, no one can, a whole life, you cannot forget photosynthesis. So if you remember photosynthesis, all you know about green chemistry. Okay, so it's so simple. It's not like that you have to memorize the definition of green chemistry as in book. Okay, so here also the book thing, green chemistry is considered an essential piece of a comprehensive program to protect human health and the environment. Now, so here I'm summarizing this. So two main objectives of green chemistry are use of chemicals which are safe to human health and environment in a chemical reaction, and production of no chemicals which affect human health and environment by chemical process. All I have been seen, just I'm summarizing this. Now come to general representation, now come to real chemistry. So as you look at the chemistry in book, or you are doing in the chemistry in the practical class, or in the research lab, what you are doing? You are simply mixing 2 or 3 things, like here I'm taking, to make it simple, 2 things, A and B, in presence of some catalyst, solvent, and energy, and getting C plus D. This is the usual general representation of a chemical reaction. Now, come to that. Here I'm getting C plus D. If C and D are all very good, like glucose and oxygen, no question. But what happened in the practical life is that maybe one of the materials, C is important or C is useful, but D is toxic, or D is not wasteful. So in that case, D is a waste. And how it is handled, in most of the time, the waste, industry people do not care about it. They dump it anywhere or something. At least, earlier days it is done. Now, because of the environment, some industries are taking some precautions, but it's not the time that all industries are taking all the green chemistry or the environment protection in that way. So that means one of the product is useful, if other product is a waste, that this is not treated properly. So from the chemist side of view, if you can design a reaction that A plus B to only C or only D, then that problem is solved, whether industry cares or not. Your design of reaction, design of strategy shows you that only C or D. Fine? Okay. Now the catalyst. The catalyst of keeping all this red because not all the catalysts are environment friendly. Like say aluminum chloride. It's a good catalyst for field gas reaction, but it's not environment friendly. Like strontium chloride, even indium chloride. There are many halides or other catalysts which are not environment friendly, but we have to use it. People are using in the lab. So with that, we can avoid this type of catalyst. Next, solvent. If you know, organic solvents are very bad. I will show one slide only. Professor Chakraborty has showed so many, but I'm taking one slide only to see the hazardous and danger of the organic solvent, but still it is practiced. And the energy, as I told you, the thermal energy is the most common energy for a chemical reaction, the heating and all the things. That thing already I talked that if you look at the photosynthesis, the ideal thing will be if you can use energy from sunlight. That is the ideal thing, right? But let us look at the ideal and practical thing. So, what green chemistry says is that from A plus B, you have to make C and D. And you have to use green catalyst. You have to use green solvent or no solvent. And green energy like sunlight. If you can do all these things, that is ideal. But always the ideal things are not happening. So you have to make a compromise. But the question is that how far you can go up to the ideal. Sometimes I'm asked that whether it's green or whether it's not green. So the question is, green means what is existing. If we can go a step forward, step further from the existing process, making at least one parameter green, that is also green. In the next step, improve it, make it to say 80% green, make it to 90% green, make it to 100% green. So 100% green is ideal, but if you can make some improvement, if you can make some innovation so that you can reach up to the goal or reach some way up to the goal, that is also considered green. So this is the goal, or this is the ideal thing, but how far is possible, I will then discuss on that. So keep that in mind, that use of chemicals which are non-toxic, making up chemicals are non-toxic, and use of the conditions which are also non-toxic and non-friendly. So that is the things which you can always remember. If you forget it, Just listen, I mean, just keep your photosynthesis in your mind and you will get answer to all these things. Okay. Now, this is one slide you can say that how toxicity of few common organic solvents. The benzene, the number one, highly carcinogenic, or I don't know whether who is number one, benzene or carbon tetrahydride, both are bad. This is highly carcinogenic, chloroform, all chlorinated solvents, acetonitrile, dioxin, DMF, THF. Ethyl acetate is the less because that is the, I mean, it was in the bottom of the list. So more or less what I'm going to tell that most of the organic solvents are carcinogenic. But some are less, some are this, and that's already shown in Professor Chakraborty's slide, that which is desired, which is not desired. I'm not going to that, but I'm not going to discuss also water reaction, but maybe one or two examples. Yeah. So this is the thing that I want to show it in a way that how dangerous, how harmful, how toxic the organic solvents. So if possible, I'm talking about the young chemist, that wherever possible, avoid organic solvents or use the organic solvents which are less toxic. Never go for benzene or carbon tetrachloride or chloroform if there is no way, or acetonitrile. They are all very bad. But if there is a way, then go for some other things. Okay. So this is the disadvantage solvent, there's toxicity, high volatility, yeah, and cost. If you look at the thing, cost of the all coming from petroleum chemicals. So if the petroleum oil, petrol, I mean, it is sold now in almost 100 rupees. So how can be the cost of the organic solvents? So, and also fire hazard. And I will not find any lab in the whole world where there is no fire at some other time. So all the disadvantages. So what is the way out? Okay. This can be a way out, one way. So water is a very good solvent, natural solvent. If you can water, nothing better than that. Then the supercritical fluids, and liquid is questionable, but anyway, at one time people thought that this might be bad. Solid surface without any solvent or neat. These things can be a way out of that. Okay. But I will go to something which is different from that. Mostly no solvent. I will mainly discuss no solvent reaction and some reaction with the nature's energy or sunlight or this. Okay. Just water, I will give only 3 slides that why water is so much, life, because environmental concern, cost, safety, there is no fire hazard, and acceptability of biological system. These are the things in favor of, okay. And there are many reactions now in water. So you can say that water is a viable alternative for organic reaction. The same reaction, Bristol, what is showed that Bristol made it very popular. This Diels-Alder reaction where this is the usual thing that in organic solvents is done. There's the endo-exo 3:1. Okay, but what was found that in water, so this is one of the eye-opening reaction by Breslow, and after this reaction, the people are now aware that green chemistry really can be a viable alternative to organic solvents. Before that, although it was noticed by many other scientists, even Woodward, but the momentum of using aqueous chemistry in organic reactions did not come before 1980. So after the publication of this result, really, you can say renaissance or research of doing chemistry in water has really get a momentum. So here, if you look at this, compared to isooctane and methanol, all are organic solvents, in water, relative rate is 740 in terms of this. And endo-exo ratio now is 21.4 to 1. So that shows the high efficacy of water. And the reaction is being done in water at 25 degrees without any other catalyst. But that shows the one reaction shows how water can be a very powerful alternative to many organic solvents for organic synthesis. Also, one reaction, I like this reaction, that's from one of the Indian chemists, but I like this reaction here. If it is a 4-component reaction, it's a hydrogen and the ketoester and aldehyde and all these things. It's a 4-component reaction in water, 30 degrees, 5 to 10 minutes. You get only one product without any byproduct, and it can be crystallized from, no hazardous, nothing work up, nothing, it can be crystallized from aqueous ethanol. So that's one of the nice example of green chemistry using water at say 30 degree temperature. That means no other, just room temperature in India, and in 5 to 10 minutes time. So that's one of the ideal example of green synthesis. Okay. Okay. Oh, that's from my lab. Okay. Anyway, but okay. Yes. Okay. That's also diazolam fluoroboric carbon disulfide and amine in water. Again, room temperature, nothing else. You can get diethylcarbamate. So variety of things. That's yes. That's also gives an ideal example of green reaction in water. Okay. Now, what are principal things? What I want to tell the mechanochemistry. What is mechanochemistry? So that thing, mechanochemistry and visible light chemistry, I would say mechanochemistry mainly I will focus on that. What? Because time also, I don't know how much, 1 hour, maybe, okay. I will stop whenever I cross 1 hour, no problem. Okay. So mechanochemistry, what is mechanochemistry? To tell that, let me come to some history or ancient time. How chemistry was developed, long days. I mean, say in Greek period, during Aristotle time or so, that time, the chemistry really was practiced in mortar and pestle. Without knowing much about the mechanism or chemistry or anything, the two things, two chemicals or say, some extract from plants, just when it was pestled in a mortar, sometimes new compound came. Or knowing some compounds, they also do this thing. Those days, the chemistry was, developed in mortar pestle. And maybe say about 40 years back or say when we are student, particularly when we were in the US, that time in the Adlich, there the front page was a mortar pestle. That's what the chemistry. From the Adlich, not me, Adlich, the Adlich Chemic Acta. On that journal, Adlich Chemic Acta, the front page was many years was given that mortar pestle. So because mortar pestle, one of the things where chemistry was generated long time back. Okay. Now, the mortar pestle, one of the drawbacks of the mortar pestle chemistry is that, say, some strong person who pestles in a mortar, very high energy, but someone maybe weaker person, he cannot or she cannot pestle this with the same energy. So the reproducibility of the chemistry, reproducibility of the thing now comes. Okay, and so you cannot do a reproducible chemistry with mortar pestle. That's one of the things. But try to find the essence of this chemistry. What is this chemistry? When you are taking something in a mortar and pestling it, what you are supplying? You are supplying mechanical energy. So the reaction is initiated or performed by application of mechanical energy, right? Like you say light energy, like your thermal energy. When you are doing the reaction, you are heating thermal energy. When you are doing ultraviolet, you are doing light energy. Even if you are doing the ultrasound, you are doing sound energy. So why not mechanical energy? So mortar pestle chemistry is the chemistry of applying mechanical energy to the reactants. Okay, so mechanical chemistry is that. Mechanical chemistry is the chemistry generated by the application of mechanical energy. Clear enough? Now, so mortar pestle, because it was not accepted because of these things, then came the modern mortar pestle. What is this? Ball milling. It's a ball milling apparatus. What is in my lab? Ball milling is what? It's a jar here. It's a jar here. Right? It's a jar, and when and then in a jar, what happens? Let's say some peoples are metal balls. There are peoples are metal balls. It can be high quality steel or can be tungsten carbide. And then if you put your reactants, what you want to do react here in the jar, and then turn your switch on with a particular RPM, revolution per minute. And this RPM gives the energy. The more the RPM, it gives the more mechanical energy to the reactants. Okay. So what turning the switch on, what you are doing, you are subjecting the reactants to mechanical energy. The another important thing is that if you put the only say minimal scale, if you put some say 10 milligram of one reactant another reactant and one ball or 6-7 balls and then turning, then the efficient mixing or efficient absorption is not possible. So what is usually done, use some auxiliary. Some auxiliary means some absorbent, like your silica gel or alumina or something, sand, quartz sand, I think. All these things can be taken, which is neutral, which is not reacting, but which is taking the reactants on its surface. Now, when you are mixing the things in a high level RPM, then you are really supplying good energy to the reactants. So, ball milling is this a pulverizing machine consisting of a rotating drum, which contains pebbles or metal balls as the grinding implements. And you know a grinding auxiliary is needed. Grinding auxiliary needed, which can be a neutral thing like silica gel, alumina, sand, whatever, even sodium sulfate, whatever. Okay. So the mechanochemical reaction, a chemical reaction that is induced by the direct absorption of mechanical energy. That is direct absorption of mechanical energy. Both the metal mediated and metal free mechanochemical reaction can be performed. Now, I will show many examples. There is almost now all the reactions, all categories of reactions rather, can be done in mechanochemistry within ball milling. All categories of reaction, I will show it. And the efficient mixing process in ball mills is one of the solutions for enabling the solvent-free reaction. It usually is done in solvent-free. Usually, again, I'm telling. And the efficient mixing is the one parameter. Say, you put the RPM at 600. The reaction is not that efficient. Then you have to increase it to 800. Or if you have to go to 1000 or 1200. So the increase of the number of RPM means you are supplying more mechanical energy to the reactants. So this efficient mixing and the supply of energy, both are very important. And the material of milling ball, beaker, reaction time and milling frequency, the RPM, influences the chemical reaction. So whenever you are describing a mechanochemical reaction, you have to mention all the things which are important for reproducibility by some other chemist. Okay, so they are the parameters which should be taken into account for a mechanochemical reaction. I'll show a few examples. Okay, one of the things from my lab, that is transesterification. Okay, this is I don't know how that can be. You cannot see the title here because of this. What is here? In some other thing, there is the hide. I don't know. Did it come? I don't know whether it's solved. I don't know. Let us see. No, this is not solved. Okay. Anyway, that is not solved. It is
okay, sir. No problem. We can.
No problem. You can see. Can you see it?
Yes, sir. Yes, sir.
You can see. Okay, fine then. No problem.
Yes.
So that's the transesterification. Okay, for the students, what is transesterification? Transesterification, you are converting one ester to other, changing the alcohol part. Like here, I'm making it simple. RCOR2. If you look at this part OR2, this OR2 is replaced now by OR3. So that is transesterification. And why transesterification needed in synthesis or in say in industry? Because say one of the compound you are looking for is a methyl ester, but in a synthesis you make it as isopropyl ester or it is ethyl ester. Then how you can convert that to the desired ester? So that is called transesterification. And sometimes the efficiency or the activity of the compound or methyl ester or particular ester is not the same with its analogues. So methyl ester is very active. Ethyl ester may not be active. That's why you need the particular alkyl ester. And that's why the transesterification is so important. Usually it is done in acid catalyzed also. There are many methods. But what we are doing it here, the ester, alcohol, we are the only basic alumina as a grinding auxiliary. Nothing else, no solvent, nothing else, nothing. 600 RPM and 2 to 3 hours, you can get this transesterified product. So that's one of the things that don't use any solvent, don't use any other catalyst, you are eating that. Why is it advancing now? Yeah. Now, there are many examples. I'm not going to details, but I'm telling it there. That the variety of this is an allyl ester and there's a benzyl alcohol. Usually you can replace that, you can get this ester, okay, benzylic ester. So similarly, there are many examples where I'm not going. There's also all sorts of things can be done. We have another example here. If you saw the heteroarene alcohol, These two are heteroarene alcohol, but this also can be done very simply by replacing this part with this part if you look at this. So all sorts of reactions, all sorts of transestimation can be done in this method. That's a general method. Okay, what is the advantages? It's transition metal free, solvent free protocol. No additive or base used for transesterification. Basic alumina used as grinding auxiliary was recycled after successive reactions. But I'm telling from the beginning, when the basic alumina which is used after the reaction is over, you wash it with ethanol or methanol and then dry it. And dry it in the pump and then dry it in the oven. This is as good as fresh. So basic alumina is not used up. It can be recycled enormous number of times, no problem, unless it is washed by the ethanol or methanol properly. And what I'm telling that since there's a variety of carboxylic esters with a wide range of esters and alcohols, so I cannot that any carboxylic ester and that whatever I have found in our lab, everything is possible by this method. Okay. Another reaction that is from thiol to disulfide. This is a simple reaction. It can be done with metal catalyst, additive, solvent, even in water also you can do it. There are many papers on that. But what I'm going to say on the ball milling thing, that the same reaction, that thiol, oxidation of thiol to disulfide, that can done again, alumina, just grinding auxiliary, 600 RPM, 15 to 30 minutes. No solvent, nothing else. And another thing, after the reaction is over, what usually we do, or many people are doing, just take this thing in a, say, in a small column of alumina, just a small column of aluminum silica gel. You put these things, you put the whole residual mass on the thing, no solvent, nothing else, and then elute with ethanol, evaporate the ethanol. If a solid compound, you'll get solid and you can crystallize it from ethanol. If a liquid compound, in most of the cases, the compounds are very pure, 95, more than 95% pure. If necessary, you can just distill it a little bit or something like that, and or you can make it small column chromatography, whatever. But most of the cases, the pure compounds are obtained are more than 95% pure. And if it is solid, just elute with ethanol, evaporate the ethanol, you will find the fine crystals when the solvent is less, and you can keep it for some time. Okay, so that's the reactions. And why disulfides? If you look at the disulfides have very, very important characteristics. If you look at all these disulfides, these molecules act as anti-lysminal agents, and that in vitro anti-lysminal activity increases from left to right. Okay, so this is anti-lysminal activity. So this is all literature thing. I'm not thinking, I'm just quoting it from literature. And here also many things. And if you look at this molecule, the simple thing, that is dipyridinyl disulfide. This molecule, other than being an anti-lysminal agent, it is used to make therapeutic dendritic cell DC-based vaccine for HIV-1. So this is the thing, these disulfides are very, very important things. And there are many methods making it. That's one of the simplest methods of making in ball milling without going into any complexity and without using any organic solvent in the whole process. Okay. Another work, okay. This is for unsymmetrical diaryl selenide sulfide of chalcogenide. If you look at this, it's unsymmetrical because both are this. And we have worked on this for a few years, and we have many papers on this subject on selenides. One of the methods we just published in that, the diazonium fluoborate and diaryl diselenide or sulfide of telluride represents a zinc dimethyl carbonate considered to be green solvent in microwave at 80 degrees in 30 minutes. You can get this thing very high yield, no problem. It is that, and you can make it sulfide, selenide, telluride, all these things. And diazonium tetrafluoride, although diazo, so always you have to take precaution that diazo has the tendency or the prone to explode or so, but we have not encountered anything. And usually, to my experience, diazonium tetrafluoride are less explosive, less hazardous than other diazonium salt. And it was usually made from diazonium chloride, as it takes some aniline or so, and then normal way, sodium nitrate HCl, you can get the chloride, and on the spot, you can just quench with ammonium fluoborate, and you can get this diazonium fluoborate. And there's a stable, solid, you can keep it in the things, nothing happens. And but always I'm taking the diazonium compounds, you have to take cautions. It is hazardous, it is toxic, and also it is prone to explode. So whenever you are working on that, but it is less toxic, less hazardous and less than normal diazonium chloride or so other salts. Yeah, but in this way you can make this thing. But what we think that, yeah, this is the green method published in Green Chemistry, but we are not very happy of using the metal and the solvent. So how to improve that? How to get green? As I told you, that's what the definition of green. Because what is there compared to that is green. But if you can avoid zinc and DMC, it can be greener. Okay, how it can be greener? So in a ball milling, we did the same reaction in ball milling, but we use no solvent, no metal. Actually, zinc is used to cleave diazonium. Disaccharide. Okay. Zinc is used to cleave this AC-AC bond or SSS bond or TTE bond. Okay, but here we are not using in zinc, but we are using base. Base can also cleave the AC-AC bond or tellurium bond or sulfur-sulfur bond. So instead of zinc, a metal, we are using some sodium hydroxide or potassium hydroxide. Grinding auxiliary is same alumina, 600 RPM, no solvent, nothing else. You can get the same compound. So we have avoided zinc, we have avoided DMC. So that's, you can say, greener. Okay. Now, there are many examples here. That's if you do the sulfide, the same, you can do the sulfide here. If you have selenide, you can do the same reaction. Okay. Or telluride, you can do a very general reaction using KOH, neutral alumina, and 6 balls, 600 RPM, 15 to 30 minutes time, you can get this compound in all high yield. Okay. And also that's dithocarbamate, that also you can make it the same way, but it's sold in water. You can also do that ball milling. Okay. Now, what the advantage you can say, the solvent-free condition, reaction at room temperature. Okay, so it satisfies all the the photosynthesis condition or green condition. That is solvent-free reaction, reaction at room temperature, metal-free preparation of diagonal chalcogenides, synthesis of a wide variety of diagonal chalcogenides, and tolerance to various functional groups present in the substrate. Okay, that's another thing. And the nice thing about in general, about the ball milling is that because the reaction was done in ambient temperature like 40 degrees or so, coming from the friction over the temperature, and in this condition, I mean, what we have found that most of the sensible functional groups also remain unaffected. That's one of the plus point of using ball milling, or a next thing will come LED. That is one of the best things about this, because you are not using high temperature, you are not using very high basic or high acidic condition. The functional groups are more or less non-affected or unaffected. Okay, again, I'm putting another one, the 1, 2, 3 triazole. These 1, 2, 3 triazoles are also very important as agrochemicals, even in defense. There are many uses of this. Okay, there is usually called click reaction, which is that you can say some aryl azide and acetylene with copper, you can make this compound. That's the usual method in presence of solvent. Okay, but what our innovation or observation is that instead of using the aryl alkene, what you do in is one pot. There is aryl halide, sodium azide, and acetylene, one pot, so that you can avoid one step and you can avoid the handling of aryl azide, which is not also good. And copper alumina, this is the catalyst we developed a few years back. This is used in many uses. I'm not going to tell that. But here, copper alumina, 10 more %, and then these things with the same condition, you can get this thing. And this copper alumina can be reused for several times, no problem. Because after the reaction is over, just dilute that and then filter it and get the copper alumina solid thing, and then you can use this copper alumina, no problem. Okay. So they are the things that are very high yield of these compounds. We have many, but we have given some different examples where we made the 1, 2, 3 triazoles, different kinds of 1, 2 triazoles. You can get this. Okay, so what again? We are avoiding the handling of hazardous and toxic azide. It's solvent-free procedure, and use of environment-friendly ethanol for isolation of that. The same technique what I'm telling. After the reaction is over, just elute with ethanol, and then evaporate the solvent. You will get your compound very pure. And increasing the overall yield by decreasing the number of steps. That's one of the again green chemistry objective, that decrease the step or reduce the step as far as possible. And recycle the catalyst. That copper alumina can be recycled without any problem. Okay. Okay, I'll come from example literature. That is okay. Other than that, so you can get the sense of how many types of reaction can be done. Okay, one of the reaction is that Mizuki-Heck reaction. All of you know that how it is done. It is done with some aryl halide and alpha beta unsaturated ester or so in presence of palladium catalyst and some solvent. Okay, but here in ball milling, if you just ball milling without any solvent or anything at room temperature, I mean the ball milling temperature, you can get this compound. That's a very good reaction, and you are hitting a carbon-carbon bond. So what I want to tell you that all sorts of reaction you can do. This is the carbon-carbon bond formation. And what I have shown that carbon heteroatom bond formation, carbon-carbon bond formation also. Okay, here is one carbon-nitrogen bond formation. Here again, the reaction is that acetylene, is that just it's a disubstituted acetylene, and you are taking an amine. You can say disubstituted amine or imine, whatever you call. In place of silica gel, ball mill, 800 RPM in 13.3 hard blast zirconium oxide, and in 5 minutes time you can get this compound very quick. You can get this time. And what is the stereoselectivity here? When you are using the acetylene dicarboxylate like this, you can get the E isomer. That's possibly because of the steric regions. Okay, you are getting the E isomer. And when you are using the alkyl propionate, you can get the G isomer. So that can give you the selectivity. In ball milling also preserve the selectivity or can get high selectivity when there is such a condition of stereo or stereo differentiation. Get very high selectivity in case of acetylene dicarboxylate, and where is that in methyl alkyl propionates. And what is this? You are getting a carbon-nitrogen bond. You are making carbon-nitrogen bond. I shown that that is the carbon-nitrogen and carbon-carbon bond. Okay. Here, another very nice reaction, I like it. There is a Grignard reaction through ball milling. Many people, I mean, those who have practiced Grignard reaction in the lab, in terms of research or whatever practice, so that usually needs very moisture-free. That's the headache in our time when we were doing research in Calcutta. That's really is the headache that in any days or so when there is high moisture, to have a good Grignard reaction or to prepare the Grignard is a really headache. Many times, many people fail. But here, in our days, it was not this type of reaction. Otherwise, that can take up our years. And here you show, then ball milling, you don't need any solvent. Then there's no question of what is moisture or not. You don't care about any season or winter season or any season. Here, the phenyl halide, and then magnesium, and then ball milling, and then 60 seconds, yeah. And then you can get this Grignard reagent formed in 95% without using any organic or any solvent. Then to the normal reaction, if you just phenol, you can get this product. If it's your benzophenone, you can get this product, that's normal product, and very high yield. So that's one of the, one of the very nice, say, achievement for the Grignard reaction in ball milling. And another thing I'm telling you, that ball milling is not only, there's an academic thing. Now ball milling is being used regularly in industry. In kg scale, in Germany, I visited a few industries where they're using the ball milling. They use a big ball milling apparatus, and with that, they can get it in kg scale. So that's the thing, the ball milling is being regularly used in many industries because it's so profitable that most of the time you don't need any solvent, purification is easier, and chance of explosion, so not high temperature. So there are so many advantages of ball milling reaction. But I'm not telling that all reaction you can do in the ball milling, but now variety of reaction. What I'm giving a chance, you give that the variety of reaction can be done in ball milling. Alumina again in ball milling. Here you find that the potassium, the ideal best condition was found in potassium using potassium permanganate, alumina, and here you get 99% yield. If you use quartz sand, 53% yield. In iodine and alumina, 93% yield. Parabenzoquinone, 69% yield. So you can use it that they studied many oxidizing agents and found that potassium permanganate, which can give you 99% yield in this case. So there's a solvent-free oxidative dehydrogenation of gamma-terpinine to parathymine in the presence of alumina or quartz sand as milling auxiliary and different oxidation agents. So that's a nice example again. Now, CH bond activation, which is we talked about thing for many, many years now, last year. And so this CH activation also can be done in ball milling. And Kastenbaum, one of the pioneers in ball milling, this is his paper, where, if you know, this is not the class for activation, otherwise I can explain that. But anyway, in our cell, this bond is unactivated. And if you can get a reaction at this position, that is called CH activation. Through your process, you are activating this bond. That is called CH activation. Usually it's done in some catalyst, whether it's palladium or in a metal catalyst, which forms a metallocycle. And during this metallocycle, when it forms the metallocycle, this position is now activated. And then you can have the reaction at this position. That is called CH activation. And here in this case, this is the rhodium catalyst CH bond functionalization here. With this rhodium catalyst in ball milling, without any solvent or anything, you can get the successful CH activation. And I think this is the first example of CH activation by ball milling. Okay, that is again reduction, normal regular reduction. With a ketone or aldehyde or anything with sodium borohydride, lithium aluminide in a ball mill, alumina without any solvent, solid state reduction. The solid state reduction of allylic carbonic compounds to the corresponding benzyl alkyl can get this. Many examples I'm showing it here. All kinds of examples. You can the ketone, aldehyde, ester, you can reduce with sodium borohydride in ball milling. Okay. Okay, now almost at the end of ball milling, I will again visible light one or two examples. So a solvent-free mechanical organic reaction exhibits many advantages over its liquid phase counterpart in terms of high productive, better selectivity, shorter reaction time, simpler workup procedure, elimination of harmful organic solvent, etc. It is expected that continuous study of solvent-free mechanical organic synthesis will attract increasing attention. It's true. Bring about the discovery of many new organic reactions and eventually lead to practical applications in the chemical industry, pharmaceutical science, and life science. That is actually being done now. As I told you that ball milling is now being regularly used in industry. And ball milling really is a great tool. It's the one powerful tool for green synthesis. Okay, that's that is the first book on ball milling for organic synthesis that is written by me, edited by me and Akim Stulle, a very good friend of mine in Germany. And that was the first book. Now there is, several books came, but that is the first book published in 2015 January. Now visible light. And visible light, okay, first this reaction I like it most to demonstrate how sunlight can be useful for the reaction. And that can be demonstrated in any lab or anywhere. So bench pinacol, this is bench pinacol. Bench pinacol can be prepared from benzophenol in presence of sunlight using isopropanol as the reducing agent in the presence of acetic acid. And acetic acid added to prevent the cleavage of benzophenol, the retro, to benzophenol and benzohydrol by the alkali derived from the glass content for the reaction. So this reaction, what I'm telling that anyone can demonstrate in your school, that take benzophenol in a small, say, aluminum flask or conical flask in isopropanol, and then one drop of acetic acid, and just put it in sunlight, in the roof or in veranda, wherever you can get enough sunlight. Wait for 4 or 5 hours, or yeah, even from 3 hours you can get the crystal, even 4 or 5 hours. If the sunlight is strong, within 3 hours you can find a very fine crystal of benzophenol on the flask. Very nice crystal of benzophenol. So you not do any crystallization, you not do anything, no workup, nothing. Just one nice example of a reaction done by sunlight, like nature's like photosynthesis. Just benzophenol to benzophenol, you can get it by sunlight. Okay, so that's a nice thing you can demonstrate. I like this reaction. I tell the reaction. Now, the question is, this interest in the sunlight chemistry or this chemistry came long back, but it was not very successful in the way that sunlight is not the same throughout the whole world. Say, the sunlight in Spain or many countries in Europe is not the same in London, or sunlight is not the same in many parts in Kashmir or in a hill area like Darjeeling and in Calcutta or say Chandigarh. So that's the thing, that sunlight is not the same everywhere. So the question comes reproducibility. Then another technology came, that LED technology. You know, we have all the bulbs now in LED, the tube lights are LED, the TV are LED. So LED came. And what then said, organic chemists look at the idea that the wavelength of LED, it comes about 400 to 600 what's it called? Wavelength is, you can say wavelength in, what's that? Nanometers, okay. So what in that way, this wavelength from this sunlight wavelength, the sunlight wavelengths and the LED wavelengths are almost the same. It comes into 400, 600 things. And so that's why it was said that whether LED can be an equivalent to sunlight. Because LED you can produce in the lab, you can have your home, you can have, yeah. So the first thing, and the good example came from the LED chemistry, LED light, okay? So here, you can say diazonium fluoroborate. I just said same thing, I think that's a very good thing. And this, say that it can be furan or pyran or so. And here in the Eosin Y, DMSO at 20 degree, and this nanometer actually, which is a nanometer, and LED, it in this it's come out 400, 600, so you can get this nanometer. In LED, you can get this product. What actually is done is that when diazonium fluoroborate with this LED light, you have the photocatalyst Eosin. How the photochemistry goes? First, the Eosin, the photosensitizer, absorbs light from LED, okay? And then I will explain the chemistry at the end of this thing. So when photocatalyst Eosin then supplies the energy or light to this thing, and where you can get a radical here, and this radical then reacts at this position to give this very clean reaction. At 2-hour reaction, LED means room temperature. So at room temperature reaction, 2-hour reaction, although DMSO is used here, most of the reaction DMSO or some other solvents are used, that you cannot avoid, but you need a very, very small amount of solvent. So you can, but one thing I want to tell or convey here, that you can mimicking the sunlight reaction. As I told in the photosynthesis, you are mimicking the sunlight reaction. That is the thing, okay? I will show some examples. Okay, I have another 10 minutes. Or how many? It's okay?
Yes, sir, no problem. You can continue.
Okay,
There is no speaker.
Okay. So yeah, I will finish the time. Here you see that, and this reaction, I mean, already I showed this reaction in microwave, that is formation of this unsymmetric diaryl selenide or telluride, jalpuridonide. This something, I mean, saw it microwave. You have another reaction in ball milling, greener. But one of the problem with these reactions is that formation of diazonium fluoroborate, diazonium salt. If we have an heteroaryl amine or this, you cannot make the diazonium salt in a standard procedure. The non-sodium, there's a method, but it's not that straight cut. With sodium nitrate HCl, you cannot make the diazonium salt with this heteroaryl amine. The same with this, if we have there's an acetylic aniline, these things, here also on the diazonium condition, you can get this compound. So sinolene. So that's the problem, that when applying this chemistry, which is this in ball milling and microwave, that using the forming the diazonium fluoroborate and reacting that is not applicable here. So what is the how that can be solved? I took that example in the way how that can be solved. The problem, what is the problem here? Drawbacks is that using the HCl. When you are using an acid, it forms a salt. When there is an acid, the HCl forms a salt to the heteroaryl amine. That's the problem. So it's not reacting sodium and HCl, it's forming the salt. So anybody's conception is that if we cannot avoid using HCl, naturally you can then solve this problem. But you need the diazonium salt, diazonium moiety, but we don't want to use HCl or any acid. How to do it? Here we found a solution. And we found that any kind of aniline, any kind of substituted NH2, whether it's heterocyclic or this aryl or heteroaryl, or here also, there's all kinds of particularly problem with the heteroaryl. So we've taken all kind of heteroaryl amine and with this diaryl diselenide or telluride, we did not use any acid. What we use is tertiary butyl nitrite, same Eosin Y and DMSO at room temperature, 2 hours with blue LED. we can get the expected the selenide, sulfide, and telluride. Okay, so as we have not using any acid, but we are getting the diazonium moiety. I will come to the example. I mean that the end. We are getting diazonium moiety, but we are not using any diazonium salt. That's why without using any HCl, we can get the reaction to go in the same way what we expected. Okay. And selenides, there are selenides are very useful things. There's some examples here where you can see that selenides are very, very important for biological activity. Okay, here the same reaction when you do it, apply the selenide, you can get selenide, and many kinds of selenide you can get it. Particularly, that's use a heteroaryl, which is not possible by other methods. Here you can get heteroaryl selenide, many heteroaryl selenides, and all substituted different variety of substitution. You can get a very good yield of these compounds. Okay. You can get the sulfide, the general reaction. When you have a sulfide, you can get the sulfide. When you have telluride, you can get the telluride. And if you look at the yield, is very good. And here also, the yield is very good. And after the reaction is over, you can just evaporate the DMSO, and then you can make a short column chromatography. You can get the compound. It does not need a very rigorous column chromatography. So because the yield is very high, you can get it just purified with the short column chromatography. Okay. Now, what are the problem there? Now we can make, there's no problem now with this method. You can make the selenide or sulfide or telluride with this method. We have many examples here. Now we can get this, all these things. Okay. Now, okay, this is important. So as we are not using the acid, what we're getting that's from aryl, this whatever heteroaryl amine or amiamine with tertiary nitrite, you can get this diazonium moiety. And this, the eosin Y with the blue LED, this is got now photocatalyzed eosin or photoactivated eosin Y. So this thing now undergoes a reduction by single electron transfer process by eosin Y to, eosin Y, activated eosin Y to give this radical. And that is the key reaction. Once you get the radical, it reacts with your diselenide also, giving this radical, and which then suffers again one electron oxidation. Here reduction, so here one oxidation to give this cation. And this one, then in a solvent, you can get this desired or expected selenide or sulfide or telluride. So that is the key reaction, that without using any acid, we are getting the diazonium moiety. This is known. That is not our invention also, this is known. But we are just only taking the advantage of this chemistry, and then it goes to this aryl radical. And this visible photolysed chemistry, Koenig has very good important concern, and he has many good examples of producing this aryl or this radical, which can react with this. So one of the good things, those who like to continue or do some research on this visible light photochemistry, which is also very emerging. So you have to find that if you can make a radical, your job is done. How to make it? That's your question. You add something, some group here, which can form a radical very easily. If you can do that, your job is done. If you get a radical, whatever radical, that is reactive and that can give a new chemistry. That's the thing I'm telling. And really, Koenig has got a very new, many good chemistry based on this concept, just on this concept. Okay, I'll give another more example from a lab, that is synthesis of biheteroaryl. It looks like synthesis of, say, unsymmetrical again heteroaryl, biheteroaryl is not that easy. If you look at the literature, one method is that heteroaryl halide, and we have that heteroaryl boronate or stannine or silane, then we can get this compound with changes in metal catalyst, ligand, base, high temperature. Look at the condition. Another condition again, the CH activation. Here also you have heteroarene, and then you have heteroaryl jet means iodide or stannine or boronate. And here you can get with changes in metal catalyst, ligand also, that all same condition, you can get this thing. So, these two methods show that you have to need a transition metal catalyst, a ligand, high temperature. So that is not desirable for any good synthesis or simple synthesis. But you can solve this problem very easily in the same chemistry, that if you have, say, any heteroaryl amine, we take this compound, then tertiary nitrite, nothing else, tertiary nitrite, eosin Y, DMSO, same condition, blue LED, you can get the same mechanism, we can get this plus N2 plus, and then we can get the radical, and then it reacts with the thing. And one chemistry already shown in the beginning of this, the chemistry is same, but you can get the diheteroaryl compound using the known chemistry but a different technique, simple green technique. Okay, so it is transition metal free, additive free, acid free, and done at room temperature. What can be better than that? So that is all the green synthesis are the parameters of green synthesis. Okay, many examples. If you look at this, different kind of heteroamine we have used. This biheteroamine. Look at this. This is your tetrahydro, your furan and this, and then you have got furan and quinoline. Any sorts of things. Any sorts of things you can find out that we made it this year. So it is really any heteroarene you talk about, we can make this biheteroarene using this compound, using this technique. So look at this variety of this, okay, and with any substitution. Here also the LED, the good part of LED is that the substituents are not affected under this condition. Most of the substituents found that. Okay, so I'm taking that this mechanochemistry and visible light photochemistry are growing very fast. It's true, and will certainly occupy important room in the chemistry for future. Really, as I told you, that industries are now attracted to this chemistry, both mechanochemistry and visible light photochemistry, and that is get a very green methods, the green procedure for synthesis. So this is a great future, I think. So anyone who like to start chemistry or who are even practicing chemistry can think of, there are still is virgin. Many people are working on the mechanical chemistry in India. When I started, there was no one. But now many groups, I'm happy to see that many groups in India are now practicing mechanical chemistry and visible light photochemistry. So that's really, and still has a great future. So anyone, any inspiring or say aspiring scientist, budding scientist can think of this. Okay, they acknowledge this. All my students associated in these works. I'm not taking the name because there are many people here associated, and of course my institute ISS, where still I am enjoying, and funds at different times. DST, INSA, they're the usual funding agency. So I thank all of them for this, for helping me or supporting me throughout my career. And well, I thank you for your attention, and also again I'm giving me this opportunity to share our works with you. So thank you, and if you have any question or any query, I'll be happy to answer.
Thank you so much, sir, for your wonderful lecture. I think all the participants have learned so many new things, and like ball milling, application of ball milling, and application of visible light for different various organic transformations. So thank you so much, sir, for sharing your valuable research work with us. So now and in your lecture, you have already covered the importance of green chemistry, then this various objectives of green chemistry, and disadvantages of organic solvent, diol-solder reaction in water, then mechanic chemistry like application of ball milling for various reactions like trans-esterification reaction, oxidation of thiols to disulfides, synthesis of unsymmetrical diaryl chalconides and 1,2,3 triazole synthesis, and then carbon-carbon bond forming reactions, then avoidance of solvent. This is a very huge achievement in terms of green chemistry principles, and then CH bond activations, then applications of visible light using visible light or blue LED. You have synthesized this selenide and telenides and biheteroaryls and CH arylations. So thank you so much, sir, once again. Now I'm requesting any participants who want to share your views. Ramandeep, you can unmute and share your views. She is our BSc 4 students, graduate students, 4th semester.
Hello.
Yes.
First of all, I want to my warm thanks to our respected staff who organized this conference. And thank you so much, sir, for your informative presentation. We learned many new things from your presentation. Thanks a lot, and God bless you, sir.
Yes. Any question?
No, sir.
Did you understand the chemistry?
Yes, sir.
Okay. Thank you then. Okay.
Thank you so much, sir.
Thank you. Any other participants?
Yes, sir. Can you hear me, sir?
Good afternoon.
Sure.
A very good afternoon, sir. I am Musarraf Shamim and I am from Kashmir, and I am a student of MSc Chemistry, Jammu University. And first of all, please have my sincere gratitude for this wonderful talk. It gives me immense pleasure to share my views in front of you. All the lecture was wonderful and full of the information. As far as the magnetochemistry is concerned, it is I have learned so many things new because I haven't studied yet about magnetochemistry. I have learned so many new things. There are so many wow moments in your lecture, such as you have described carbon-carbon bond formation reaction through ball milling process. As I have learned this, what is ball milling process? What was the advantage of it, and what are the applications of it? As you have described the dial-Seltzer reaction, also solvent-free dehydrogenation of terpene in ball milling, carbon hydrogen activation, reduction in ball milling, and visible light-mediated green protocol for synthesis of biheterocycles. So in this lecture, I get the idea how one can avoid toxic organic solvents. And as we know that using hazardous solvents are very harmful for our environment. So in current scenario of green chemistry, you have covered every topic and I guess every line. There is nothing such a question which I can raise, but I can appreciate that whatever you have described and you have given to us in this precious time. And I would like to ask you one more thing. I have attended your one more lecture on value-added course, which was organized by Department of Chemistry in this International University in the month of August. That was also very, very informative session, sir. And all the movement were for me as you have completed all the current scenario of green chemistry, which helps us to reduce the toxicity rate and get atom economy product and energy efficiency, which are the principles, such some of the principles of green chemistry. Thank you so much, sir, for this wonderful talk. And it was a
Okay, you're
dream to have
welcome.
you.
Thank you so much. Okay, maybe we'll meet
Thank
some
you, sir.
online.
Thank you, Musarat. Now I'm requesting Monica because she wants to tell us something. Monica, can you hear me?
Yes, sir.
Oh, Nirjar. Yes, please.
Yes, sir. Actually, I have no particular question, but it was both of the lectures was very good and all over nice session, and we have learned many things from these two eminent professors, and they are also the eminent in green chemistry field also. So we have learned new techniques also like ball milling, sunlight, and the water mediated chemistry by Professor Chakraborty sir. So it was all over a good, very good session.
Good. All of you are telling the same thing, praising us. But the question is, okay, we will be very happy if you have some. How do I understand that you have understood everything? I look that you are telling all the things, all are same voice. Huh?
So, dear participants, if you,
I'm the lighter side. It's okay.
so dear participants, if you want to share your views or if you have any question, you please ask, because this is a good opportunity for you people to interact with Professor Anu, and Professor Chakraborty sir is also with us right now. So you can interact with sir also. Now, Diksha, if you have any question or you can share your views.
Good afternoon, sir.
Yes.
Sir, first of all, I would like to thank you for making something certain in this time of so much uncertainty. That is letting us learn everything new that's happening around us, and knowing about the emerging tools in green chemistry is already a win-win. Listening to you guys is already a great opportunity that we can't thank enough. And yes, we did learn a lot. I can assure you that when we learn something interesting, the time just flies by, and it did fly. We could not realize how much it took, but yes, we enjoyed it a lot. And I can assure you that you did open new doors to knowledge for us. Thank you. Thank you so much, sir.
Thank you. Very welcome.
Thank you, Diksha. Now I'm requesting Rajvinder.
Good afternoon, sir.
Yes.
Thank you, sir. Thank you so much for such a nice and
semester.
informative presentation. We learned many new things like ball milling and visual mediated reactions. And this was very informative, and we are very grateful to you, sir. Thank you. Thank you so much.
Thank you.
Thank you. Now, any participants, if you want to share your views or if you have any question, please.
Hello,
Excuse me,
sir.
Yes, Sumitra.
Sumitra, is it okay?
Hello, sir. I am Sumitra Murmu from
Yes.
Krishna Chandra College. Sir, I have a question. You have said that exam mechanochemistry
Yes.
with matter. You said that the mechanical energy.
Sumitra, you can speak in Bengali also. Sir can understand Bengali. No issue.
থ্যাংক ইউ স্যার।
And I
বলছি স্যার আপনি যেটা এক্সাম্পলটা দেখালেন, স্যার আপনি যে এক্সাম্পলটা দেখালেন মোটরের এক্সাম্পল দিয়ে, যে সেখানে মেকানিক্যাল কেমিস্ট্রি মেকানিক্যাল এনার্জিটা রিয়াকশনের টাকে আগে নিয়ে যেতে সাহায্য করছে। সেই ক্ষেত্রে সেটা আমি বুঝতে পারলাম যে সেটা বুঝতে পারলাম না যে মেকানিক্যাল এনার্জিটা সেখানে কি হবে, প্রোডাক্ট তৈরি হবে।
Okay, one thing. I understood. The full understanding, or very precise understanding of mechanical is still known. But what is till now, what is going on and what is conveyed is that the application of mechanical energy then makes a bond elongated. Say you have a carbon-nitrogen bond, or say carbon another bond. So by applying mechanical energy, you are now weakening that bond, and then another nucleophile reactor now attack. This is known so far that that is the thing, that direct absorption of mechanical energy makes a bond elongated and then weaker. Like you say carbon iodo bond, carbon bromo, carbon chloro. So because carbon and iodo bond is longer, so that is more reactive. So if you have make it further longer, so that will be more reactive. So that is actually the principle of the understanding so far at this point is that application of mechanical energy makes a particular bond more reactive, making the living group easily cleavable. Understand?
Okay, sir.
Thank
Or
you.
any other?
Okay, sir.
Okay,
Thank
sir.
you, Sumitra. Now I'm requesting Shivalika from.
No, sir.
Any other question?
Yes,
No, sir.
sir.
I have not.
Okay, thank you. Okay.
Now I'm requesting
Sir,
Shivalika.
Okay. Someone is taking something?
Yes, sir. I have a question. I'm Namneetka, research scholar for my RIMT University, Mandi Govindgarh.
Yes.
Sir, I have a questions regarding synthesis of compounds and what we synthesize, whether it is for ball milling method or any other method. How we can say that what we synthesize organic compound or inorganic compound, they are eco-friendly and are not hazardous to the environment. How we set the criteria scientifically?
I still, I don't, your voice is cracking. Okay. You say diazonium salt or something like that?
Sir, my question is that once we synthesize the organic compound, whether it is by using ball milling method or any other method, how we can ensure that our organic compound or inorganic compounds are eco-friendly and are not hazardous to the environment?
How do you know it? Okay. If any compound, there is, let's say, you can say now there is, you can say encyclopedia of compounds. So there are many now, you can say the website, you have many repository, or you can say many directory where you can find the particular compound is hazardous or not. But if you have a new compound, then it's not said. But easily you can find that. Say if you put a Google, the toxicity of compounds or the this, you can find many books or handbook. In that handbooks, the compounds are noticed where you can find the thing, whether it is toxic or not. Okay, that's your question.
So my question is that we can see the material safety data sheet also, but if we synthesize a new compound, and how we can set the scientifically, we can give the solid reason that our substance or our compound is not hazardous.
Okay, if you have a new compound, then you have to experimentally find out the toxicity and all the things. There are many methods that you can find out the toxicity of any compound. Okay.
Okay, sir.
You can find out that yes, there is established technique to find the toxicity of any compound. Like the drug company, pharmaceutical company. Whenever they make a new compound, first thing they study the toxicity of the compound. That is found in any academic lab. There are many academic labs we can find the toxicity of compounds.
Okay, sir. Thank you so much.
Sure.
Thank you, Navneet. Now I'm requesting Sivalika from BSc 4. Please share your views.
Yes, sir. Good afternoon, sir.
Good afternoon.
I would like to thank you for giving a valuable time to us. Your lecture means a lot for us, seriously. It was beyond excellent. I saw one thing, how we are able to keep the audience engaged throughout your PPT presentation was great. Heartily thank you to you, sir. Thank you so much.
Thank you. Okay.
Thank you. So, dear participants, any other participants you want to interact directly with you? This is a good opportunity for you people. So, any other participants want to interact? Even Professor Asit Chakraborty sir is also with us now. Yeah, Amandeep. Or Amandeep. Any other participants from Akal University? Okay, if no, there is no question. I'm again thankful to you, sir, Asit Chakraborty sir and Bishiranu sir. Thank you so much for giving your valuable time. Now I'm requesting our head of the department for the vote of thanks. Thank you so much, sir. Over
Thank
to
you.
HOD Dr. Sandeep Kumar sir.
Unmute. So thank you to Professor A.K. Chakrabarti sir and Professor B.C. Ranu sir and all the participants who have attended this first technical session. Sirs, it was a great privilege for all of us to listen you and listen the part of your knowledge. It was not a complete knowledge you possess. It was just part of the knowledge we have received. And it was a fortunate for us to be part of this session. So I'm pretty much sure that all of the participants, they must have learned a great deal of knowledge from the lecture you have delivered, especially in the field of organic synthesis and especially in the green chemistry, because this is the recent trends being followed for the synthesis. So I hope we get a chance to meet you again and again, and if possible, face to face whenever this pandemic will over. We like that you must visit our institution and have face to face interactions with the student. I'm falling short of my words to express my gratitude to you esteemed personalities, but I'm really falling short of the words. So with this, I'm just thanking you for delivering this such a great and informative session for our students. Thank you, sir. Thank you very much for enlightening the knowledge of our students.
Okay.
Thank you.
All of you.
Now I would like to request our Dean Research, Professor Shantanu Ghosh, to say a few words of thanks. Over to you, sir.
Okay. So I thank the two eminent speakers, Professor Chakraborty and Professor Ranu, from the bottom of my heart for this engaging 2-hour session, which felt like a few seconds for me. So there has been a huge breadth of knowledge and information that has been shared by the speakers. And I'm sure that participants have got a lot of benefit, derived a lot of benefit from this interaction. And again, I take this opportunity to thank on the behalf of Akal University Department of Chemistry, both our esteemed speakers, and also congratulate Dr. Sandeep Kumar and his departmental colleagues for this wonderful compilation of speakers. Thank you very much.
Thank you.
So thank you so much, sir. Asit sir, can you hear me?
Yeah, I can hear you.
Thank you so much, sir. Thank you so much for your valuable time, because in this pandemic situation, the benefit is we can hear from you, or our participants can hear you like this in online platform. But the disadvantage is we can offer a cup of tea also in this online mode. So thank you so much. We will definitely organize a offline conference and definitely invite you to share your knowledge from campus in front of our
Sure.
students. And thank you so much. Thank you, sir. Thank you so much for your valuable time. Thanks a lot, sir.
Thank you.
All the best.
We'll take it after some time. Okay. Thank you, Oshit. Nice to see you.
Thank you, Vindavanda. It's
Yeah,
good that I could meet you virtually, although we are in the same city, but we cannot meet each other.
Okay. Thank you. Thank you, everybody, Bubun and all other things. Okay. Thank
Yes.
you.
Thank you so much, sir. So, dear participants, we will again meet in the second part, which will start from 4:45 p.m. Thank you.
Okay.
Sorry, 1:45. Thank you.
Sure.
Thank you. Thank you, sir.
Okay.
Thank you.
Good afternoon, sir.
Very good afternoon, Navjeet Kaur ma'am.
Good afternoon, sir.
Good afternoon, ma'am. And we are waiting for all the participants. We will start your lecture sharp at 2. Okay.
Okay,
so
sir, sure.
after 5 or 6 minutes, all the participants will definitely come. Okay.
Okay, sir.
Dear participants, we will start this lecture sharp at 2. Thank you. Very good afternoon to all of the participants and respected speaker, Navjeet Kaur Madam. Thank you so much for your valuable time, and definitely we all, means including all the participants, learn many things from your valuable talk. So to introduce Madam, I want to share a PPT. Please wait for me. Yes. Yeah. Dr. Navjeet Kaur Madam is now working as assistant professor at Department of Chemistry, Banastali University. It's a NAC A++ graded university from Rajasthan, Jaipur. Madam did her PhD from the same university. She received a PhD from 2014 under the supervision of Dharmakishore sir, and she did masters from the same institute, that is the Department of Chemistry, Banastali University, Rajasthan, and she did BSc from Punjab University, Department of Chemistry, Chandigarh, and most importantly, she has published almost more than 150 research publications. And recently, in last year, she enlisted among the 2% of the world's renowned research scientists. So many congratulations, Madam. And definitely we will invite you to share that experience later in any other webinar. And Madam, now 5 research scholars are working under Madam's supervisions. And with this, Madam received so many awards, and Madam delivered different lectures. So with this short introduction, I'm welcoming you, Madam, once again at the Department of Chemistry. On behalf of Department of Chemistry, Akal University, thank you so much, ma'am, once again for giving us valuable time. Now I'm stop sharing this my slide, and you please now share your presentation and go ahead. Over to you, ma'am.
Okay, thank you, sir. So my screen is visible to you?
Yes, ma'am.
Okay,
yes.
Thank you, sir. Good afternoon, everyone. Myself, Dr. Navjeet Kaur. I'm from Department of Chemistry, Banastali Vidyapeeth. And
Madam, can you please start your video as well?
Okay, sir, sure.
Yes, ma'am. Thank you.
Okay. My today's topic is green chemistry, and then it's the synthesis of 1,4-benzodiazepines. Chemistry is an old science that is involved in every aspect of life on the earth, and it is known as mother science. The main essential feature of chemistry is the synthesis. According to E.J. Corey, he quoted that a chemist who designs and completes the original. Just a second, sir. Okay. According to E.J. Corey, a chemist who designs and completes an original and aesthetically pleasing synthesis is like a composer, artist, or a poet who, with his great individuality, fashions into new forms of beauty from the interplay of mind and spirit. So if we talk about green chemistry, which is the need of today's green chemistry is a utilization of a set of principles that will help us to reduce the use and the use and generation of harmful substances during the manufacture and application of chemical products. And green chemistry aims to protect the environment, not only by cleaning up, but by discovering new chemical processes that will not pollute. And this chemistry is a rapidly developing and an important area in chemical sciences. If we talk about the relation between green chemistry and synthetic chemistry, then synthetic chemistry is the branch of chemical sciences in which we synthesize new chemicals and develop new modified ways of synthesizing the existing chemicals. So a key aspect of green chemistry is the involvement of synthetic chemists in the practice of environmental chemistry. Synthetic researchers or synthetic chemists whose major objective has always been to make new substances and to make new cheaper and better, something that will not harm the environment. So now the time has arrived for a synthetic chemist to make or to generate those chemicals that will not pollute the environment and whose use and ultimate disposal of chemicals will be as much as environmentally possible. Green chemistry removes the additional cost by eliminating or reducing the use of toxic and harmful feedstocks, catalysts, and the generation of dangerous intermediates or byproducts, so that we can meet the environmental and safety requirements of conventional chemical manufacturers. So if we talk about this diagram, then in this case, we can say one step towards green chemistry is that we should use the existing environmentally benign chemicals, or secondly, we can do that substitute the other feedstocks that are made by environmentally benign processors. Principles of green chemistry. 12 principles of green chemistry are there, whose motto is to prevent waste and atom economy, less hazardous synthesis, safer chemicals and products, safer solvents and auxiliaries, and design for energy efficiency, use of renewable feedstocks, avoiding chemical derivatives, catalysis, design for degradation, and real-time analysis for pollution prevention, and then is minimize the potential for accidents. If we talk about these principles one by one, then one is the prevention of waste or byproducts. It's better to prevent the waste than to treat and then clean up the waste after that it is generated. Next is atom economy. Atom economy or atom efficiency is the conversion efficiency of a chemical process in terms of atoms involved. Atom economy is the molecular weight of desired product by molecular weight of all reactants into 100. So this is a typical reaction which is which occurs with less than 100% yield and with byproducts. We take reactants, and if the desired reaction will take place, then we will get desired product. But along with this, sometimes a side reaction occurs from which we get byproducts, and even sometimes byproducts are generated because they were inherent to that desired reaction. And next one, sometimes our reaction can be incomplete. That will also produce, that can also result into a leftover reactants that will also like a byproducts. And other is a reaction with 100% yield. In this case, reaction will occur with 100% yield, but we will also observe byproducts which are inherent to the reaction. So reactant to desired reaction, then products, but sometimes some inherent reaction occurs that will produce byproducts. Next is a reaction with 100% atom economy, in which is are those reactions in which there will be no leftover reactants and there will be no byproducts. So in this type of reactions that are totally towards green chemistry, in this case, we will take reactants and we'll get the desired product without any byproducts and without any leftovers. Next is the minimization of hazardous products. Wherever and whenever practicable, synthetic procedure should be the one which can use and generate substances that has no or little toxicity to people or environment, and designing safer chemicals Chemical products should be designed to effect their desired function while minimizing their toxicity. And next is use of safer solvents and auxiliaries. The use of auxiliary substances, we can say solvents, separating agents, they should be made unnecessary wherever is possible. In green solvents, we can use ionic liquids. Ionic liquids are liquids at room temperature or below. They are non-volatile and they have high vapor pressure. They can serve as the optimal replacements for traditional volatile organic solvents. Reactions occurring in ionic solvents will not need any, they don't need any special apparatus, and they can be recycled. Next is supercritical carbon dioxide, which is a fluid and is known as a green solvent, and is a solvent with low viscosity and has no surface tension. It has a unique ability to diffuse like gases through solids and to dissolve a wide range of organic substances and catalysts, etc. The supercritical carbon dioxide fluid is now attracting the attention of commercial and industries, and is used as a solvent for the separation because it's low toxic and is non-inflammable. And its stability and its low temperature of the process allows us to allows us that we can extract the chemicals or extract our products with little damage or denaturation. Now, because carbon dioxide is obtained as a byproduct of other industrial processes, so it is inexpensive, and because it's a gas, it can be easily evaporated and will not leave left any residue. Next green solvent that we can use is a supercritical water. Organic substances are insoluble in water. So many compounds which are soluble in water, they become soluble in water when it becomes supercritical. So this is clean and cheap solvent and is regarded as a green solvent for many synthetic reactions. Next is reactions in aqueous phase. Use of ordinary water, not the supercritical one. Use of ordinary water for organic reactions was unknown till the middle of 20th century. However, replacement of organic solvents starts occurring with eco-friendly water, and it has an immense degree of success. And some of these reactions may occur at higher rates because of its high polarity. And the reactions that we carry out in aqueous medium that can include reductions, oxidations, polymerization, and many other named reactions. And other possibility is that we can perform our reactions on solid phase. And many reactions that we perform on solid phase that occur without any solvent. And these reactions are simple to operate, they are economical, and in these type of reactions, as we are not using any solvent, so any type of pollution that is linked with solvent can be avoided. This is designed for energy efficiency. Energy requirements of chemical process, they should be recognized for their environmental and economic impact and should be minimized. If possible, then a synthetic procedure should be one that can be performed at ambient temperature and pressure. And if we can, along with that, we can also develop alternative sources of energy like photovoltaic, hydrogen fuel cells, bio-based fuels can also be utilized. And these type of sources will make us move towards energy efficiency. In this case, we can use catalyst. And next is a microwave assisted reaction. This is also an approach towards green chemistry. Microwave assisted organic synthesis is the preparation of organic compound from available starting material via some procedure in which there will be a microwave irradiation. As microwave irradiation is less hazardous, it's a potential tool of green chemistry. Microwave synthesis opens up new opportunities for synthetic chemists in form of new reactions, especially those reactions which were not possible by conventional heating. If we compare microwave reactions with conventional reactions, then we will see in case of microwave, there will be increase in reaction rate. And in this case, specific material will be heated, and specific temperature we can maintain. and less solvent will be required, and there will be efficient internal heating, and heat flow will be from inside to outside. And now if we compare with the conventional, then conventional reactions usually occurs with decreased reaction rate. And we can, in this case, we can get compound mixture is not heated equally. And there will be no specific temperature, more solvent will be required. And in this case, heating will be external. And in heat flow will be from outside to inside. Next is ultrasound mediated reaction. The ultrasound irradiation, which is also known as a sonochemistry, it is also an important tool in organic chemistry. Reactions using ultrasound energies, they are generally carried out at room temperature, and they occur with excellent yields. Two main advantages of sonochemistry in organic synthesis are that these type of ultrasound irradiation will lead to increase of reaction rates and will also increase the product yields. So this type of technology is more convenient when we compare it with traditional method, or ultrasound mediated reactions can be easily controlled. Then is use of renewable feedstock. A raw material or a feedstock, it should be renewable and then depleting whenever technically and economically practicable. And next is why unnecessary derivatization that is used for blocking, and then for protection, deprotection, and temporary modification of physical and chemical processes should be minimized, or even because if we use if we will use more derivatives, then it will lead to addition, and we have to use additional reagents and will generate more waste products. It will take more time and higher cost of products. So it's the need of time that we should reduce using derivatives as much as possible. Next is a catalysis. Catalytic reagents are superior to stoichiometric reagents because catalysts are used in small amounts and they can even carry out a single reaction many times. So catalysts are preferred as compared to stoichiometric reagents, because stoichiometric reagents are generally we use in excess and they work only once. Next, catalysis can enhance the selectivity of a reaction, and it decreases the temperature of reaction. It reduces the reagent waste, and it avoids the unwanted side reaction that will lead to a clean methodology. Apart from heavy metal catalysis, some soft metal catalysis can also be utilized, like we can use zeolites, phase transfer catalyst. In phase transfer catalysts, crown ethers are very famous, and they are finding increasing industrial applications too. Next is designing of degradable products. Chemical products should be generated and so that at the end of their function, they can break down into into not harmful degradation products and do not persist in the environment. New analytical methods. Analytical methodology need to be further developed to allow for a real-time in-process monitoring and control prior to the formation of harmful substances. Next is safer chemicals for accident prevention. Analytic substances and the form of a substance used in chemical process should be chosen to minimize the potential for chemical accidents, including releases, explosions, and fires. And green, so we can say green chemistry is all about reducing the waste, material, hazard, risk, energy, and cost. Now, if we talk about the synthesis of 1,4-benzodiazepines, so overview is first is the introduction, then is preparation of starting materials. After that, we will synthesize oxidizolo, imidazo, benzimidazo, thiazidazolo, isoxazolo, pyrazolo, incorporated analogs of 1,4-benzodiazepines linked to 1,4-benzodiazepine through 2-phenoxyl and phenylamino bridge. Next is synthesis of pyrimido incorporated analogs of 1,4-benzodiazepines linked to it directly or through 2-phenoxyl or phenylamino bridge. Next is synthesis of benzodiazepine, benzothiazepine, and benzooxazepine incorporated analogs of 1,4-benzodiazepines linked to it through 2-phenoxyl bridge. Introduction. Why heterocycles? Heterocyclic chemistry is one of the largest classical divisions of organic chemistry, and heterocyclic compounds account for more than half of the chemicals that are known. Majority of the pharmaceuticals, both natural or synthetic, vitamins, insecticides, pesticides, herbicides, and dyestuffs, they contain or they possess heterocycles. And a considerable number of compounds synthesized in industrial sector each year are heterocycles. Different uses of heterocycles as a structural motif they can be used as new material as a protecting groups, as unique solvents and reagents, and they can these chemical intensities we can modify and substitute these heterocycles too. Synthesis of heterocycles, if we talk about general methods of ring synthesis, then most of the methods for synthesis of heterocycles are classical, and the synthesis often it involves a condensation reaction of some sort. Modern examples usually involve different type of substitution patterns on the ring, and in this case we will match the electrophilic and nucleophilic functionality. An ideal synthesis, if we talk about any ideal synthesis, then ideal synthesis will be the one that will produce a desired product in a few steps as possible, in good over yield, in good total yield or overall yield, or by using environmentally compatible reagents. Synthetic variables that usually are optimized are time, cost, yield, simplicity of the performance, safety, and environmental acceptability. 1,4-benzodiazepine nuclease is known to show a wide variety of biological or pharmacological properties. So on 1,4-benzodiazepine nuclease, we have appended condensed heterocyclic systems like oxadizole, imidazole, benzimidazole, thiazole, isoxazole, pyrazoles, pyrimidines, 1,5-benzodiazepines, 1,5-thiazepines, 1,5-oxazepine nuclei, and this field has attracted the attention of chemists on because of the significant medicinal properties associated with these type of compounds. 1,4-benzodiazepine is known for its anti-tumor, anti-ulcer, anti-convulsant, biological activities, etc. Our main aim in the present work is to synthesize 1,4-benzodiazepine molecules, which will include structural features of other bioactive pharmacophores which had the previous history of being biological activity with the expectation or on the premise that their presence in a single molecular framework can contribute significantly to the biological activity in the resulting molecules. So first of all, we will synthesize a 1,4-benzodiazepine nuclease. And after that, on 1,4-benzodiazepine nuclease, we will append other heterocyclic moieties. And like we will append oxadizole, imidazole, benzimidazole, thiazole, isoxazole, pyrazole, pyrimidine, 1,5-benzodiazepine, thiazepine, and oxazepine nuclei on 1,4-benzodiazepine nuclease. This is etravirine. Etravirine is a FDA-approved anti-HIV drug. In this case, we can say we have majorly three portions. One is the aminopyrimidine, and the other one is the para-cyanoxyphenyl, and the third component of etravirine is para-cyanoaminophenol. So our second strategy in this present work was to incorporate the vital fragments of FDA-approved drugs. Fragments are aminopyrimidine, para-cyanoxyphenyl, and para-cyanoaminophenol on 1,4-benzodiazepine nuclease. So if we conclude this in diagrammatic form, then we will take, first of all, we will synthesize 1,4-benzodiazepine nuclei. Then we appended different, then we appended a bridge on
अल्ट्रासाउंड असिस्टेड mediated reaction में जाके वो स्टॉप हो गई. Dear participants, currently we are facing some technical problem, maybe at the speaker's end. So as soon as it is resolved, we'll again resume with the presentation of ma'am. So kindly bear with us and have patience. Thank you.
Local. कोई होगा हम लोगों को बचा रहा है। आ गया सर मैं dear participants, sorry for the inconvenience caused. I think Madam will start.
Sorry, sir. Sorry.
No problem, ma'am. No problem. Yeah, now it is.
So, sir, should I start from here, sir? Or from next slide?
Yes, ma'am, your slide is not visible right now.
Okay. Okay.
Yes, ma'am. You can continue from this slide. Thank you, ma'am.
Okay, sir. Thank you. This is atravirine. Atravirine is a FDA-approved anti-HIV drug. Sir, am I audible to you?
Ma'am, yes.
Oh, okay, sir. Okay. This atravirine drug that is FDA-approved has been three components. One is aminoprimidine, and the second one is the para-cyanoxyphenyl group, and third is para-cyanoaminophenyl. And our second strategy was to incorporate these vital fragments of FDA-approved drug on 1,4-benzodiazepine nucleus. If we see diagrammatically, then we'll see that we have, first of all, we will synthesize 1,4-benzodiazepine nucleus. And then on the second position of 1,4-benzodiazepine, we had appended oxyphenyl and phenyl amino bridges. Or we can say they will act as a spacer or as a bridge. And then on through these spacers, we appended some nuclei We have appended 5-member heterocycles, that is oxidizole, imidazole, benzimidazole, thiazole, isoxazole, and pyrazole. And in next segment, we have appended 6-member ring, that is pyrimidine. And we have also appended 7-member heterocycles, that is 1,4-benzodiazepine, 1,5-benzothiazepine, and 1,5-benzooxazepine. Next is preparation of starting materials. Starting materials were like we have synthesized amidins, then we have synthesized immediate esters, and this one is the thiosemicarbazole, and we have synthesized dimethylamino-methylene ketone intermediate. Next is charcoal. So we can say in these two are amidins. One is through oxyphenyl bridge, and one is with the phenylamino bridge. And in case of immediate esters too, one contains the phenylamino bridge, and other one contains the oxyphenyl bridge. First of all, we have taken acetylene molecule as a starting material, and then we reacted it with chloroacetyl chloride to form N-chloroacetyl derivative of acetylene, which further we have reacted with hexamine and methanol, and it results into the cleavage of this ring and formation of an expanded ring, that is 1,4-benzodiazepine molecule. After that, this ester group is converted into carboxyamide group on reaction with methyl piperazine. After that, we have added chloride group on this position to form an amino chloride intermediate. When this amino chloride intermediate is reacted with the paracyano molecule, in this case, in place of X, it can be NH or OH. In case of OH, it will be paracyano-phenol. In case of NH, it will be paracyano-aniline. And on reacting amino chloride with this molecule, we will get a nitrile. And when this nitrile derivative is reacted with hydroxyl amine hydrochloride, it will form amidin intermediate, and it will react it with methanol in presence of HCl, then we will get immediate ester. When this amino chloride intermediate, or we can say is a nuclei, is reacted with para-hydroxybenzaldehyde, then we will get an aldehyde derivative, which on reaction with thiosemicarbazide will form thiosemicarbazone intermediate. And in third branch, we have reacted this amino chloride with para-hydroxyacetophenol, by which we will get this ketone intermediate. On one hand, we have reacted it with DMF-DMA to form a dimethylamino-methylene ketone intermediate. And in other reaction, we have reacted it with benzaldehyde to form a chalcone intermediate. Then the synthesis of oxidizole, diazolo, imidazole, benzimidazole, thiazole, isoxazole, and pyrazole, incorporated analogs of 1,4-benzodiazepine linked to it through 2-phenoxyl or phenylamino bridge. Our aim in this section is to incorporate 5-member bioactive pharmacophores on the second position of 1,4-benzodiazepine molecule, with a premise to develop a novel synthetic analogs of medicinal interest. We will append oxidizole nuclei, imidazole, benzimidazole, thiazole, isoxazole, and pyrazole nuclei. Structures of the 5-member nuclei. And the structures that we will synthesize in this section will be are oxidizole, derivatives of 1,4-benzodiazepine. Then is imidazole, derivatives of 1,4-benzodiazepine. Then is benzimidazole derivatives, isoxazole derivatives of 1,4-benzodiazepine, and is pyrazole derivatives. And finally, we have thiazole derivative. And the difference between these two are that one is through oxyphenyl bridge, and another one is phenylamino, and same is true for these two complexes also. First of all, in this case, for incorporation of oxidizole ring on second position of 1,4-benzodiazepine through a phenylamino bridge, we have taken the intermediate, that is amidin, and it's reacted with chloroacetyl chloride. And in next case, the same reaction is happening, but the difference is that first reaction is is with the molecule which have phenylamino bridge, and the second reaction is with the molecule which have oxyphenyl as a spacer. In this case, we have taken the immediate ester intermediate. When is reacted with ethylene diamine, it will give a imidazole derivative of 1,4-benzodiazepine. Here, imidazole ring is in reduced form. Then after that, it is oxidized with the iodoxybenzoic acid to form an oxidized imidazole ring. And in next reaction, we have reacted immediate ester with ethylene diamine to form a reduced imidazole ring, which is oxidized with iodoxybenzoic acid. In this case, we have taken immediate ester intermediate, which is reacted with orthophenylene diamine to form an benzimidazole ring. And this benzimidazole ring is incorporated on the second position of 1,4-benzodiazepine through phenylamino bridge. In this case, same reaction is happening, but the difference is that in this case, we have appended 1,4-benzodiazepine nucleate through an phenoxyl bridge. Here we have taken thiosemicarbazone intermediate and is reacted with iron ammonium sulfate to form thiazole ring. Then we have taken dimethylamino methylene ketone intermediate. When it is reacted with hydroxylamine hydrochloride in presence of a base, it will form an isoxazole ring. Similarly, when this chalcone is reacted with hydroxylamine hydrochloride in presence of a base, it will give us a reduced isoxazole ring, which is then oxidized with iodoxybenzoic acid. In this case, we have taken dimethylamino methylene ketone intermediate, which is reacted with hydrogen to form an pyrazole ring. In this case, we have taken chalcone intermediate, which is reacted with hydrogen hydrate to form a pyrazole ring. This is a reduced one. So in next step, we have oxidized it with IBX. Next is synthesis of pyrimidine incorporated analogs of 1,4-benzodiazepines linked to it directly or through 2-phenoxyl or phenylamino bridge. Pyrimidines have been already known for their chemotherapeutic activities, for their biological activities, and they possess a wide range of biological properties. Because of this, in the literature, pyrimidines are known as privileged scaffolds, and we have taken this. We have appended these pyrimidine nuclei on 1,4-benzodiazepine nuclei through phenoxyl or phenylamino spacer. Structure of compounds. Here we can say we have in all these structures we can see we have appended pyrimidine nuclei on second position of 1,4-benzodiazepine through phenylamino, or in all these 5 through oxyphenyl bridge. So here we can say in this case we have in these 2 compounds we have incorporated pyrimidine nuclei, and we have started with chalcone. So here we can say this component, as I've already told in my previous slides, that this aminopyrimidine is a component of etravirine drug. So we have incorporated this component of etravirine on second position of 1,4-benzodiazepine. And in this case, we have incorporated 2 components of etravirine. That is, one is aminopyrimidine and next one is para-cyanoxyphenyl. In this case, again, we have incorporated 2 fragments of etravirine on 1,4-benzodiazepine. One is aminopyrimidine, next one is para-cyanoxyphenyl. In this case, we can see that we have appended all the 3 components of etravirine on the 2 position of 1,4-benzodiazepine. One is aminopyrimidine, next is oxyphenyl, cyanoxyphenyl, and then is para-phenylamino. We have started with a amidine intermediate. When this amidine intermediate is reacted with the diethyl acetylene dicarboxylate, and it will construct a pyrimidine nuclei on second position of 1,4-benzodiazepine through phenylamino spacer. In next reaction, we have reacted this again with diethyl acetylene dicarboxylate. In this case, we have oxyphenyl bridge instead of phenylamino bridge. In this case, we have taken dimethylamino methylene ketone intermediate. When is reacted with urea, it will produce a hydroxypyrimidine ring. In this case, we have dimethylaminocytine intermediate. When it's reacted with thiourea, it will append a pyrimidine ring on 1,4-benzodiazepine nuclease through the phenoxyl bridge. Again, we have this dimethylamino-methylene ketone intermediate. In this reaction, we have reacted this intermediate with guanidine. When we reacted with guanidine, then we will have a aminopyrimidine ring on second position of 1,4-benzodiazepine. Again, now in this case, we have reacted the same intermediate with acetamidine. When it's reacted with acetamidine, then we will have a methylpyrimidine ring on second position of 1,4-benzodiazepine. So we can say, see that in all these three reactions, we have taken dimethylamino-methylene ketone intermediate, which is when reacted with thiourea, guanidine, and acetamidine. Then it will give us a pyrimidine nuclei. It will produce a pyrimidine ring, but this one is a reduced pyrimidine ring. So we will oxidize it with iodoxybenzoic acid. Again, when chalcone is reacted with the thiourea, in thiourea, it has given us an reduced pyrimidine ring, which is then oxidized with iodoxybenzoic acid to form a thiol substituted pyrimidine ring. Here we have taken amino chloride intermediate, and here as we can see, so these all are the components of etravirine ring. In case of etravirine, in this case we have taken the one component, that is aminopyrimidine, and we have appended this aminopyrimidine on second position of 1,4-benzodiazepine. And in this case, we have taken two components of etravirine that are appended on second position of 1,4-benzodiazepine. And again, here two components. In first case, it was paracyanoxyphenyl, and this case it is paracyano-phenylamino component. And now, if we see in last reaction, then we have appended all the three components of etravirine on second position of 1,4-benzodiazepine, that is paracyano-oxyphenyl, paracyano-phenylamino amino group, and then is aminopyrimidine ring on the second position of 1,4-benzodiazepine. Then is synthesis of benzodiazepine, benzothiazepine, benzooxazepine, incorporated analogs of 1,4-benzodiazepines through a phenoxyl bridge. Because of the interesting biological properties exhibited by azepines and 1,4-benzodiazepines, we have considered to design the molecule in which these moieties will be present in a single molecular framework, so that to see the additive effect on the biological potency in the resultant molecules. In this case, we will append 1,4-benzodiazepine, thiazepine, and 1,5-oxazepine nuclei on the 1,4-benzodiazepine nuclei. So the compounds will be like, we will synthesize this 1,5-benzodiazepine appended nuclei, then 1,5-thiazepine, this one and this one, blue in blue color, 1,5-thiazepine nuclei appended on 1,4-benzodiazepine nuclei, and then in pink color, we have this 1,5-oxazepine nuclei, which is appended on second position of 1,4-benzodiazepine. All these molecules are appended on 1,4-benzodiazepine through phenoxyl group. We have taken dimethylamino intermediate, which is reacted with orthophenyldiamine to produce an 1,5-benzodiazepine nucleus. In this case, we have taken dimethylamino-methylene intermediate, which is reacted with orthoaminothiophenol to produce a 1,5-thiazepine ring. In this case, we have reacted with orthoaminophenol to form an 1,5-oxazepine ring. Here we have taken chalcone intermediate. When chalcone is reacted with orthophenyldiamine, it produces a 1,5-benzodiazepine nucleus. This is again a reduced one. So we will oxidize it with iodoxybenzoic acid. In this reaction, we have taken chalcone, which is reacted with the orthoaminothiophenol, which will produce 1,5-thiazepine nuclei, reduced one, and then it's oxidized with an oxidizing agent to form oxidized 1,5-benzothiazepine nuclei. And this reaction, we have taken chalcone, and chalcone is reacted with the orthoaminophenol. When it's reacted with orthoaminophenol, it will give 1,5-oxazepine nuclei, When this 1,5-benzoxazepine nuclei is oxidized with iodoxybenzoic acid, then we will get the oxidized rate. Now, so we can say organic chemistry, organic synthesis is a pure and applied science. Scope is still unlimited. It surprises us all the time. So the way we do organic chemistry and the organic chemistry we do are both changing these days. And organic chemists will integrate the science. All these organic chemistry have so much applications in our daily life. And they provide us food and agriculture. In agriculture, we get fertilizers. Then they have a role in energy, petrol, and gas. Very important is heterocycles have a prominent role in medicines, and then polymers, textiles, and even in our daily life, like soaps, detergent, and perfumes. Future challenges that organic synthesis has already made a great contribution to the development of material and biological sciences. So we can expect an increase of its importance in future too. On the other hand, but for a sustainable future society, it's necessary that we redirect the traditional chemical industry towards the one which will be environmentally acceptable, or we can say chemistry that will be green and clean, and will and this type of green chemistry which will be that will be in harmony with the society. So this is a responsibility of a synthetic organic chemist to do better for the better life of humanity. So with these all 12 principles of green chemistry, I would like to thank you, all of you. Thank you.
Thank you. Thank you so much, ma'am. Thank you for your very lucid and valuable lecture. I think all participants, postgraduate as well as undergraduate students, have learned many things about green chemistry and their 12 principles. Thank you so much. Now I'm requesting, dear participants, if you have any question, please unmute yourself and you can ask directly to ma'am, because it's a nice opportunity for you people to interact with madam. Okay. Anyone? Please unmute and share your views if possible.
Good afternoon, ma'am.
Good afternoon.
Good afternoon, one and all present here. We are very grateful to gather informative knowledge from you, ma'am. Thank you so much for giving your valuable and precious time to us. Moreover, making us conscious about green chemistry and especially their synthesis. It's an immense pleasure meeting you, ma'am.
Thank you.
We are also thankful to Akal University for giving us such an opportunity to enhance our knowledge on green chemistry. Thank you so much.
Even I'm thankful to Akal University to providing me this opportunity, sir.
Ma'am, we are very grateful while studying here.
Okay, all the best for your future.
Thank you, ma'am.
Anupriya, is there anyone who wants to interact with madam?
A very good afternoon, ma'am. Am I audible?
Yes, audible, please. You're audible to me.
I have a question. So, as you have described about heterocyclic, yes, ma'am. As you have described about heterocyclic synthesis, so question strikes on my mind: can heterocyclic compounds act as nanomaterial from aspect of size or their properties?
Yes, they can act as nanomaterials too. Even many synthetic chemists are pursuing their research on this topic.
Okay.
And we can also use a.
Thank you so much.
Okay. Thank you.
Thank you, Musarat. Now I'm requesting Dr. Naseeb Singh, sir. Please unmute and share your views.
Hello, good afternoon. Hello, good afternoon, everybody.
Good afternoon,
sir. Sir, the lecture on green chemistry, green synthesis of 1,4-diazepine is very informative. I'm thankful to respective organizers for such a virtual conference on green chemistry. which is a recent trend in chemical sciences. Even myself, after submission of PhD thesis at Sri Mata Vaishno Devi University, Katra, has started working in the field of organocatalysis at Guru Nanak Dev University, Amritsar, now at Guru Nanak Dev University, Amritsar, and which is another subfield of green chemistry. Once again, I must thank to Dr. Navjeet Kaur for highlighting useful green-centric approaches for the synthesis of 1,4-benzodiazepines. I also thank to Dr. Bhuvan sir for sharing the conference brochure with me in person. Otherwise, I would have lost the opportunity to enrich my knowledge in the field of green synthesis. So thanks a lot to you, ma'am, and to you, Bhuvan sir.
Thank you, sir.
Thank you, Dr. Nasib. Thank you so much. In future also, we will definitely share all information with you related to any conference. Thank you.
Thank
now,
you so
any
much.
other students? Because our next participants, Jayatitra sir, also waiting for his valuable lecture. So again, we have another 3 minutes. So any participants, if you want to interact, please unmute and share your views. Any other participants? So if you don't have any other questions or queries, then thank you so much, ma'am. You have described many things about like importance of green chemistry, 12 principles of green chemistry, and you have described so lucidly the importance, and then green solvents, green all green credentials, green tools, and then different importance of 1,4-benzodiazepines and synthetic synthesis of structurally diverse 1,4-benzodiazepine derivatives. So with this, thank you so much, ma'am. Thank you so much for your valuable time. Thank you so much.
Thank you, sir.
Now,
Thank you.
okay. Now I'm requesting our next speaker, Professor Jayatitra Rao sir. Jayatitra sir, can you hear me?
Can you hear me?
Yes, sir.
Okay, good afternoon to
Thank
all.
you so much, sir, for giving us this opportunity. Yeah, good afternoon, sir. So to introduce, sir, I want to share some his short CV biodata. Just wait. Give me 1 minute. Yes. Again, on behalf of all the faculty members of Department of Chemistry, Akal University, I'm welcoming you, sir, once again. And Professor Jayatitra Rao, sir, is an eminent scientist now at IICT Hyderabad. Professor Rao did his PhD in 1983, means almost 4 years before my birth, from Department of Organic Chemistry, IIC Bangalore, and then he did several postdocs. One is in Hawaii, USA, and then research associate as 1985 to 1986 at Columbia University. Then he joined IICT Hyderabad R&D Institute in India. Presently, he is emeritus scientist at Fluoroagrochemicals Division. This IICT is a CSIR lab, prestigious CSIR lab, one of the prestigious CSIR lab in India. He received Alexander von Humboldt Fellowship from Germany, and he is visiting scientist of so many universities. And he received so many awards. He is a fellow of Royal Society of Chemistry, London. He is a C. Chem awardee, and then he received other prestigious awards and recognition. And he has published more than uh, 230 publications, and most importantly, he has 80 patents, which is a huge. And he published 7 book chapters, 2 books, and he supervised 45 PhD scholars, and right now 6 PhD students are working under the supervision of Professor Rao. So with these few words, I'm again welcoming you, sir, at this conference. Thank you so much, sir. Now I'm stopping my slide, and you can share your slide. Thank you, sir. Thank you once again.
Thank you, Dr. Wabun, for the kind introduction. I thank the authorities of the Akal University for providing me an opportunity to talk to you, and in particular to Sandeep Kumar and Dr. Bhuvan Chakravarti once again to bring it to you. So today, this in 1 hour, I whatever efforts we have put towards developing a green chemistry will be described to you. Okay. So the first is the acknowledgement, belong to CSIR. Our president is, vice president is the, uh, and then president is the sorry, uh, Prime Minister Modi is the president for our CSIR organization. And I belong to IGNA also, Indo-German Not Contract Association, Alexander von Humboldt Fellow, and then RSC acknowledgement, and of course the IICT, the emblem what I have. So I thank all of you for for the kind introduction and in inviting me to your lecture on green chemistry, seminar, webinar on the lecture chemistry. Okay. So this is the first slide what I have. So I'm lucky to meet this person who is known as George Hammond. He's now no longer. So he visited us when I was doing PhD in 1980 Bangalore, IIC Bangalore. I just picked up what he, gave some kind of a quotation kind of thing. What he says is, we chemists, we go and mix chemicals in the laboratory, and then we get some new chemical. So the moment we get the new chemical, we are excited, we are so thrilled and other thing. And then after that, we characterize it by recording NMR, mass spec, IR, UV, and all. After that, we forget it. What he says is, do not stop at that stage. Take it and then find out the properties of those chemicals. What is that you get by determining the properties of the chemical? These chemicals with good properties can improve our living standards, style of living. We can push forward ourselves. That is the objective what he has. So, and also it's a great inspiration to meet him. He's a very big man in USA, although he looks very simple, and he visited our lab. You can see the laboratory conditions also during that time, 1980s. So it is a fantastic down to earth man, and then highly inspiring. So I keep his photograph always. So this is what we are involved at the IICT. So when you make the molecule to absorb the light, it undergoes polarization or charge transfer within the molecule or zwitterionic excited state, which has implications in biology, vision, phototaxis, photosynthesis. And then it has a, implication, the NIR dyes, NLO compound, non-linear optical compounds, near infrared absorbing dyes, and then organic light emitting diode. This is the coming up field. Organic solar cells and photoresist, fluorescence, all these things we were able to cover, and we published papers in all these areas also. Can you hear people? Can you hear me?
Yes, sir.
Hello?
Yes, sir.
Can you hear me?
Yes, sir,
Yes,
clearly.
sir.
Okay, I continue. So what we did also, we started looking at the structure and scaffold-based new chemical entities. As an organic chemist, we make all kinds of chemicals. So what is the objective in looking? We were able to find out, how the structure and scaffold-based new chemical entities have some importance. So we prepared all these kinds of heterocycles. Still, we are continuing it. What we do after making synthesizing the various heterocycle, We look for bioevaluation. This is another major field. So this enters into the drug discovery kind of thing. So coming back to our topic, what I've given to you to talk to you about our efforts towards developing the green chemistry. So these are other speakers might have given this information also. So if you look at into the website of the American Chemical Society, you get all these 12 principles associated with green chemistry. So what green chemistry says, prevent waste. Whenever you make some chemical, do not waste it. That means you do not throw it into the environment. That is what you say. So it involves, your hard work and then your ideas, all those things are involved. So whenever you make a chemical, do not waste it. That is one. Then you look into the atom economy. This is most important thing. I will tell you further, clearly when I take an example of the Baylis-Hillman reaction. Atom economy. Atom economy means, left side of the atoms must be equal to the right side of the atoms. Number of atoms involved in. You write generally some structures and then put an arrow and then write the product. So atom economy means, number of atoms involved in this starting material must be equal to the product what you generate after conducting a chemical reaction. So it is most important. Then there is no waste involved in this process. Less hazardous synthesis. When you synthesize, you have to make sure that your chemical reaction should not explode. Your chemical reaction should not catch fire. This kind of a thing. You have to make sure. So then you have to read the properties of the chemicals, what you are using it. That's most important thing. Whenever you conduct a reaction, you must read the properties of the chemicals and then accordingly you design your preparation or synthesis or a method what you are trying to develop. That's most important. Design of benign chemicals. So it is once again linked with the hazardous system. So you go for a less hazardous chemicals, easily available starting material. Whenever, whoever teaches you the organic synthesis, they say that the starting material must be available in abundance and cheap. So therefore, you have to go for a benign chemicals. Benign chemicals mean, easily available, less expensive, and then available in kg quantities. Okay, and they are not hazardous. They are not poisonous. Like that. So many things you can put it. Benign solvents and auxiliaries. So benign solvent means nowadays people are avoiding chlorinated solvents. The chlorine containing solvents are being avoided. Why they are being avoided? When you do the reaction and then leave it to the environment, those chlorochemicals or solvents having chlorine, okay, they ended up into the atmosphere and then go and then interact with the ozone layer and then they destroy the ozone layer, thereby the entire earth, the globe will get affected. So that you have a problem. That is being proven beyond doubt. Okay. And then auxiliaries and the other things also, whatever you use, that should all go the same thing. Design for energy efficiency. So, if you take some kind of a solvent or some kind of a chemical, you have to heat it up to 150 to 100 degrees. So if you can reduce that 150 whatever reaction temperature, 150 degrees centigrade reaction temperature to room temperature, okay, that's fantastic. So you have achieved the energy efficiency of the system. That means you are not supplying the excess energy. The minimum required energy is being supplied to conduct the chemical reaction. That is what it means. Use of renewable feedstocks. Renewable feedstock. This is most important. And then you will understand. This is very interesting. Presently, what we have renewable, we don't have any renewable feedstock. We are using petroleum source. We buy crude oil. India buys crude oil, as other countries also using crude oil, and they distill it and give it to you petrol and then diesel, which we use it every day. Okay. Then the other materials associated with the crude oil are the organics like anthracene, benzene, and all. So these are not renewable feedstocks, but we are using it. We have to avoid them. That is what we want to say. So sooner or later, we have to avoid these things. So now we are going for a solar cells. As you can see, the the government of India is more interested in electrical energy. In Delhi also you can see that quite a few stations, charging stations, electrical charging stations are being constructed, and then you can buy a car run by electricity rather than petrol. These things will come. Probably you are young, in another 10 years you will see this also in India. Totally we will be avoiding using a petrol and other, because they are not renewable feedstocks. So what are the renewable feedstocks? I'll tell you very interesting example for you, because you are in Punjab. The farmer in Punjab, what he is doing now during this winter season, they have a lot of stubble in their fields. They just burn it. So why should you burn that stubble? Waste, isn't it? So what we can do, and then now they are they are spraying some chemical, and then removing the stubble in the fields, farm fields. So that is also not good. What you can do with this stubble, take this stubble and then incubate with all kinds of bacteria, go for a R&D, that is research and development, and see whether you can make some valuable chemicals out of it. Ethanol, you can make it. Ethanol is also can be used as a energy source. They are, ethanol is being mixed with petrol and diesel also in other countries. So you can use ethanol. That is known. So someone has to try this. Maybe you are young people, you can become an entrepreneur and find out a process how to convert the stubble available in Punjab and convert that into a useful chemical. This will be very interesting. Something I suppose challenging. Probably quite a few people might be attending. So this will be the feedstock. No, you convert the stubble again. Next year also you get stubble. Okay, like it will be feedstock. Okay, so renewable. It is renewable also. Once you take ethanol, so that converted into carbon dioxide, and carbon dioxide is being fixed with the various feeds. Like whatever rice and then wheat. There it is being fixed. Carbon dioxide fixed and converted into carbohydrates. Photosynthesis. Reduce the derivatives. We have a anxiety to make one compound, then we make all kinds of derivatives. Instead of making all kind of derivatives, you reduce those, making those derivatives. That is also saves. Catalysis. Catalysis, that's also important. Here I mentioned it. Energy efficiency, number 6. Energy efficiency, if you use a catalyst, suitable catalyst, it reduces energy of activation. So you don't have to provide that much of heat energy or any other form of energy to drive a chemical reaction. And also catalysis will also provide you a stereochemistry problems also can be solved using catalysis nowadays. So these catalysis, catalysts may be inorganic in nature, organic in nature. Organic, catalyst, organocatalysis is the recent field where people are using a variety of, organic catalyst. And then design and degradation during the, you have to design it perfectly that you don't get any degradation in the chemicals what you are using it. Okay, that is also important. If you use the degradation, some other chemicals are produced. We don't know their property. So when we leave it to the environment, we'll be in trouble. We don't know what they can create to us, may be useful or harmful. A real-time analysis for pollution prevention. This is most important. Whenever you do it, you have to do it a real-time analysis for pollution prevention. You have to depend on it. So most, this is belong to the industry actually. So because they'll be producing it in chemicals, tons and tons. So they will be, associated with this kind of a problems. Inherently benign chemistry for accident prevention. These are the most important. Whenever you conduct a chemical reaction, you have to make sure that there is no accident. So you study the properties of the chemicals what you use, and then when you mix it also you have to understand it doesn't lead to the prevention. I'll give you an example. When you people might be doing the bitter lithium reactions. Okay, the bitter lithium or organo aluminium chemicals which you are using it. So bitter lithium, the moment you expose it to moisture and then oxygen, it catches fire and it creates a sound also. So you have to be very careful when you are using bitter lithium. So you should not expose it to moisture. You should not expose it to oxygen. You should not expose it to higher temperatures. What happens? There will be, heat, light, sound, and then explosion together. Put together, you will have. So you have to be careful in doing. These are all, associated. There may be some more also. You can go through it and then learn it from that. This is another interesting thing. How do you define green chemistry? There are several definitions available, okay? And then, you know, you can define it as you like. You can give your own, but I just put it for you something, 6 types of definitions. Design and implementation of chemical products and processes that reduce or eliminate the use and generation of hazardous substance, as we discussed in the last slide. So you have to understand the hazardous substances and eliminate them, using them, and then, generation, all these things you have to understand. So that will lead to the green chemistry. That's what. Must adopt nature chemistry using renewable. As I said, Punjab produces stubble. You take the stubble and convert into useful, kind of thing. So you have the sugar also. From sugar, you can make it, furon. Furfural, you can make it. Furfural will be a feedstock material. So you can convert the furfural into various things where it is available, and it is cheap also. Okay. So like that renewable feedstock, that is biodegradable materials, once again, do not persist in the environment. They don't persist in the environment. That is the important thing. Green chemistry uses catalysis. I already mentioned catalyst can be biocatalysis to improve efficiency, conduct reactions at low and ambient temperature. It's a kind of you can define it. So the chemistry which is involved using catalysts and biocatalysts will lead to the green chemistry. Green chemistry is a proven systems approach. Nature is adopted. So without wasting energy efficiency and then, environmentally benign. So we just approach nature, learn from nature, and then what is that, system it has generated, understand the system and then implement it. That will be another approach. Okay, I'm sorry. Green chemistry offers a strategic path to build a sustainable future. Why we should do it? Because the green chemistry provides you a sustainable future. It doesn't, provide you, environment getting affected or hazardous chemical and then, all kinds of things can be avoided. So it gives you a sustainable future. For our grandchildren, this, earth will be more suitable to live longer. So we leave something for our grandchildren also without disturbing, environment, and then developing a green and clean chemistry. That is the objective. Okay. Coming to the chemistry now, a Baylis-Hillman reaction. So what it involves an aldehyde, preferably, and then, like this acrylates, a double bond carrying electron withdrawing group, and in the presence of tertiary amine, okay, which is acting as a catalyst, organocatalyst, which gives you this kind of a derivative, which is called Baylis-Hillman effect. Okay. Where if you take X is equal to oxygen, it becomes a hydroxy group, and then you have electron withdrawing, that could be a methyl carboxylate, and then methyl ester or ethyl ester, or a nitrile also it is possible. And you have a double bond. What is happening here is a carbon-carbon bond is formed. Okay. So it is a carbon-carbon bond forming generation. Why it is so important? It is very, very, benign and then environmentally safe, atom economy. If you look at into the, equation left-hand side, you have this aldehyde and you have this. Put together, it gives you this. There's no other materials also. Okay. That is the most important thing. So you get it this. That's why it is called atom economy. So all the atoms of left-hand side are being, holding in the right-hand side. Okay. So another thing, the tertiary amine, what we use is the DAPCO. Okay, here it is. So that is being regenerated. So DAPCO is water soluble. You can wash the reaction mixture with the water, and then when you evaporate the water, you get the DAPCO back. That means a catalyst which is being regenerated and can be reused. So that is the advantage. You don't have any waste generated in this reaction, and the mechanism is given something like that. You people can approach and then read something. X is equal to several groups are also given here. R is equal to alkyl, hetero, alkyl, all kinds of things are involved. So this is the one reaction which we used it extensively. Okay, and then prepared all kinds of chemicals, new chemical entities having anti-diabetic activity, okay, anti-cancer, and then insecticidal property, antimicrobial property, anti-inflammatory activity, and then antifungal activity, and then anti-malarial activity, antidepressant activity, and platelet aggregation. This is if you have a coronary disease, okay, heart disease, CV, coronary vascular, whatever, okay, this can be used in that. That also be prepared. So this has a very, very important reaction, because many people are working in India. Quite a few people are also working on this Baylis-Hillman chemistry, and then we published a review also in Tetrahedron letters. This is the various synthetic methods which we develop. Also, it gives you this, several things, the pyridones, and then you have quinolines, and then pyridines, tetrasubstituted pyridines, and then fused pyridones, and then this Baylis-Hillman adduct chlorination, and then you have a lactone, plenty of things, aminopyridines, you have it like that, quinoline, and then chloro oxindole, and then this is quinoline derivative also, Baylis-Hillman adduct quinoline derivative. So several things which we have developed, several methods, and published it. Okay, Baylis-Hillman reaction. What is this? How do you say that it is a green and clean reaction? So you use ethyl acrylate, a reagent and solvent, right? You should make sure that you use a sufficient amount, not excess to sufficient amount. You have to use it. It could be either acrylonitrile or methyl acrylate generally. And then you have aldehyde. Okay, you mix it with DAPCO. That means you are not using any solvent. That is very, very clear. So if you are not using solvent, excellent. So it comes under green chemistry kind of thing. So let's look into it further a little bit. We are using this as a solvent, as well as not in excess, as a limited amount of solvent. Okay, and also a reagent. And then after the reaction, you get this Baylis-Hillman adduct. Okay, ethyl acrylate, whatever we use excess, is completely recoverable. You can recover it. Okay. After the reaction, what you do is you just wash it with sufficient amount of water, such that you can remove the DAPCO. So DAPCO comes into water, and then you can remove the water. You get the DAPCO, which can be reusable, and then recovered and reused. So DAPCO is water soluble and recoverable, and then reusable. Okay. It is an organocatalyst also, this DAPCO. What is that? And then what you do is, after washing with water, you have the excess of this ethyl acrylate or methyl acrylate or acrylonitrile, whatever you use it, that you can easily distill off. The boiling point of that is very, very, below 100. You can distill it off and recover it completely. No waste. So whatever the product remains will be the Baylis-Hillman adduct, which you can use it. It's almost 96% pure. You will get it. 96% pure about. So this is the very clean and green reaction in terms of it. The most important thing is this Baylis-Hillman adduct, where you have a hydroxy group, a double bond, and then ester group, and then or if it is aromatic, that is also. So it is a densely functionalized molecule or product, which is the Baylis-Hillman adduct. So you can do variety of chemical transformation. If you have a hydroxy, you can convert that into chloro. If you have a hydroxy, convert that into a keto group. If you have a double bond, you can make the epoxide, or if you have a you can conduct a Michael addition, because you have alpha-beta unsaturated ester here. You have an ester that you can be reduced into alcohol, can be reduced into aldehyde. Many chemical transformations can be conducted using this densely functionalized Baylis-Hillman adduct. That is the advantage here. That means you can open up variety of chemistries possible using this Baylis-Hillman adduct. Okay. Okay, and what we did is we published this paper making the chloronicotinaldehydes. Okay, how we can say that it is a green reaction, I will tell you. So you can make the enamides, very simple. Okay, right, and then you treat with POCl3-DMF. POCl3-DMF is known as a Wilsmeyer-Hack reagent. When we do the POCl3-DMF reaction, you get the product. It's around 60 to 70% yield of this chloronicotinol, substituted chloronicotinaldehyde. You get it. Okay. So again, when you use POCl3, these phosphate salts will be there in the reaction. crude reaction product, what you have it. So you have to remove them. And then the DMF will also be there if you are using excess. Okay. Now what we did is we replaced this POCl3 with diphosgene or trifosgene. Because the diphosgene, we developed a process. I will tell you, further in the next few slides, I will explain it, how we have prepared the diphosgene. So you use diphosgene and then DMF. When you mix diphosgene and DMF, you can generate the Wills-Meyer-Hack reagent. Next slide will give you the mechanism also. And then that will give you the product in a fantastic yields. Over 96% you get it. So we were able to, hike the yield from 60, 70 to 96% yield using diphosgene. Another advantage of the diphosgene is it doesn't leave any kind of inorganic salts in the reaction medium. Because the diphosgene, when it reacts with DMF, it ejects carbon dioxide, which is a green gas. It goes into the environment, and then it is recyclable, get converted into, again, by photosynthesis, it will be fixed in the plants. So there is no problem with that, greenhouse gas. So basically the reaction medium will be very clean. So therefore you have something like 96% yield of this chloronicotinaldehyde. Trifosgene also can be used. So the reason why we have gone for diphosgene and trifosgene is they are safe. See, people have reported using phosgene also. Okay, phosgene is highly poisonous. So we should not use hazardous. Even diphosgene is also to an extent hazardous, but it is easily handleable, and then you can buy them. Like POCl3, you purchase it from a chemical vendor nearby. Like that diphosgene and trifosgene also, you can buy it from a chemical vendor. So they are safe chemicals, not that poisonous completely, but hazardous chemicals definitely, not poisonous. So you can use it and then get the reaction. So we have several, enamides prepared, 11, 12 enamides, and then we get all these corresponding chloronicotinaldehyde. So what is the advantage? The phosphates are being eliminated. Of course, yields are 96%, and phosphate salts, inorganic phosphate salts are eliminated. Carbon dioxide is being left to the environment. Ease of workup, because there is no, salts and other thing, it becomes easy. Once you have a 96%, workup becomes easy. Tetrasubstituted pyridine is being produced. So these are the various advantages. So it is a green, towards the approach. So it's to an extent, whatever possible, it's a green and clean reaction. That's what we report. Oh, here it is given, we published it in Tetrahedron 2006. Okay. The mechanism is also very important. I'm showing it to you. When you mix POCl3 and DMF, dimethyl formamide, so you get this Wills-Meyer reagent. Okay. So this Wills-Meyer reagent will react with the enamide and gives you imine, which, proton migration gives you bisenamine. Okay. When bisenamine is reacted with Wills-Meyer reagent, another mole, you get this monoformylated bisenamine. Okay. If it reacts at a different position, you get monoformylated bisenamine, right? So this monoformylated reacts with another molecule of the Wills-Meyer reagent, another mole of reagent, whatever Wills-Meyer reagent, will give you diformylated bisenamine. So this is the intermediate which forms, and then which undergoes a deep-seated rearrangement, and then finally it undergoes hydrolysis to get you the chloronicotinaldehyde. So the mechanism is complex. Reason is very, very simple. There are so many bonds forming and bonds breaking. So it is very interesting to write the mechanism. That's what we understand. And then we were able to give you a reasonably good mechanism. And all mechanisms are all debatable also. Okay. After making these chloronicotinaldehydes, now the next slide, you will see it. Okay. When you take this, aldehydes and then do a Wills-Meyer reaction at room temperature using DAPCO, it forms a very similar reactant, but it takes 2 days, 4 days, 18 hours, 20 days, and the yields are in this range. Okay. And then if you take R is equal to, alkyl, okay, and then you do the same reaction. You have 7 days, 9 days, 13 days, 13 weeks, 20 hours, and 48 hours. The conditions are so different in all these cases. That's why they are reporting at this. Okay, never mind. So it's a report. That means, we require to reduce the time and as well as the yield. So what are the factors contributing to this yield and time of the reaction. So when we prepared this chloronicotinaldehydes, as earlier slide I've shown you, and then we conducted a Bailey-Silman reaction, okay? Within 4 to 5 minutes, you get 100% of this. That is, mixing of the reagents or the delay, that's what I feel, okay, when we did the reaction. So you get it. So this is without solvent. We are not using it, just mixing one to this chloronicotinaldehyde and then ethyl acrylate or methyl acrylate or acrylonitrile and then adding Dabco and stirring it. So you get it this. And then you take the chloronicotinaldehyde and then use the acrylonitrile methanol, you use it 5 ml. So without this also, within 10 minutes, you are able to get 99% of this yield. This is fantastic. You save the time compared to this days and weeks of this reaction, hours, days and weeks, we were able to do it within no time, 10 minutes maximum. So this is, so what is the contributing factor here? What we reported in this paper is that the bulk polarity of the medium, okay, whatever the bulk polarity of the medium we are using to conduct the reaction has a role to play. That is what we see. Okay, we can see what way it is, green and clean reaction. Ethyl acrylate, reagent and solvent. No, we are not using any solvent, so the ethyl acrylate becomes reagent and solvent. Ethyl acrylate is completely recoverable. Dabco, organocatalyst, okay, and then we are using catalyst. And DAPCO is a water soluble and recoverable. We can recover it water soluble because atom economy is being maintained. Densely functionalized product, that is the bonus. No solvent, time of reaction. All these things contribute to the improvement in the chemistry. So they get into the domain of green chemistry, green and clean chemistry. I'm sorry. So this is what happens when you plan properly. We can do it. There is one more problem also we noticed when we use ethyl acrylate or methyl acrylate. When we use a little bit excess and then longer reaction times, this ethyl acrylate or methyl acrylate, acrylonitrile, they undergo dimerization, and then we get dimers of this because of the Dabco catalyzed reactions. So self-condensation, self-CC bond formation, that is one. So we have to use optimum amount of the solvent. If we use excess, then you have another pathway open up where we, creating some new chemical, which is not good, which, doesn't fall into the category of green and clean chemistry. That's what we have to do it. Okay, another thing what we did, so people have reported that the aldehydes do not react with the cyclopentanone and then cyclohexanone. And also they mentioned that even if they react with this and forms a Bailey-Silman adduct, they are not stable. Okay, that's what they reported. Then what we did after reading that paper, we thought that we should try with our nicotinaldehydes, or even this quinoline, chloroquinoline aldehydes also. So accordingly, we conducted the reaction. So we get over 98%, okay? Little bit of aqueous methanol. So it is stable, and then we got the crystal structure for the two chemicals, two Bailey-Silman adducts. Even this also forms this chloroquinoline aldehyde also. Now the student has to improve it, but the student left. We could not do further much on these activities. So we can easily improve this time as well as yield of the reaction, avoid solvent also. Okay, that is the limitation in this. So what we would like to say here is these whatever adducts involving cyclopentanone and cyclohexanone, they also form Bailey-Silman adduct, and they are perfectly stable. And then we were able to get the crystal structure for the couple of Bailey-Silman adducts. Okay. Then what we did is chlorination of Bailey-Silman adducts. How do we do it? There people were doing chlorination and then using several reagents. Okay. So what we did, as I told earlier, we were using trifosgene and diphosgene. Okay. So we use that pyridine as the catalyst and dichloromethane as a solvent. We're able to get this and this. Where you use it acrylonitrile, this becomes minor and this becomes major. So here this becomes major and this becomes major in the case of nitrite. So We have this. We published that. The interesting part of this thing, when you use nitrile, you have a different stereochemistry compared to the ester. That is the most important thing. So how do you analyze it? So here we used a GC. We employed a GC, gas chromatography. Okay, that is this best analytical tool, and measured these two, and then we recorded the NMR also. Earlier people also reported that they give this based on the HNMR, so they were able to find out the isomers based on the difference in proton NMR. So we used proton NMR, carbon 13, and as well as the GC. So all the three we use because we need it. Whenever we convert this into a chloride, we required to know the stereochemistry of the double bond. That became essential. So we had to do the analysis. So we were able to do it and develop this procedure also. And then aldose reductase. Okay, what is that? We were able to make, here is the chemistry sequence. So you have an aldehyde, reacts with the acrylonitrile, gives you this Bailey-Silman react, and then you convert that into a cyanoaldehyde using ionic liquid with sodium nitrite at 80 degrees, you get this aldehyde, cyanoaldehyde. Then you take the cyanoaldehyde and condense with the rhodonine. So you get the rhodonine derivative of the Bailey-Silman, modified Bailey-Silman react. Okay. So these compounds are closer to the drug which is being marketed, which is known as eperlistat. It is here written, eperlistat. This is the only drug is used for, what you call it, activity, it is the neuropathy, diabetic neuropathy. What is diabetic neuropathy? When you have the sugar in your body or in the blood, what happens? The excess of sugar will get converted into glucose, into sorbitol in the presence of aldose reductase, and then that sorbitol again it converted into fructose. Okay, when this sorbitol is converted, okay, that has a blood-brain barrier different level, and it goes and binds into the brain. Once it binds the brain, you have a problem. So you are, you'll have all kinds of neurological problems. We cannot say anything what is going to happen. This is very, very dangerous. So that stage one should not get it. So to arrest this sorbitol formation, what we use, you can use this eperlistat drug, and then aldase inhibit the aldose reductase enzyme. Okay, once it inhibits, the glucose will not get converted into sorbitol. Okay, that is the idea. So this is a therapeutic use. So what we thought is this eperlistat analogs can be prepared as given in this equation. We prepared all kinds of analogs, okay, and then studied their inhibition property with respect to aldose reductase. Okay, when it binds with the aldose reductase, it inhibits the formation of sorbitol. That is the thing. So this has a therapeutic importance. So we conducted several tests for over 39 compounds, okay, and then looked for the aldose reductase inhibition. They are found to be a couple of things, better than the targeted molecule. I mean, marketed molecule like eperlistat. We have a couple of them. 5 compounds were found to active compared to the standard drug eperlistat. We always compare with the standard drug eperlistat which is in the market. Binding activity was given and revealed by molecular docking. We did the docking studies also. The essence of this is you can convert the Bailey-Silman adduct into eperlistat and go in a relatively green and clean reaction. Okay, that is what we would like to. Here, ionic liquids, you can recover it. Sodium nitrite is a inorganic compound, we can recover it or put it into whatever. Rhodonine, it is a condensation reaction, very high yield you get it. Ammonium acetate, acetic acid, they're all recoverable definitely. Okay, that is the to an extent I can say that it can enter into the green chemistry domain. It is possible with some more modifications and other things. We can put it into the green and clean reaction, right? And then we prepared the tetrazoles. So tetrazoles are found to be, the sartans. The sartans are blood pressure, whatever. So what we did is, people are using, these are all the drugs, medicines available to buy and then reduce the blood pressure of a given patient. So it has a therapeutic value. So what we did here, the chemistry using the Bailey-Silmanite, acetate is formed. Acetate is formed and then treated with azide, get a good yield of these, and then reduce the azide with using zinc and acetic acid, and then you get 4. Okay. There is something it is missing, which I cannot see it. Okay. The amine, what you get it is treated. This amine found to be, a little bit highly reactive. So the moment we prepared it, immediately we used it using azide. So azide will add up here to give you this tetrazole, azide and then formaldehyde. That reaction gives you tetrazole. These tetrazoles have a medicinal properties. That is what we found out. So this is the sequence. Okay. So when we use nitride, you have a different stereochemistry and then convert that into a tetrazole. So we pumped in various kind of thing, and then we studied the anti-cancer properties of these molecules. We got the crystal structure. So, and then here this UV spectrum also we tried. We took the COF thymus DNA and then dissolved it in a buffer and then added these tetrazoles. Okay. When we add the tetrazole, it goes and binds with the DMA, and then there is a change in its absorption. You can see it clearly. If you increase the concentration, there is an increase in the absorption. That means it is binding to the DNA and changing its double helical structure. Once it binds with the DNA, there will be, loose, the helical tight helices. The 2 helices will get loosened, and then that is responsible for increasing the absorption, what we have observed. So there is a change in the supramolecular structure. See that double helix DNA is known as supramolecular structure or a supramolecular assembly, whatever. Okay. So that can be easily studied using this. So we have the binding site also. Okay. What we want to say is the chemicals involved in all these steps, they are very simple, easily available. Okay. Acetyl chloride here, Bailey-Silmanite, you know it very well. Acetyl chloride, you can use it, acetate, that is also very simple. And then azide, which is also simple chemical, we throw away chemical, where is available, probably, something like 300 rupees a kg, you can buy it, sodium azide. And then reduction, zinc and acetic acid. Acetic acid is cheap, zinc is also cheap. And then again, you use sodium azide and formaldehyde. That is also, formaldehyde is also cheap chemical. Formalin, you can make this very simple. So it is involves very simple chemical. Thereby we say that it is a green and clean reaction. It may not be clean because of all these, zinc acetic acid and azide. Azide is dangerous, known to be explosive nature. When azide mixes with heavy metal like lead or mercury, it has an explosive properties. So we have to be careful in that. But we have used it as a cheap chemical. Okay. So we have developed some processes at IICT also. So let's see how green and clean they are. They are perfectly green and clean. Why they are perfectly clean? Is a methyl chloroformate, MCF, and then which reacts with the chlorine, okay, in the presence of light, visible radiation, and chlorine radical is generated, and that replaces it to CMCF. That is chloromethyl chloroformate. That, and then HCl, you get it. So here, what we are doing, methyl chloroformate is a liquid, okay, and then CMCF, chloromethyl chloroformate, that is also a liquid, okay, but it is a higher boiling point than methyl chloroformate, no problem. Chlorine is a gas, so easily you can, HCl is a gas. So the chlorine and HCl, you can drive out. Its chlorine presence will be very, very less. HCl presence also will be very less. Maybe it is, a little bit more compared to chlorine, but by bubbling nitrogen, you can drive out the HCl and chlorine out of the reaction medium. And then you have a 98% selectivity. You can isolate these things by distillation, simple distillation. So there is no loss of any chemical. There is nothing like, unwanted chemicals are formed. You have a very good stoichiometry, and then you have formed a very high yield and then very high selectivity also. So what we can do is we can stop the reaction at 95, 96% stage and then distill it off so that you don't get the corresponding dichloro derivative. So you can monitor the reaction by GC, no problem. You can do further another analysis also No problem. So it's a clean and clean process, which we have conducted it, something like a 2 to 3 kg level. A reactor was designed at IICD, and then we were able to make the CMCF. Not only CMCF, next stage is, you convert the MCF into chlorine, diphosgene, which is this tetrachloro derivative. Okay. So you fertilize it in the presence of chlorine and then MCF. You get this and corresponding HCl. HCl gas is, constantly ejected from the reaction medium when the chlorine enters into the reaction medium and then, reacts and gives you HCl. You can trap the HCl and make the bottle grade HCl also. You can sell it. There is no waste on the thing. And then, you have a diphosgene, which is also a liquid. So diphosgene is also high boiling point. You can distill it off. Okay. Compared to MCF, this is still high boiling point. So there is no problem in isolating it. You can distillation. So this is a dead end reaction. That is a complete chlorination you are taking place. Therefore, you don't have to worry about the selectivity in this case. Whereas in this monochlorination, you do have a selectivity. You have to worry about it. You have to monitor the reaction time to time to find out 90 or 92, 95% conversion and then stop it and distill it. Whereas in the case of diphosgene, you still have, dead end reaction, that is complete chlorination you are doing it. So you can monitor the reaction by GC also, and then, you can distill it off and isolate it. We were able to do something like 3 to 4 kg, diphosgene, we were able to distill it IICT and then use it for various reactions. And then this is the tertiary butyl. I must tell you here this diphosgene and then triphosgene, you will get it by putting it in a dimethyl carbonate. If you use a dimethyl carbonate, replace the chlorine with methoxy group, okay, then it becomes a dimethyl carbonate, and then you can do the chlorination in the same way. There you have a 6 chlorines as being added. So this is the process. It is, the triphosgene is more safe compared to diphosgene, and it is a solid also. Solid is easy to use, and then it is being produced by Excel Industries in India, but now they stopped it because they were buying it from China. Now there is a problem with the China. So again, I'm sure they are going to restart. That's what I hear. They are going to make the triphosgene. Okay, these are all cheap chemicals. You can buy them. Okay. That is what I would like to say here. Next reaction is what we tried at IICT is the tertiary butyl toluene. This is, a process. We were asked to conduct trial runs for this. This benzyl chloride, tertiary butyl benzyl chloride, okay, this has an application in agarbatti, that incense sticks, and then wood, you call it, there that is being used. Okay, so you convert that into another alkoxy derivative, so which has a good what you call it, sublimation property, and then it has a fragrance property also. So we use that kind of thing. So the problem what you have here is it can go to benzoic side or it can go to this alkyl side also. Okay. So both possibilities are there. So how do you control the selectivity? And at the same time, you should not see that the dichlorination and trichlorination is going on. So it is a little bit more complicated. We were able to peg it really in a very fine way. So we reduced the temperature and then conducted the reaction, where we have to stop it at 50% conversion, 55% conversion, and then you have to do online monitoring, and then you get this, you distill it up. Because of the difference in boiling point, you can easily distill it. So here also you have a 98% selectivity, you have it. So these are the higher boiling TBT chloride. That's what. HCl gas, you can take the HCl gas and trap it and convert that into a HCl, hydrochloric acid, and bottle it and sell it. There is no wastage in this. So the next one is, this is the deep-seated rearrangement where, we were studied. We were using, as I mentioned, we were using the Bailey-Silman reaction. So this is the Bailey-Silman reaction. When that is mixed with oxone, oxone is a peroxide, inorganic peroxide, it is a triple salt. Okay, oxone is an inorganic triple salt. So, and then sodium chloride, water, acetonitrile. So the water and acetonitrile is, benign solvents, green and clean chemistry stands for. Oxone is an inorganic compound. Sodium chloride is also inorganic compound, and water soluble, you can get rid of it. So this is the Bailey-Silman adduct, which is treated with these. at room temperature to 50 degrees stirring, you get a deep seated rearrangement. And we have 24 examples, over 80 to 98% yields are reported. This is a very good synthome. Okay, we were able to convert this, whatever Bailey cinnamon and left, further by adding a stereochemistry as well as functional group attached to this. So we have improved its synthone capabilities. That's what we believe in. So this we published in green chemistry also. So as per the whether it is related with the green chemistry or not, yes, it is related. Easy workup. So oxone, sodium chloride, and all these things get into water. So you put it in a solvent and then wash it with water. All these things can be removed. The only product will be in the organic solvent, and then you solvent, you distill it off, you get the work product. That is also possible. Or you can wash it with water, and then if you do it in a higher scale, this will be easily taken into that. Or you can do a continuous extraction also, like something similar to the succinate extraction you might have heard. Like that, liquid extractions also can be done to take it. That is another application of industrial aspects, that you can make it in a tons and kgs of levels also, it is possible. So we were able to do the reaction at a 5 to 10 gram scale. That is what we reported. 5 to 10 gram scale, easily you can do it. Another green reaction, this is the vitamin A, Wittig reaction. The objective of this is to, can we make in India a vitamin A industrially feasible? That is the question. So we were able to prove that we have the developed process and it is feasible in India, and we can make it industrially. Why we should make it industrially? If someone says tomorrow, puts sanctions, America and then Europe, this Japan, they are famous for putting sanctions. Sanctions mean they will not allow trade between these countries and India. That is what happened. Now India is favorable, no doubt. But earlier, during the Vajpayee's tenure as a prime minister, he went to the Rajasthan and then conducted a nuclear reaction, underground nuclear reaction. That time, the US and then Europe and Japan, they put a lot of sanctions on India. So that time, India decided to go for making this process. Why it should be prepared? Because this vitamin A acetate is very much essential. It is being added in poultry feed, it is being added in cattle feed, and it is useful for human consumption also. Those who have a problem with the eyesight and other things. So it is very, very important. Imagine, how much of poultry feed and cattle feed we are using in India. Okay, so it requires tons and tons and fatty. So it has become a strategic chemical, honestly speaking. So they gave that. So the Wittig reaction, when you convert, you get all trans and then 11 cis, 2 isomers you get it in the Wittig reaction. Okay, then you have a problem of converting this 11 cis isomer into all trans, because all trans is required for human feed and then cattle feed and then poultry feed. So how do you convert that? So we developed a process. So photochemical process. So what we did, we took it in the solvent and photocatalyst and irradiated it 500 nanometers, filter, through filter we use it, and then you can have solvent recovery, and then everything is this. So what we are doing, we are using minimum solvent. Photocatalyst, it is a photocatalyst, a molecule, organic molecule, dye molecule, it attached to a polymer bead. So that polymer bead is not soluble in any solvent. So it is a heterogeneous photocatalysis. If you filter it, you can recover the photocatalyst. If you distill it, you can recover the solvent. There is no loss in that. So we have got these conditions, prepared. So what is the mechanism? It's a quantum chain mechanism. That's what we propose. Photocatalyst absorbs light above 500 nanometers. Why above 500 nanometers? Because the vitamin A, which absorbs light around 330, 340 nanometers. So we should avoid that absorption of the light by the vitamin A molecule. So therefore, we have put filters, light filters, which blocks the radiation below 500 nanometers and then allows only above 500 nanometers. The photocatalyst, which absorbs the light around 540, 550 nanometers, that the dye molecule, red dye molecule. So when it absorbs the light, it gets into singlet and then it gets into the triplet state. Okay, that triplet photocatalyst interacts with the 11-cis isomer and then transfers energy to convert into 11-cis triplet. Okay, this 11-cis triplet get converted into all trans, but this conversion happens in the excited state, in the excited domain, excited state domain. So the all trans triplet form, it reacts another 11-cis molecule and transfers energy to give 11-cis triplet state. So, this is called a chain reaction initiated by this. So this is the concentration dependent. So we are using something like, 75% of vitamin A. That's very, very high concentration. We add a solvent to reduce the viscosity of the reaction medium. That is the purpose of adding. Otherwise, you can conduct a clean reaction also. Because the high viscosity of the vitamin A acetate, we had to use some solvent to mull it. So that's why. So, when you have you might have heard about the radical chain mechanism, where the radical is involved and that creates a chain. Here, excited state, which is equal to quanta, is involved for carrying, chain reaction. So it is called quantum chain mechanism. And then another problem what we, solved in the IICT is that with respect to this thing is you get triphenyl phosphine oxide as a byproduct in the Wittig reaction. What to do with that? Suppose if we conduct a reaction in 1 ton level, that equivalent of triphenyl phosphine oxide is generated. So we cannot throw it into environment. People don't like it, and then you will be fined, penalized, maybe jailed also because of the laws what we have in India. So what we did, we took the triphenyl phosphine oxide, mixed with diphosphine or triphosphine. So it gives you this triphenyl phosphine dichloride. It gives. Okay, it's a clean and green reaction, absolutely. So when diphosphine and triphosphine reacts with this, then that it gets converted into carbon dioxide, and then chlorine, will be attached to phosphorus. So you get triphenyl phosphine dichloride. In the same pot, you can add red phosphorus, okay, and then heat it up. You get triphenyl phosphine, and then the phosphorus will pick up this chlorine. That means the reduction it goes, and then you get PCl3, phosphorus trichloride. So you can easily distill it out. Whatever remaining in the reaction vessel must be triphenyl phosphine. So what we did is we were able to convert the triphenyl phosphine, okay, and then reuse it, recycling and reuse it. Both the things we have a patent of this also. So the another reaction we is the iodoxybenzoic acid. Am I taking more time? I hope another 5 minutes I can continue. Hydroxybenzoic acid.
You can take 30 minutes also, no problem.
Okay, then I will complete all my slides. I'm close to completion. Okay, you take the Bayes-Hillman adduct and then mix with acetonitrile, the green solvent, I believe, IBA, hydroxybenzoic acid, and an oxone you can eat. What this oxone do it? It's again triple salt. It gets converted into IBA into IBAX as it's shown here. So the IBAX, where iodine is in the oxidation state, 5 oxidation state plus 5. So this is more reactive. Whereas in hydroxybenzoic acid, this is in the oxidation state of plus 3. So plus 5 is more reactive. So we are generating plus 5 in situ. Okay, IBAX. That is what the oxone role is. Oxone is an inorganic triple salt, water soluble. That is what. When you use this IBAX, this hydroxy is get converted to ketone. So what we did here is we have conversion of hydroxy to ketone. Why it is required? There is a method was lagging behind. Then no one tried. Several people tried, but that was not a clean green reaction. Whereas what we conducted is found to be clean and green reaction. IBA is an organocatalyst. Yes, the moment you say that you are using a catalyst, it's a green reaction. Oxone is a triple salt, so you can remove it. That is also green category. Recyclable catalyst, okay, you can recycle it again, recover and recycle it. Filter to get catalyst after the reaction because it's heterogeneous, so you can filter it. Recyclable, easy workup, high yield, highly functional product. This is what. So it's a green and clean reaction. That's what we believe. So you have again indole carbaldehyde. Okay, indole carbaldehyde mixed with oxone and sodium chloride in water and acetonitrile with a 1:1 ratio and heated to 50 degrees. So what you get? Chlorooxindole, you get it. Okay. If you use excess of oxone, okay, you get isatin also. You can stop the reaction very well in this. That is what we did it. When we use excess, 1 mole equivalent higher than what is required, then you get the esatin also. So it is the same thing when you use sodium bromide or sodium chloride. Sodium chloride gives you sodium bromide, you get a bromo derivative. So certain reactions, if you are not, you know, cannot be carried out with the chloro, with the bromo it is carried out easily. That is the notion what we have in organic chemistry. So we put the sodium bromide and convert that into bromo oxindole. So you can easily do that reactions also. A substitution at the bromo position, this position also. Okay. And here also, if you use XR, you will have the, you know, esatin derivatives coming up in this. So several examples we have cited on this, and then we believe it is a clean and green reaction because, you know, you have all these conditions and other things, very ambient. So then, you know, we looked into the coumarin also. You take the coumarin, oxone, and sodium chloride, you get here only, you have a fantastic regioselectivity. The chlorination or the bromination goes only to this position. It doesn't go anywhere also. That is what we have observed, okay, at 50 degrees. These also conditions you can make it. And then when you make this, okay, when you block this position, if the chlorination, bromination occurs into the side chain, and then you get a phenacyl bromide or phenacyl chloride type of derivatives. So that is also we observed. That means, you know, this is the selectivity is also important. This is the selectivity under green and clean, you know, reaction conditions. Oxone, inorganic, same thing, it is repeated. Sodium chloride and sodium bromide, it's a salt, which is solvent, water, okay. Easy workup, high yield, high selectivity, and higher functionalized product. So the functionalized product is higher. What to do with the coumarins? Coumarins have, you know, been used in the literature and they have several applications. We believe this method will help us further. So the variety of the coumarin derivatives which we reported will have an impact on, you know, making other chemicals using this procedure. Okay, this is another important thing. When you take the chlorine and, you know, aniline and then chlorinate it, it doesn't give you the selectivity. Whereas if you convert that into an aniline, N-acetyl aniline, okay, and then do oxone, sodium chloride, water, you know, under these conditions, okay, you get very high selectivity. That is only, you know, orthochlorination it goes. You take same sodium chloride, you get orthochlorination it goes. Where now you are using benzamide, that is the benzoyl chloride, you are using it and attaching it to amino group of, you know, nitrogen of the amino group, right? You can use sulfonine chloride and you can make this sulfonamide and do the same reaction. So under these whatever groups, we were able to see the very high selectivity of orthochlorination. That is most important. People are trying with palladium and then so many metal complexes, metals, and then using all complex reaction mechanism. There also you are not getting completely 100%. There are people have published in Angawande Chemi also using palladium and other things. We were able to do it in a very, very simple way to get this. And then, you know, easy workup, high yield, complete selectivity, you do have it. What is the mechanism of this? Okay, we were trying to do it. This is the oxone peroxide, okay, link. When you heat it up, you get the sulfate radical and hydroxy radical. Hydroxy radical is more powerful. That reacts with the chloride and gives you chlorine atom and then hydroxide ion. This sulfate radical, okay, it picks up hydrogen from the attached with the nitrogen, okay, it provides you N radical. That N radical reacts with the chlorine radical generated by the hydroxy radical pathway and gives you N chloro derivative. This N chloro derivative, which is the stability is accountable, so that quickly, you know, rearranges and then migrates to the ortho position. Thereby, you observe the highest ortho selectivity. That is what we propose in the mechanism. Okay, this is what we believe. Okay, this is end of my talk. So I thank all my students who are all in there. There are 47% of students completed their PhD. There 5 more are remaining. And then he is submitted, Lakshmi Reddy submitted, is Umashankar submitted, and then Madhu is writing, Himabindu is still writing, and MVL and Raji is also going to submit. So, you know, 52 students, and then thank all my students, and then master students, the list is big, so I stopped at 51. I thank the director, IICT, Dr. S. Chandrasekhar, and I, you know, these are all some photographs of my students. quite a few guys are good. Then he's a entrepreneur. He holds an industry. He has around 400, 500 people working for him now. And he's another entrepreneur. He has a small industry. He has 10 to 12 people working for him. And he is in the USA. He has a small analytical laboratory in USA. He's also entrepreneur there. He's opened up. And the remaining people are all, settled in industry and other people. He is at Kurukshetra, NIT Kurukshetra. He's a professor there, C.H. Prabhakar, and he's at Andhra, Guntur. This guy is assistant professor, and some more people are here, collaborators. And then he's my PhD teacher, Ramamurthy. Presently, he's working in Miami, and in this, there are few people. He is also another entrepreneur who has a lab, MVLN Raju, Mantina Venkata Neeladri Raju, who is, has 10 people working for him. He is yet to write the thesis, although he completed his PhD work 3-4 years back, and then he said he want to start a small industry, and then he struggled. Now he has established it, and then he has 10 to 12 guys working for him, and then he is writing the thesis. And these are all the people who have completed their PhD and they are working. He is at NIPER Guwahati. He is Jagdish Kumar. Okay, NIPER working for NIPER, and then he is working for ISER Tirupati, and then she is working for analytical chemist. She has got a offer from Germany. She will be going as a postdoc, and she is also working some industry. She was postdoc with me. She is also postdoc with me. Yeah, right. I thank you for your kind attention. Thank you very much. If you have any questions, I will be happy to answer your questions. Thank you.
Thank you so much, sir, for your such a valuable talk. I think all the participants have learned many things. So now I'm requesting any participants from student side, if you have any question or you can, this is a great opportunity for you to interact directly with sir, or if you have, you can share your views also. So any student, please unmute and share your views.
Yes, any questions?
So if not from student side, I am requesting Dr. Adinath Maji sir. He is an associate professor of Vishwabharati University, Department of Chemistry, Vishwabharati. So I am requesting you, sir, please say a few words regarding this today's lecture by Professor Jayatitya Ray sir.
Hello.
Sir, Adinath sir, please unmute your mic. Sir, please unmute your mic. Sir, unmute का कोई ऑप्शन नहीं है. सर सर यहाँ पर एक्सेस नहीं है. Adinath sir, can you hear me?
Hello.
Yes, sir.
Hello.
Yeah.
Yes. Now I actually host is not allowing me.
Okay, sir. Sorry for this.
Okay. So now, am I audible?
Yeah. Yes, yeah. Definitely, I'm able to hear you.
Okay. So thank you, Dr. Rao, for a very nice presentation and very good introduction, actually.
Okay.
Because what I can say that now it's a time to message to our society about the impact of green chemistry, I believe.
Yeah.
What I have seen, apart from chemistry, you have definitely. I'm not saying about the chemistry, because definitely about the chemistry we don't have so many things to say, because definitely you are doing
Sir,
a
sorry
very
to
good.
interrupt you. Sir, can you please start your video also?
Okay.
Okay.
You can see my video, isn't it?
Yeah, I can see, but can you see my video? I don't know.
I'm trying to see that. Yes.
Okay, so Dr. Rao, what I want to say, your introduction part, that is the social impact of green chemistry. It's very important. Till now, our Indian farmers, particularly from North India, they are burning their stubble, which is really a problematic issue. And till now, we could not convince them that we should stop it. And so I think, as a responsible person in our society, we have to do something, not only green chemistry in our lab. You have elaborately explained everything about the green chemistry, particularly the application of Bayes-Hellman reaction and your synthesis about the functionalization of chloro-nicotinaldehyde, also using the aldose reductase as a green reagent. So everything, what I can say that really it's a good impact, and it's very useful information for our undergraduate and postgraduate student, definitely. But what I want to say that I think this is a real time to do something about our society for the green chemistry. And just maybe just few words I can add as in conclusion, that you know that I am from Vishwabharati Shantiniketan, the university founded by Tagore. Okay, so now the Nobel laureate, first Nobel laureate, everyone knows it. And at long back in 1921, he thought about this. So he was not a scientist. He was an, a poet, or what we can say. But he thought that our villagers are waiting for the living touch of creative faith, and not for the cold aloofness of science, which uses efficient machinery for extracting statistics. That means, I think what I can say, that what we are doing in our laboratory, it should go to our society, to the villagers, that in such a way we have to explain everything, that what we are doing we should do in such a way that we can protect our environment. So and with respect to this, the today program is very nice, particularly the 4 green chemistry lecture, and your lecture, your presentation, I can say is definitely a very lucid and fine presentation. So I must thank you, and I must thank the organizer for giving me this opportunity to congratulate you, and that's all. Okay.
Yeah. Can I say something, Adinath?
Yeah, definitely.
I will put it. Kashi is not built in a day. Do you agree with me?
Yeah. Yes.
So we had to work at a phase wise to introduce this, put into the brains of younger generation, and they will adopt these rules, whatever green chemistry rule, and then go for a green chemistry only, not disturbing the environment.
Yes.
So I expect, these younger generation to help my, what you call is grandson and grandchildren, to be safe on this planet Earth.
Yes.
In a more philosophical way. Thank you.
Definitely. This is the sustainable development. Definitely. And we are also trying little bit, at least. Okay. Thank you.
Thank you so much, Dr. Agnath Maji sir, and thank you so much, Professor Rao. Now I'm requesting any other students, any other participants, if you want to share your views, please unmute your mic and say a few words. Yeah, Musarat, can you hear me? Musarat, can you hear me?
Hello?
So just a minute, sir. I think there is some technical problem.
Okay.
Resolve it within this.
I wait.
Yeah, very good evening, sir. Am I
Yes.
audible now?
Yeah. I can
Sorry
hear
for
you.
the inconvenience, sir. Actually, the host was not allowing me to on my mic, so I was not able to give give a brief introduction. Thank you so much, sir.
Yeah.
So first of all, I would like to introduce myself. I am Musarraf Shamim and I am from Jammu and Kashmir. I am a student of MSc Chemistry, University of Jammu, Jammu and Kashmir. And I would like to thank you for such a wonderful presentation, and how you started your presentation was eye-catching moment for me and everyone present here, I guess. So you have enlightened all the principles of green chemistry, and I don't think so there is any question left. Whatever you have discussed, you have described everything in one presentation. So as for me, so you have take us as for me, you have take us to the another world, that how we have to develop a green protocol, how we have to save our environment with the help of green chemistry. And I am lack of words. Every moment in the presentation was wow moment for me. And I am really, really thankful for you, sir, for your precious time. And I would like to thanks Department of Chemistry, Akal University, for giving us PG chemistry students this opportunity to learn something new in the recent trends, and as we are going with the flow. So definitely in future we will try to develop a green protocol for the synthesis of greener products and try to save our environment, because we are the younger generation, as you have asked about that we have to implement this in our future. So definitely we will try to follow this path. And thank you so much, sir, for inspiring us and for this wonderful lecture. Thank you so much, sir.
Thank you. Thank you for the compliments.
Thank you, Musarat. I am requesting Navneet. Please unmute and share your views.
Hey, sir. Good afternoon, sir. Sir, I'm Namni, research scholar, RIMT University. One thing I asked that the farmers can burn all the stubbles, but sir, there is a question regarding how much we farmers are educated, and the second thing is that our research work is published in English language, not in the regional language. So there is also a gap that what we are doing in a research work, they are not in a proper channel to provide the information to the farmers, how these are useful for us and how we can generate the value added product from them, just like we can make the biomass briquettes and porous carbon material from them. But they don't know how we can, how our government or our societies can help the farmers to provide the information to them.
Yes. Oh, very good question, Navneet Kaur. So what I would like to say is, you are the younger generation. You had to become entrepreneur. So what you have to do is, you had to read the literature available, how to convert that stubble into useful form of chemicals. So stubble is nothing but cellulose. Cellulose is nothing but polyglucose. So when you hydrolyze this cellulose under controlled condition, you should be in a position to get glucose, or something like disaccharide or trisaccharide, octasaccharide, something like that. You should get it. So are those chemicals are useful or not? You have to find out. So someone has to take lead. This information is available. There are quite a few people in the globe working also how to convert stubble into useful chemicals. The first useful chemical is the ethanol. Another chemical is furfuronaldehyde. That also you can get it. Okay, these are the two chemicals. Formaldehyde and ethanol. It is, formaldehyde and ethanol, they are already their commercial product which can be used. Besides that, can you convert into more useful products? It is a more or less a political thing, what I can see it by reading the newspapers and news channels, listening to it's a more political. You leave it aside, the political. Government will help you, Punjab government and also government of India, both will help you. If you have a good proposal to develop a process to convert that stubble into useful form of chemical. This will be a feedstock chemicals. It will go to a stage of feedstock chemicals. Okay, this is most important because India is agriculture based country, so we have lots of tons of stubble. So if you can get something out of it, it will be great. People are working, you can also make an attempt.
Yes, I can also work on that. But the question is that because I also live in the village, but no one is from the government side that they educate the farmers so that they can't do that. So what we can do here?
Farmers' protest is a purely political, so I cannot say anything on it. Okay, I cannot say anything on it because I'm not competent enough. I'm a scientist. I'm not a politician, so I cannot speak. Yes. Even if I speak on this, that will be, not relevant. Science, I can speak. I can tell you because I'm practicing chemistry. So what I suggested is stubble will be useful. That is how I say it.
Yes, sir. I know, sir. Thanks.
Thank you, Navneet. Now I'm requesting any student from Akali, from our department, like Viddeep, please unmute and share your views.
Sir, good afternoon, sir. Thank you for amazing lecture, and thank you for motivating us as I am belonging from the farmer background, and obviously I will try to give my efforts for the process extraction of ethanol from the stubble. Like these projects are eco-friendly due to relatively lower carbon dioxide and particulate emissions and displace fossil fuels such as coal. So it's very informative for us and a motivation for us. Thank you very much, sir.
No, the carbon dioxide increase also, it's a boon for us, honestly, because once you increase the percentage of carbon dioxide in the environment, we can grow trees like anything, because the trees will absorb the carbon dioxide, fix them as a carbohydrate, photosynthesis process. Our country, India, is we have lots of sunlight, so you have water also, monsoon. So it is a very good place to grow plants. Now we should grow the plants. That is what I feel. So that will help us. Onion was join out on sir. Right, sir. Then Khaled inga awal Khaled. Okay.
Thank you, Viddeep. Now I'm requesting Dr. Sujata Kundan. Please unmute yourself and share your views. Any other student from our university? Because it's a great opportunity for you people to interact with sir directly.
Yes, sir. Very good evening, sir. Sir, Sir, am I audible?
Yes, madam, please.
Sir, I am Manmeet Kaur from Chemistry Department of Akali University. A very thank you, sir. It's an honor for us to associate with you, and we are totally overwhelmed with your presentation, in which your hard work is purely reflected in a graceful manner, and definitely it has inspired us up to extent that we will put into a action so that we can also make a green chemistry development in the coming years. And moreover, I want to extend a special thanks for our faculty members who put efforts to create such a thoughtful event. Thank you, sir.
Okay, can I say something, madam?
Yes, sir.
See, people who want to go for job in industry, chemical industry, they are, have to go for this green chemistry only. The reason is very simple. The pollution control department or pollution control whatever thing of the each state has becoming stricter and stricter. They don't allow any chemical industry to throw chemical outside. They have to recover and recycle. There you have to do the green chemistry only. There is no other way. If they throw it, they have to pay a lot of fine or penalty. So you better learn from now itself what is green chemistry. Then you have a better position in when you join industry. That is my view. Thank you.
Thank you, sir. Thank you, sir.
Thank you so much, sir. Is there any participants want to share your views? So if not, then I'm requesting our HOD sir, Dr. Sandeep Kumar, for the vote of thanks. Thank you so much.
Thank you.
Thank you, Dr. Bhuvan. Thank you, Dr. Bhuvan. I'm feeling honored to present today's vote of thanks for such renowned personalities of today's conference. On the behalf of the entire fraternity of University, especially Department of Chemistry, I would like to express my humble gratitude to our guest of honor for today's one-day international national conference on recent trend in green chemistry. Professor A.K. Chakrabarty, Professor B.C. Rano, Dr. Navjeet Kaur, and Professor V. Jayatirtha Rao, sir. Thank you for being part of this conference. Especially they took out valuable time from their busy schedule and give us remarkable insight on such a contemporary topic. It is matter of great pride and great fortune that such prominent personalities share their knowledge with us. I appreciate and acknowledge the participants of this conference from various institutions whose wholehearted participation made this conference a success. This type of event can't happen overnight. I have been fortunate to be supported by my esteemed faculty members of Department of Chemistry. With deep sense of appreciation, I would like to thank them all for their dedication and untiring efforts to make this conference a success, and especially to Dr. Bhuban Banerjee for taking initiative for this conference. This event would not be successful without the support and guidance of our Honorable Vice Chancellor, Sir, Professor Gurmel Singh Ji, the most reverend personality of Akal University. His immense support and constant encouragement motivated us to conduct such an informative conference. We are so grateful for your support, sir. Last but not the least, I pass my sincere thanks to the technical team of Akal University, whose efforts made this event possible, especially to Mr. Sunil Ji and Mr. Pradeep Singh for their swift responses to our queries and requirements. Once again, I thank all the participants for attending the conference. Thank you all. Dr. Bhuban Banerjee, sir.
Thank you so much, sir. And thank you all the participants for your valuable time. Hope you all enjoyed a lot. And thank you so much, Professor Rao. Thank you so much for your valuable time. Hope in future we will organize some offline conference also. And that time we can invite you here at Akal University.
Oh, that was great.
Yeah, thank you so much, sir, for your valuable time. Thank you so much. Have a nice day.
Taking off.
Okay, thank you. So, dear participants, we are now leaving this meeting. Thank you. Thanks a lot.
Thank you.
Thank you, sir. Have a nice time ahead.
Thank you.
Thank you, sir.